and it was super nice. Walks on the beach, and super great food and great science. Yeah, I hope you can do it live again soon. Okay, so first thing, I'm supposed to give a review talk, and this is a very old subject, and okay, we started working on it maybe about 6-7 years ago, so there's already a lot of work, and I list here all the collaborators that I've worked with on this topic. So I will cover the main algorithm that is being used, but I will focus on one specific application. Okay, so I will not make like an exhaustive review where every slide is a different topic and it's impossible to follow. Okay. So, but before that, let me just admit that I'm very much outdated. So the right title should be this one. The movie just came out yesterday, I think. So if you like the old Matrix Reloaded, maybe you will also like this new one. I haven't seen it yet, so let's see. Okay, so this is the outline. So as I said, I will focus on this example of 2-to-2 graviton scattering, and I will explain the main algorithm for this non-perturbative S-matrix bootstrap in this context. Okay, but I hope we will have some time for a big discussion on more open problems and general directions. So let me start in the beginning. So the beginning, I think, is during the war, actually, when Heisenberg wrote a series of papers with this title, The Observable Quantities in the Theory of Elementary Particles. And the motivation was actually quite modern in the sense that he was thinking, well, he was troubled by the infinities that appear in perturbative calculations in quantum field theory. So at the time, this was still very poorly understood. And so we thought, well, let's think about physical observables, like scattering events. So he formulated the properties of the S-matrix as a physical observable, and he tried to understand what were the main properties that these physical observables have to obey. Okay, so then later on, this really became very popular in the 60s, essentially in the context of the strong interaction. So in that context, you have many hadrons, many resonances, and well, one can measure some cross-sections, some scattering amplitudes between these objects, and there is no field theoretical calculation to predict this, right? Because it's a strongly coupled theory. So the idea that became very popular was this idea of nuclear democracy, that all particles are equal. There's no elementary particles and composites. They should all be treated equal. And well, actually, this was very much based on the idea of Regge trajectories, that all particles fall on Regge trajectories. So they are really tied together, and the full consistency of the theory should fix the theory entirely. So here you have Jeffrey Hsu, which was the main promoter of this idea. In fact, I think people used to say there is no God but Mandelstam, and Hsu is his prophet. Okay. So, but it seems that Mandelstam himself was a bit of an agnostic. He never really subscribed to this bootstrap gospel entirely. He would usually went back to quantum field theory calculations to check his ideas. But this was very popular in the 60s. But this idea that you could fix the theory entirely just from consistency properties of the S-matrix, in the end, basically it failed, and it had to fail because we know there are many consistent quantum field theories. So we're not going to find a unique solution. We are going to find some space of allowed solutions. Well, nevertheless, this was actually very fruitful because it gave rise to string theory. For example, the Veneziano amplitude was written as an example of this amplitude that contains all particles in Regge trajectories. And another related topic is S-matrices in 2 dimensions, where if you assume integrability, no particle production, then in the late 70s and early 80s, there was a lot of progress. People really just solved some 2D quantum field theories by bootstrapping the S-matrix, by guessing the S-matrix just from first principles, plus this principle of integrability, of no particle production. Okay? So this was led by the Zamologikovs. But in higher dimensions, not much progress was done until more recently, and the motivation from that came from a parallel program, which you know very well, which is the conformal bootstrap program, that started a bit later in higher dimensions. So these were the, if you want, the seminal papers. But these papers really didn't have too much impact because at the time, okay, these are very complicated equations. What are we going to do with this? It was a bit unclear. The big impact came when it was applied to 2 dimensions in this famous paper, the BPZ paper. And there you know the story, right? Minimal models, conformal field theory. It was an explosion of work, but it was, again, very much limited to 2 dimensions, where conformal symmetry is infinite dimension. So the main breakthrough in higher dimensions came with this paper in 2008 by our friends here. And this is where I was, okay? So I was working on the conformal bootstrap with applications to holography, conformal blocks. I was thinking about this. And in the back of my mind was this problem: why this works so well for conformal field theory? Like, for example, we know this beautiful success story where you can map the space of theories and isolate theories with super high precision in these small islands. How come this works so well for conformal field theories, and the same idea just does not work for massive quantum field theory? What are we doing wrong? And yeah, that was basically the origin of our work, was to try to apply exactly the same philosophy that was so successful in the conformal case to the non-conformal case. And the philosophy, let me just tell you the main steps. You choose an observable, physical observable, then you list the consistency conditions, and then you use that to bound the space of theories, right? So it's very simple algorithm. And we knew how to do it in principle, right? I mean, this table, I think everybody more or less knew how to do this table 50 years ago, or maybe, okay, let's say 10 years ago for sure. Okay, so this was the table of the analogy. You pick an observable. So in conformal field theory, the good observable to pick is the 4-point function. Sorry, this is just distracting you here. The 4-point function, and in massive quantum field theory, the natural observable to pick is the 2-to-2 scattering amplitude. Okay, so again, here there's a kind of an art. You have to choose an observable that is sufficiently rich to constrain the theory and sufficiently simple to work with. Okay, so somehow the balance is when you get to a function of 2 variables. So that's what experience has taught us so far. And so that's the good analogy. And then, okay, you have crossing symmetry, which here is just permutation of the external points, and here is permutation under the Mandelstam invariance, and then you have the use of the Hilbert space. So you decompose the Hilbert space in irreducible representations of your symmetry group. So this is what I was doing here. So you insert here the resolution of the identity, And if you do it in conformal field theory, you get an expansion of the 4-point function in conformal blocks. And if you do it in scattering amplitudes, you get an expansion of the amplitude in partial waves. And then the last constraint is unitarity. So these coefficients, these lambdas, are squares of OP coefficients, so they're positive. And in the scattering case, these Fs can be put together to form probabilities of going from 2 to 2 particles with fixed spin L, and so they are bounded by 1. Okay, so you see that actually the last line is different. You see that the nature of the constraint is slightly different, and that actually, there's where it lies many of the difficulties in translating, direct translation of the methods of conformal field theory to the S-matrix. Okay, so this was where we were, if you want, 10 years ago. And since we were so confident about conformal field theory, the first thing we tried to do was really to say, well, maybe the S-matrix is too difficult. People have thought about this for many decades. Let's try to use the conformal bootstrap to get bounds about quantum field theory, massive quantum field theory. And the way to do that is to put the quantum field theory in ADS. Okay, so that was our first eureka moment, if you want, was when we tried this. We put a quantum field theory in ADS, and then we tried to use the bootstrap, the conformal bootstrap, for boundary correlation functions to get information. Well, if you want, you have boundary correlation functions, like the 4-point function here, to get information about the S-matrix, if you want here. And I mean, the eureka moment was this plot. And I think this was about in 2015 or something. I was at CERN, and we were able to make this plot where we showed that so if you take this flat space limit seriously, you predict that dimensions of scalar operators scale like the radius, m times the radius, and the OP coefficients scale like scale exponentially with the dimensions. Okay, so the dimensions go to infinity in the flat space limit, right? This goes to infinity, and so you see that there is this exponential dependence that you can really predict just by computing this diagram in ADS, a simple diagram that you can compute that relates OP coefficients to bulk couplings. And the remarkable thing that we found is that by doing the numerics in ADS, so by finding a upper bound on the OP coefficient, as you increase delta, we actually matched precisely the slope predicted by this calculation. So we were able to derive bounds in flat space by extrapolating the conformal bootstrap to infinite radius. Okay, so this is okay, not. I realize this is quite fast. I'm not giving you all the details. This is just a personal note of how we actually entered this this topic. Yes.
Sorry. So this work I'm familiar with in 2 dimensions, right? I mean, in higher dimensions also you have this paper, but is there a very clear understanding of the ADS bounds going over to the flat space bounds?
Yeah, good question. Exactly. So this is this success was in 2-dimensional bulk theory, and so far we have not been able to make the numerics work in higher dimensions, but I believe that's a numerical.
I see. So you're saying that's
numerical difficult, because you see here, you can see it here. You see that to see this slope that was predicted, you have to first try this n is the number of derivatives in the usual conformal bootstrap. So you have to go to very high number, 200, and then still, 200 is still here. So then you still have to extrapolate with some fits in 1 over n to get down to the orange curve, which is the extrapolation curve. So this is completely out of reach in higher dimensions. But that's a very good question, because that's exactly what I wanted.
So you believe that's only a numerical issue, that it will go down and be either in the flat space curve?
Yeah, I believe it's a numerical issue. Yeah. But it's very important, because it basically tells you that you're not going to be successful by only using this approach. So, well, let me just finish what I wanted to say. So what we did then, two-dimensional conformal field theory. I think there is a lot of feedback. Yeah, there is echo. Maybe you can mute yourself. Okay. So what I was saying is that, you can do this for fixed ratios of the delta 2 over delta 1, which corresponds to the ratios of the masses in flat space. And from this conformal bootstrap extrapolation, you get these red dots on the bounds of cubic couplings in flat space. And then, since we get this nice bound, we try to derive it directly from S-matrix. And we indeed, in this case, is actually very simple. So you actually can derive an analytic formula. And you see here that the blue curve matches precisely the red dots. Okay, so this was our first success. And let me just tell you this funny fact. So after we did this, we found out that actually this formula for 2D S-matrix bootstrap was already done in a very nice 2-page paper by Michael Kreutz in '72. And this beautiful 2-page paper, it's very, very nice and clean derivation just using complex analysis, had 0 citations for 40 years. Okay, so this is I think this is the example I know of some very good paper being completely unnoticed for 40 years, and then now I think it has about 10. I don't know. It's not a lot, but at least it's recognized as a very good paper. Okay. So this is the end of my broad historical introduction with some personal notes, and now I want to focus on a very more specific application of the S-matrix bootstrap directly in higher dimensions, and in particular I will focus on one example. Okay, so the S-matrix bootstrap is just a general method that you can use to bound properties of the S-matrix. So in particular, you can apply it to the S-matrix of massless particles of some effective field theory and bound Wilson coefficients. Okay, so that's a big industry, an important topic. And so we've done that in several models, like the flux tube in 2-dimensional flux tube of a confining gauge theory, or the pions, so the chiral Lagrangian. We're also working on photons, so the Euler-Heisenberg Lagrangian, but I cannot explain everything in a reasonable way in one talk, so I will focus on one application, and the method is more or less the same, it's just the different application that changes. Okay, so any question about the big picture, or before I go into explaining this specific application?
So I never really understood how the massive case was brought into this picture. You said the initial motivation was that, right?
Yes. So massive is even simpler than massless, like I'm doing here. So because here I'm doing massless theories, they have massless particles, but they're not conformal field theories. So they fall in the same class of quantum field theories, which are only Poincare invariant. So you cannot use conformal bootstrap anyway, right? So it's in that sense as difficult as a mass gap, and in fact it's harder. If you have a mass gap, your numerics converge better, you have more theorems about some analyticity domains. So I could also talk about that. There is also results on, say, bounds on quartic couplings, if you want, or cubic couplings in theories with a mass gap. Well, actually, the one I'm showing you here had a mass gap, right? This was massive particles, but this was two-dimensional. We now have done also higher dimensions, but numerically, right? We don't have an analytic formula like this one. Did I answer your question?
Yeah.
Okay, thank you.
Hi, Joao, can I ask just one small question? So with the gravitons in the, when you do S-matrix bootstrap with gravitons, are you assuming crossing or is there some?
Yes, so I will explain that. Okay. Of course, if you're just doing scattering amplitudes in quantum field theory, it's a much more solid background, right? You have some things you can prove starting from, let's say, LSZ definition of the scattering amplitude. So you can prove crossing, or you can prove some analyticity domains and things like that. In the gravitational case, we don't have that luxury. So we will, essentially what we will assume is that the properties we see in amplitudes that we compute in the effective field theory, order by order, in the low energy expansion, persist to all orders. Say the crossing and analyticity that we see in perturbative graviton scattering amplitudes, we're going to assume they exist. They are also true non-perturbative, but that's definitely an assumption. We don't have a first principle proof of that.
Right. Okay. Thank you.
Okay. So let me just explain the problem. Okay. So now this is about the problem. So the problem is about higher derivative corrections to gravity. So GR is the low energy effective field theory, and you want to know what bounds can you put on the Wilson coefficients of the higher derivative corrections. So we will do this in the simplest possible context, which is maximal supergravity in 10 dimensions. Okay, so it's simpler because supersymmetry helps you deal with all the complexities of the helicities. And the way it does it is this formula. So we're going to focus on the 2-to-2 scattering of gravitons, or in fact the full supermultiplet. And supersymmetry, maximal supersymmetry, tells us that this full amplitude is fixed up to a scalar function, which is fully crossing symmetric of the Mandelstam invariance. Okay, so there's a prefactor that takes care of the helicities and which particle in the super multiplet of the graviton you want to focus on. Okay, so that's why this is a simpler problem, and we started with this problem. And then what do we know about this? Well, we know the low energy behavior that supergravity predicts. So in fact, it will be useful to focus on a particular component, which we'll call T, which is the scattering amplitude of two charged scalars. Okay, so these charged scalars, they are just some spin zero components of the supermultiplet. So for example, in type 2b is the axi dilaton. And so this T, so this factor R for these charged scalars just reduces to s to the fourth, the Mandelstam invariant. It's as simple as that. And you see that the prediction from supergravity is very simple. It's just the T and the U channel exchange of a graviton between two charged scalars, two identical charged scalars. And so in the second line, I wrote the corrections. So now this T, okay, this is exactly, I mean, this factor and this factor are the same. They might not look, but it's really trivial algebra. And the first correction to supergravity, which is this term, is a constant. And this is the main focus of this talk. Okay, so this constant is directly related to the first Wilson coefficient in the effective action of 10-dimensional supergravity, or the UV completion of supergravity that preserves maximal supersymmetry. And the first correction appears exactly at r⁴. Okay, so, but I mean, alpha for me, it will really be this coefficient in the scattering amplitude. And notice it's a dimensionless parameter because I'm measuring everything in Planck units. Okay? So that's the definition. The question we're gonna ask is, what are the possible values that alpha can take compatible with having a unitary and analytic S-matrix, okay, and causal S-matrix. And what do we know about alpha? Well, we know quite a lot because we have string theory, and in string theories, alpha can be computed exactly, both in type 2a and in type 2b. So let's look at type 2a first. You have here a very simple formula, elementary formula in terms of the string coupling of type 2a, and you can plot it, and you see it as a minimum. So the allowed values of alpha in type 2a start from 0.14 and go to infinity. And you see actually infinity corresponds to weak coupling in string theory. And there's a similar story for type 2b. Here it's a bit more complicated because you have a complexified string coupling. So the alpha is this Eisenstein, non-holomorphic Eisenstein series on the fundamental domain. But again, you can plot it, and you see that the minimum happens here at the cusp of the fundamental domain, and it's again about 0.14. Okay. So this is what we learned from string theory. Alpha above 0.14 should be healthy. We know UV completions of supergravity that have that alpha. Then another thing we know is that we know alpha must be positive. Okay, so that follows from some simple argument. You can just go to the S complex plane at fixed t and do some standard dispersive arguments to derive this sum rule. So you see that you have an integral over the imaginary part of forward scattering. So this is positive by the optical theorem, and therefore alpha must be positive. You can also check that this is IR finite, so you can compute the IR behavior of this imaginary part just from the effective field theory. It's just a one loop calculation effective field theory, and you see it starts as s to the fifth. It cancels this prefactor. So this is a perfectly UV IR finite sum rule for alpha. So alpha is positive. So that's the summary. A priori, we know that alpha is positive, so this is impossible. Let's call it the desert. That alpha bigger than 0.14 must be possible because it exists in string theory, so we call it the garden. And there's a gap, very small in the middle, which we don't know. Are there any UV completions of supergravity that have alpha less than 0.14? Okay, so that's the question that we can address with the S-matrix Bootstrap. Is it clear? Is the question clear? So now I will explain how the S-matrix Bootstrap can address this question, but it's important that the question is clear.
Yes.
Thank you. Okay, so as I said, this is a general algorithm. So what is the algorithm? There's basically three steps in the algorithm. First, we just write an ansatz that obeys all these properties. Exactly, okay? So here there's no approximation, it just does this exactly. Okay, so again, I already mentioned this, but let me emphasize that we assume, so we will impose the strongest form analyticity, sometimes called Mandeltham analyticity, which even in quantum field theory is not proven. So We will assume, yes.
Sorry. If I may just ask, like, I'm a bit confused that there is actually a lower bound. I mean, I would have normally thought any small alpha would be allowed, but if it's...
Sorry, I couldn't really understand. The sound is a bit cut.
Sorry, I was asking, like, why isn't some infinitesimal alpha not allowed? Could you kind of repeat that argument?
Why alpha negative is not allowed?
No, his question is, why is an infinitesimal alpha not allowed?
Positive, let's say, alpha.
Infinite alpha is allowed, yes. But that's just weakly coupled string theory does that.
No, the question is infinitesimal, so very small alpha. Why is that not allowed? He wants to know.
Okay, good. Sorry, I really, the sound is really difficult. I mean, as I said, here, a priori, we don't know, but that's a question. I don't think there is any reason why alpha, so you're asking why alpha cannot be 0?
Yes. Yeah.
Well, we will argue that it cannot. I mean, if you want an intuitive explanation, is the fact that GR by itself is not UV complete, right? If you just take supergravity, the amplitude violates unitarity. It grows too fast with energy. So it needs to be UV completed. And it could be that alpha is 0, but maybe not. We're going to argue, and the numerics tells us that in any UV completion, alpha actually has to be bigger than about 0.14. So, but it's non-obvious. But yeah.
Can we not make the observation that the imaginary part in the forward limit is related to total scattering cross section, which I mean, typically is not. I mean, if it was 0, then it would correspond to 0's total scattering cross section.
Yes, very good, Aninda. Yes, that's a better argument. So if alpha was exactly 0, it would mean that there was no scattering. Yeah, right, because this forward amplitude is related to total cross section. But okay, you could still think that it could be infinitesimal, but yeah, there is an actual finite bound in units in Planck units. Yeah. Thanks, Aninda. Yeah, that's the better answer.
I thought 0.14 was a string theory computation that you got from string theory, right?
Yeah. 0.14 is a string theory. I'm jumping ahead. So we will see that the numerics give a similar result. I'm jumping ahead. So I get a lot of feedback from TFR. If you have a question, ask, but otherwise it's better if you mute, but you get a lot of feedback.
Yeah, I don't think they have a question right now. Please.
Okay, I will continue. Okay, so I was here. There's 3 steps in the algorithm. The first one is an ansatz that obeys all this exactly. I will explain in detail how that is done. The second one is to impose unitarity. And here we do it by decomposing in partial waves and imposing unitarity of each partial wave. So this we cannot do analytically. So we formulate this and we give these constraints to the computer. And then it becomes an optimization problem. You minimize alpha in this case, right? Choose some observable of the amplitude. In this case, we're going to focus on this alpha parameter, but we can do many other things. So let me give you just one more refinement that is crucial, is that this ansatz will have a large number of parameters. Well, it will have a number of parameters, finite number of parameters that will be of order n squared. So this n is crucial because we will have to extrapolate to large n to cover the full space of S matrices with these properties. Okay, so there's an infinite function space, infinite dimensional function space, and so we need to send this n to infinity. And there's another important parameter, which is the number of unitarity constraints we put, which again cannot be infinity because we're doing it numerically. So there's another finite parameter L, which is up to which partial wave we impose unitarity, which we will have to extrapolate. Okay, so there's a final step of extrapolation in this algorithm. Okay, now I will go 1, 2, 3, 4 with equations. Okay, so 1. That's it. Okay, that's the ansatz. So it's actually quite simple once you think about it. So so this is supergravity. Okay, so we just put it explicitly, and then we add this big sum. And what is the property of this big sum? Well, it's like a triple Taylor expansion in these variables, rho s, rho t, rho u. And what are these variables? These are just maps from the cut plane, S minus the cut from 0 to infinity, where you expect the discontinuities from particle production in a massless theory, so it starts from 0. And rho is just a unit disk. Okay, so this is just an elementary map, that holomorphic map that brings the plane to the unit disk. And so the assumption of Mandelstam analyticity enters here. We're saying that functions are, that the S-matrix is analytic in this cut plane. So it's analytic in this disk. Therefore, it can be well approximated by this Taylor series. And n is this truncation, okay? And the parameters are the coefficients of this Taylor series. And crossing is trivial to implement. We just make this tensor symmetric so that it's permutation invariant under STU. Strictly speaking, what we're doing is an extension, right? This is, I'm writing it as a function of 3 variables, S, T, and U. Of course, what matters is the restriction to this physical set S plus T plus U equals 0. And that's the way we implement crossing by extending to 3 variables and then restricting. Okay.
Now, can I ask a small question? Yeah. Can I? So, I mean, because we have these multi-particle cuts. I mean, we don't expect this sum to converge point by point in S, right? I mean, this. I mean, are you assuming some convergence of the sum in the?
Yes, that's a very good point, and it's a subtle point with this method, right? So you're saying you will have like branch points. Well, not here actually. Well, in a massless theory, all branch points accumulate.
Yeah. Even in a gap theory,
so you will have You will have branch points always here, but that's enough for your argument, right? You will have a branch point at the boundary. So the boundary of the unit disk is the radius of convergence. Is really the limit of the radius of convergence of this Taylor series.
Right.
So when we now are going to evaluate the amplitude exactly at here, we seem to evaluate it at the limit of the convergence.
Yes.
Maybe I missed something, but
sorry, just to so what is the I didn't understand the answer. The radius of convergence is 0, strictly speaking, in this case, right?
No, the radius of convergence is 1, is the disk, right? Because the maybe I should mark here with another color. I don't know, maybe this. So here the center is in my unit is S equal -1 in Planck units.
Okay, thanks.
So it's fine. There is a finite radius of convergence, but still you can worry that when we're going to evaluate the F-matrix in the physical domain, it's going to be exactly at the boundary.
Yes.
And I guess the most honest answer is that it works. If it didn't work, this could be the reason. Then a posteriori, we can explain. So let's just say it like that. I'm creating a set of S matrices that have the right analyticity and the right all the right properties. Now you could worry that they do not really cover the full exact S-matrix, because when you send n to infinity, then it will not converge at the boundary. Okay, so there could be a problem of convergence as n go to infinity. And so numerically, we see that that works, so we don't observe this problem. In practice, I suspect, but this has not been cleared up, that this has to do with the fact that unitarity, in fact, the S-matrix, strictly speaking, should be thought of as distribution. So, in fact, you should not evaluate unitarity pointwise. You should make like some small wave packets. And so in practice, what that can be thought of is like just evaluating the S-matrix slightly inside. So if you evaluate slightly inside, is like putting a small wave packet, and that would smooth out the
thank you.
convergence. But yeah. Was there another question?
Yeah, so I thought the higher order correction, the R4 term was just alpha times s to the 4. So what are you doing right now?
Right, but to bound this term, what we have to do is to really build the full S-matrix. And then in the space of the full S-matrix, where like we go to all S and T and U, we then check that it's compatible, and then we go and measure what was the alpha. Okay, so of course, to get the alpha, okay, maybe that I didn't say, but to get the alpha, you have to go here and Taylor expand around s equals 0, and this will start as a constant. In fact, this is what this prime means. You have to put some restrictions in this sum so that it indeed starts as the effective field theory that we want. And there's also some other technical restrictions that it has good high energy behavior and all that. But this prime.
Okay, so now you're trying to
some
match
extra
the
constraints that I'm not telling you about.
You're trying to match the effective field theory computation with the string theory computation. Is that what you're trying to do?
No, here there's no string theory, there's nothing. I'm just trying to write an S-matrix, full S-matrix for all energies that is consistent. And then I'm going to measure the alpha. And I'm going to try many, many S-matrices to see what is the smallest alpha that I can get in an S-matrix, but that is good to all energies.
Yeah, but the initial computation of alpha that you got was in the string theory, right?
This was just to check that this was just like some a priori expectations for what alpha can be. I used the fact that we have some UV completions of supergravity that we trust, namely string theory.
But in order
in particular, we don't know
can I just advise that you can ask the question maybe after the talk, because already 44 minutes are up. So maybe we should allow Joao to continue.
Yes. Okay. I will try to answer that better. I'm probably repeating myself. Okay. So so that was first step. Step number 2 is unitarity. Well, there's some equations here, but not very important, the details. The main thing is that unitarity for the full super amplitude simplifies drastically using this identity of this prefactor. So this prefactor has this property that if you sum over the polarizations of the internal particle, it reproduces itself up to s to the 4. Okay, so that's the essential property that we use. And using this property, one can show that unitarity of the full 2-to-2 supermultiplet is equivalent to unitarity of this charge scalar. And that's the great simplification. So in practice, we just impose unitarity of the charge scalar. Okay, so you have two identical charge scalars. You expand in partial waves in the S channel. So this is the standard way of expanding partial waves. You take the amplitude, you integrate with the corresponding 𝗰𝗵𝗶𝗶 polynomial, and that gives you the partial amplitude for a total energy square root of S and total angular momentum L. And the square is the probability from going to two gravitons to from two charge scalars to two charge scalars. and that has to be bounded by 1. So it's as simple as that. The great property of this is that you see this S is linear in T. So this will give rise to quadratic constraints in our parameters beta. Okay, so these beta are our free parameters. They enter linearly in the amplitude. So these are quadratic constraints, but there are many of them. There is one constraint for every S from bigger than 0. So the way we implement this is with a very dense grid of points from 0 to infinity. And then there is one for every L from 0 to capital L, from 0 to infinity, and we truncate at capital L, and this is the parameter we need to extrapolate in. Okay. So that's unitarity. And now we're done. We can now just give the problem to the computer. And as I said, it's a problem with quadratic constraints, so it's called a semi-definite programming problem, and it can be solved very efficiently using the numerical algorithm that Simon Zafin wrote for the conformal bootstrap, this SDPB code. So I'm already showing you here the results in this plot as a function of the two parameters, L and N. I recall that L is the number of constraints. So as you increase L, it's harder to minimize alpha, right? We're trying to minimize alpha. If we put more constraints, it's harder. So it grows with L. And N is the other way around. So N is our freedom. So as you increase N, you are able to minimize more because you have more freedom in your ansatz. So now what we do is the extrapolation. That's the step number 4. So what we will do first is to extrapolate in L to infinity. So that seems to be rather easy because you see you have these big plateaus. So for fixed N, when you go L to infinity, you get some nice plateau that you can extrapolate to infinity. So this is what I'm showing you here. For example, here, so for N equals 13, we extrapolate here. 14 here, 15, okay. And we actually extrapolate, we can estimate the error by extrapolating with slightly different powers of 1 over L and choosing slightly different points. So we estimate the error. And then we extrapolate again to N equals infinity. So first infinite constraints and then infinite freedom. And well, the result is what I already anticipated, that these two extrapolations lead precisely to a value around 0.14. Okay? So there is still some error. As you can see here, the error is significant because these numerics are quite challenging, but it's very suggestive that indeed the bound coincides with what is realized in string theory. And let me just, so when we do this, we don't get just the minimum value of alpha, we get the full S-matrix because we get all the parameters that minimize, for which alpha is minimized. So we can look at the S-matrix, and in particular, we can look, sorry, this is just a summary of where, of what we got, okay. It's, these numerical results match what we expected from string theory. And as I said, we can look at the S-matrix, and in particular, we can look at the sum rule. Okay, so alpha verify this sum rule. We can look at how does our optimal solution that has the minimum alpha satisfies the sum rule. So we plot here the integrand, and you see that the integrand has a very characteristic peak, which corresponds to a resonance. And we can actually see this resonance in, it's a spin 0 resonance, and you can see it if we look at the spin 0 phase shift. We see that the spin 0 phase shift indeed crosses pi over 2 like it should in any resonance at around, well, 3 times the Planck mass square. Okay. So this resonance, you can call it a gravitons following these authors that found a similar resonance in 4D gravitational scattering. And well, I guess it's tempting to identify this resonance as the lightest massive string states that, of course, as you turn on the string coupling, it becomes a resonance. And okay, maybe this is the lightest massive string state in string theory. Okay, this is all I wanted to say about this example. I'm not sure how much time do I have, or if there are some time for questions before I go into the final discussion.
Yeah, so around 9 minutes, that is the, so you have around 9 minutes left.
Sounds good, sounds good. Is there any question about this example before I now move to a broader discussion?
Sorry, Joao, just one quick question. So the previous S0, you got S0, and I mean, as in the SL, the delta L equal to 0 is real. So even at large S, your SL mod SL is just 1, right? I mean, is that?
That's a very good question. So you're asking about particle production, right?
Yeah.
Saturated in the 2-to-2 channel. Numerically, what we see is that at low energy and low spin, unitarity tends to be saturated. But I mean, for this finite value of n equals 24, as you go to higher energies, you will see deviations from mod. So let me write it. So mod of SL will be less than 1 at higher energy. So if you plot it, it's going to be something like if you plot mod of S0, for example, as a function of S, it will start here at 1, we'll have some oscillations, but then at higher energy, we'll have some more oscillations. Okay, so that's the typical scenario with a finite number of variables. But what we see is that if you increase n, then these wiggles go a bit further and become smaller. So this is n increasing like that. Okay, so in some sense, it seems that the numerics want to really be fully elastic, that the optimal scattering amplitude wants to be fully elastic. But in fact, it can never get there because there's even some theorems that in higher dimensions, you cannot get a fully elastic S-matrix. There's always at least some asymptotic inelasticity at large spin. I hope I answered it.
Yeah, thanks.
TIFR has a question. TIFR, unmute yourself.
Hi, Joao. Yeah, I have a question about this alpha that you want to measure. So the way you defined it as the coefficient of this term in the Wilson interaction, one of the Wilson coefficients. But your S-matrix had all sorts of features all the way up to 0. So in principle, how does one pull out this particular Wilson coefficient from there? And second question is, the way you parameterize your S-matrix, it seemed to make this even more difficult because you expanded at S equal to 1. And how would you get anything near S equal to 0?
Yeah, okay, this is a good question. So to identify alpha, so alpha for me is really defined from this expansion of the S-matrix, okay? So the relation with this effective action is just because we know it, but I'm not using the effective action at all. It's just a Taylor expansion around S equals 0. Actually, around STU equals 0 with the same ratio. So it's really a low energy expansion.
Sorry, but you cannot do the expansion.
So technically, yeah, you're right. Since the rows are defined centered around here, this point S equal -1, basically all terms in principle contribute. But you see, at finite n, this is just trivial algebra. It's just some polynomial. I just expand. So at finite n, I can just do it. I can take my ansatz and expand around this point, because it's just a finite sum. So I can expand it around this s equals 0 point, which is what I need to do to measure alpha. So that's what we do.
Sorry, if the chair allows, I can just pursue this a little bit more.
I couldn't understand.
Yeah, can you repeat that? Yeah, I also couldn't hear you.
No, I just meant, if you allow me, I can ask a little bit more about this now, or should I wait?
Joao, do you want to finish the discussion and then take questions?
Maybe it's better. Otherwise,
Please,
I like. Yeah. Usually, it's better to take questions because people don't ask many. But in India, is a very good culture of asking many questions. So maybe let me finish. So, okay. So I have a few slides of general remarks. So the first is about generalizations of this problem. So the obvious thing to go to study is to study different space-time dimensions, still with maximal supersymmetry. And in particular, I think d equal 11 should be very interesting, because in d equal 11, what we know from M theory is a single number. There is no free parameter, so alpha in M theory can only take one value. And I wonder what the S-matrix can tell us about that. Yeah, so that's an open question. Of course, it would also be very interesting to do 4 dimensions, but there we have a conceptual obstacle, because there the S-matrix, strictly speaking, is not well defined. There are infrared divergences. So one needs to define some finite quantity and then understand its properties, so that we can run this game of having a physical observable and its consistency conditions, and then get bounds from that. Okay, so in 4 dimensions, I think there is a lot of conceptual work to do I mean, there are proposals in the literature about IR-safe dressed S-matrices, but as far as I know, nobody really tried to list the rules that this dressed S-matrix satisfies so that we can run the bootstrap. In particular, I think unitarity should be quite non-trivial for these dressed S-matrices. Then another comment is inelasticity. So we already talked about that. So there is some inelasticity that we expect from black hole production at high energies, and also from 3 graviton production at low energies, 3 and 4. So we can also compute that in the effective field theory. So we could try to make a better model. Instead of just saying S is bounded by 1, we could say S is bounded by some function that we compute using low and high energy knowledge from gravity, and see how that changes the bound. And well, of course, no SUSY and other Wilson coefficients, I think, would be very interesting, because in string theory, then you can start to play with like 2-dimensional allowed regions and things like that. So I think the most important and most present thing is to have a better numerical formulation. And this is what we are working on, because really we are hitting the wall with this numerical algorithm that I presented. And the better numerics are usually the dual algorithms. Okay, so this is some technical thing in optimization problems. You can have primal methods and dual methods. And essentially the difference is that in the primal method, you actually build a solution and you approach the optimal from within, like we did. While in the dual method, you build some functional that excludes solutions, and you approach the optimal bound from outside. And it turns out that usually the dual methods are more efficient. And that's exactly, actually, in conformal field theory, what is used is a dual method. So that's part of the reason the conformal bootstrap is so successful. So it will be important to develop dual methods for the S-matrix bootstrap. And there's already a lot of work in that direction, especially in 2 dimensions. In d greater than 2, there is only these 2 papers. And this paper in particular from Andrea and Amit is very interesting, because they are able to set up a dual method only using proven analyticity assumptions in quantum field theory. The disadvantage is that they can only do it for theories with a mass gap. Okay, so it doesn't apply to this specific problem, but for theories with a mass gap, there is now a dual method that is completely safe, even in terms of analyticity assumptions. This method assumes Mandelstam analyticity, so in principle, it can be applied to massless, but yeah, we need to explore it more. So far, the result is, there is only this paper, we are working on it. So I think this is a very important frontier in the topic. So I wanted to make a comment between what we're doing and between what many people, other people are doing, including Aninda, and emphasize the difference. Okay, so unitarity can be written like this condition. Okay, so this is just writing SL in this standard form, and you see the non-linear condition. And there is a weaker condition that follows from it, which is positivity. And positivity is already a very strong condition that has been used to derive many bounds in Wilson coefficients. But let me just tell you what happens in this example. So in the example that we have studied, positivity can never give better than alpha greater than 0, because the supergravity amplitude is already real. So the imaginary part is 0. So there is no problem with the pure supergravity amplitude. So positivity will never improve this bound. To get a bound like this, you really need nonlinear unitarity. Okay. So the advantage of working with positivity is that you can do lots of analytic stuff and dual numerical stuff, very systematic, and so better numerics. The nonlinear part is harder, as I explained, and so I think there is a lot of room to improve and try to translate or update some of these better methods that have been developed for positivity to the nonlinear case. I think this is a very important thing to do. And I'm probably running out of time. Okay. So my final comment is about when you actually want to study a quantum field theory, you know stuff about the quantum field theory usually, right? So in QCD, we know the UV, right? We know that quarks and gluons are free at short distances. And so we know something about pion scattering. We know, for example, hard scattering, okay? So can we input some information into the S-matrix Bootstrap that specifies what is the UV theory of the quantum field theory we want to study? So this is a very important question that is mostly open, but we've done some progress. So here I show you one example. So in 2 dimensions, you can access the central charge of the UV CFT by doing a kind of a mixed bootstrap that joins the S matrix with form factors and spectral densities of the trace of the stress tensor. And so I'm showing you here a plot. If you assume a 2D quantum field theory with this spectrum, so with a ON global symmetry and with this mass spectrum, then there is a lower bound on the UV CFT, the central charge of the UV CFT that grows with N. Okay, so that's one example where you relate UV CFT behavior with the S-matrix Bootstrap. And we're doing something similar in 4 dimensions using the dilaton scattering. Okay, so by putting together the scattering of physical particles with this probe dilaton of Kolmogorski-Schwimmer, we are able to access the A anomaly of a 4D quantum field theory together with the S-matrix Bootstrap. Okay, but this is still work in progress. So, and since I didn't have time to cover all the many open problems that are in the topic, let me encourage you to go and see the slides of the discussion session that Sasha and I prepared for the strings, where you have a big list of open problems for you to think over Christmas. I just stole one slide that I just leave here if you want to discuss something about this list of open questions. But there are many more in the discussion session at string. Thank you very much. Sorry for going over time.
Okay, thanks, Joe. It was a very nice review talk. We had a lot of questions during the talk, and we are already 5 minutes over the schedule. So, Joao, are you going to be around for the discussion session, which is going to be from 5:45 IST to 6:15 IST? So that's 2 hours and 50, well, 2.5 hours from now.
Today I have this end of the semester is quite packed, but I can
try. So we are going to take some questions. So let's take some questions now. Then there's a raised hand. 𝗦𝗫𝗀𝗀𝗀 has a hand raised.
Yeah, so I was wondering how you get the extra terms, the rho is to something, rho is to something, rho is to something terms. Are you using effective field theory methods to compute the scattering amplitudes? How are you computing those terms?
I'm not computing them. So notice that the coefficients are free parameters. I'm just parameterizing my ignorance about this S matrix. Okay, so this is just an ansatz that satisfies the properties I listed here. It is Lorentz invariant, it is crossing symmetric, it's analytic, and it matches the low energy effective field theory. Okay, it's just an ansatz. You can choose another one. The good thing of this ansatz is that the free parameters enter linearly, and as I take this n to infinity, I can cover a very big space of S matrices. Okay. So.
And how do you get the betas?
So the betas are free parameters and they are obtained by the optimization. Then I ask a question. Within this space of S matrices, which of these S matrices has the lowest alpha? Okay, where alpha is computed. Okay, so alpha is a trivial computation, will be some specific linear combinations of the betas, beta ABC times some number, some known function of ABC that follows from Taylor expanding this around s equals 0. Okay, so I say minimize this thing within the space of betas subject to the unitarity constraints. And that's what fixes the betas.
And do you consider higher spin particles, or particles of all possible spins, or just scalars?
So the external particles, well, in the physical problem, they are the full supermultiplet, but in the end, it reduces to these charged scalars. So that's the only amplitude I consider.
Why does it reduce to the charged scalars?
There are lots of other hands raised. Can I just recommend that you can probably write to Joao in private and clarify this? Otherwise, others won't have a chance to clarify their doubt. Yeah. Is that okay, Shomdatta? I'm very sorry about this. We're already running over time. Sorry about this. Sorry to cut you short. So, Amin, you have your hand raised, please.
Yes, thank you. Yeah, thanks for your talk. Yeah, I'll try to keep it short. I had a basic question regarding the first part of your talk. So you had a slide where you mentioned the similarities between the CFT and the S-matrix 4-point function bootstrap. So maybe one thing which is quite different, perhaps, is that if you it's well known that because of the finite radius of convergence of the OP, once you impose crossing symmetry on every 4-point function, there is no additional constraint coming from crossing symmetry of higher point functions. So this, of course, would not be true when you consider general quantum field theories. So, so unlike the CFT case, this is perhaps also partly a comment, but I guess, is this true that, for example, if you do everything, you get all the constraints out of the Wilson coefficients from 4-point functions, once you go to 5 or 6-point amplitudes, you will just get additional additional constraints which are not there in any 4-point amplitude. Is that right?
Yeah, that's a very good comment. So this is another difficulty in the S-matrix bootstrap, is how to impose all constraints systematically. So the first step looks more or less the same, but as you say, in the conformal case, we can just add more 4-point functions. And in fact, to get the islands I was showing, people have done several 4-point functions. But in the S-matrix, well, you can put several 2-to-2 scattering amplitudes, but you will run out of that as soon as you do everything you can with the stable particles that you have at infinity, which are usually a finite set.
Mm-hmm.
So in the S-matrix, it seems that if you want to be systematic, you will have to study 2-to-3 scattering and 2-to-4 and all n-to-m scattering amplitudes. While in the conformal bootstrap, there is this systematic way that if you just look at more operators and look at 4-point functions of all operators, that's enough. I agree with you. It's a different, it's another qualitative difference between the two as bootstraps.
Okay, thank you.
Well, there is one speculation that actually in the strings conference, Shi-In was suggesting that maybe if we look at scattering amplitudes of resonances, then we will also have infinite number of them. But this is very speculative. I don't know if really it makes sense to define non-perturbatively scattering amplitudes of resonances, which are and then study that. But maybe that's one direction one could imagine.
Okay, so
Thanks.
I will allow for 2 quick questions. So Aalok, Aalok, please.
Yeah, thanks. Yeah, so just one small question, Joao. So as you were saying that we are interested in analyzing these amplitudes for positive S, and from low energy perspective, you are looking at like S close to 0. So you can do, as you were saying, maybe some wave packet analysis, even though the sum is strictly speaking not convergent at the boundary of the circle. Yeah. But if I wanted to use this ansatz to compute amplitude for physical S, some finite S, I mean, is there a, how would we go about doing it? I mean, we know this is not the right ansatz, maybe, right, for positive S away from S equal to 0. But is there some improved ansatz we could use? Or hello?
Yeah. I mean, this is a long discussion. I think.
Okay, sure.
Let's put it this way. Let's say this is just an ansatz. For any finite n, this is a good scattering amplitude, and you can look at it. Now, if the n equals infinity is really a good function, or there is some distribution with some complicated limit, I think this is unclear at the moment.
Thank you.
Okay, last quick questions from TIFR.
Hi, Joao. That was a beautiful, very simple, very clear talk. Thank you so much.
Thank you.
One quick question about the last part, the last slide. You suggested that you could do the same thing for the M theory example, where you had a unique number for alpha. So I was wondering whether you expected your considerations to zero in on that unique number, and if so, what would that mean? Would it mean that if you put all the constraints for all L, in general, there will be no solution unless you choose your n equals infinite. At any finite n, you will have no solution if you put all the constraints at every L, and then you would have to go all the way to infinite n to get a solution at all. Is that what it would mean?
Yeah, I mean, personally, I'm pessimistic. I think it will be very difficult to exclude the very large alpha, because large alpha is like weakly coupled. So I think if you just add, I feel that if you just add some particle, some light particle to the graviton, to supergrav, you will generate some very large alpha. It's hard for me to see how it can be excluded, but I guess you're asking how could it happen technically in terms of this extrapolation in large N and large L. I guess the simplest way to see it would be if you had a dual method, because in a dual method, one would approach the bound from the outside and would try to squeeze. So if there was upper and the lower bound for alpha, and then we'll kind of squeeze on the exact value of M theory. With a primal method, it's harder to imagine. I guess it would have to be a bit like you're saying, that if you put finite number of constraints, you would see some alpha allowed, and then as you increase number of constraints, this region that disappears, and then you have to study like how the region grows with n and decreases with L, and again do these limits carefully. But I mean, this is very speculative. Yeah, I don't have a clear picture in mind yet.
Okay, thank you.
Thank you.
Okay, let's thank Joao again for a very nice review talk. And we are, thanks to me and all the generous questions, we've already run over time by several minutes. So thank you very much, Joao. And the next speaker is going to be Enrico Pajer. Please share your screen. Enrico Pajer, please share your slides.
Yes, yeah, thank you. Yeah, no, I think I can do it. You cannot share screen. Okay.
Wait. I'm okay. Sorry, I think it was my fault.
Let's see.
So let me, Enrico, probably you are supposed to be, yeah, great.
Good. Okay. Yeah, it seems to work, right? Everyone can see.
Okay,
And
great, Enrico. So you have 30 minutes. I'll give you a warning at 25. Is that okay?
Absolutely, yeah.
Okay. So would you prefer to take questions at the end of your talk?
No, definitely during the talk. I can see that the participants need no encouragement to ask questions, and I've seen some really interesting discussion going on. But yes, nevertheless, please keep asking. It's going to be much more interesting for everyone if you interrupt me and ask questions.
And just to the audience, Enrico is not going to be around during discussion, so probably a good idea to ask your questions during the talk, or but we'll try to make sure that it doesn't go into a Lorentz dilated train, whatever. Anyway, so take it away, Enrico. So Enrico is going to tell us about the timeless history of time.
Thank you very much. Thanks a lot for the opportunity and for the invitation. Actually, I apologize for not being available at the discussion session, but it's so hard to get a COVID booster shot, and I managed to get an appointment, and I really cannot miss that. So things are getting a bit dire around here. And also, I wanted to apologize for not being at my talk yesterday. I would like to thank the organizers and the participants for putting together this very nice meeting. So the idea, what I wanted to talk about, is some recent progress, mostly in understanding quantum field theory in the sitter, and try to put it into the perspective that is perhaps more interesting to the participants of this meeting. So I'm going to start right away with some motivation and connection, and you can approach this topic from various points of view. From one point of view is coming from cosmology and the idea that we would like to understand the very early universe and inflations, because we get to measure those quantum correlators in cosmological surveys. And that is probably the way that I was approaching this. But there is another angle, which is perhaps more relevant to the Indian string meeting, which is understanding quantum field theory in perturbation theory in the sitter space. Is definitely a small corner in which we can understand how things work in the sitter, and maybe we can hope from that corner to try to understand much more challenging questions, such as the one that I'm trying to list below. For example, although the rest of the talk will be exclusively about quantum field theory and in perturbation theory in the sitter, my hope is that eventually this will connect to things such as the search for the sitter solution in string theory, and perhaps the way that this connection might happen one day, very, very optimistically, which is related to Joao's talk, is that if we understand correlators in the sitter as well as we do amplitudes, or perhaps better even, then we can eventually start to use those constraints to prove the UV regime of those correlators, and eventually we will see some constraints arising for potential UV completions of this theory. So there should be a connection to the quest of finding the Sitter solution in string theory. Another connection is to try to understand. We've heard some discussions about positivity bounds and in flat space, and these are really interesting ways that we have to cut out theories that do admit a consistent UV completion, since our universe eventually is an expanding one, and it looks like the metric is pretty close to the Sitter. We would like to know which theories are consistent in the Sitter rather than in Minkowski, and if the classes of theories that are consistent in the Sitter we already know is different from those that are consistent in Minkowski. So we would like to really know which one are consistent in our universe. And for that, we need to develop different type of positivity bounds. We cannot just rely on the flat space ones for applications to the whole of the universe. And eventually, I think that hopefully some of these results will one day give us some organizing principle or some constraints in thinking about a holographic approach to the Sitter. During this talk, I will not really make a lot of progress on any of these directions, but that's where the long-term applications of these results, I hope, will be. So let me kind of focus on the observable. Actually, a lot of the spirit is similar to the discussion that we have had with that Joao just presented, in which you start thinking about observable in the given system you've chosen and try to put constraints on those. So the word bootstrap could be used for this type of approach. So the system that I want to consider is the Sitter space. And in particular, for the rest of the talk, I'll focus on the Poincaré patch for various reasons. One is that is the one that is usually relevant for cosmology. And so if we want to bridge the gap to make some relevant statement about observations, this is the relevant one. So the Poincaré patch only covers half of the Sitter space. Let me see, yes. And so this is the infinite past, this green line, and I will always assume that in the infinite past, I choose some vacuum, which is called the Bunch-Davis vacuum, which corresponds to assuming that on short scales, the vacuum is the same as the vacuum in Minkowski. A more formal definition, but which is equivalent, is that this is the Euclidean Hartle-Hawking vacuum on the global de Sitter. And the name of the game is assuming a vacuum and assuming some theories, understanding what is the state at the end or towards in the asymptotic future of this phase of the Sitter expansion. So if we assume quantum mechanics, the universe is described by a wave function of the universe that I'll call psi. And what I will try to do is describe what is the wave function of the universe in the asymptotic future, which is this future conformal boundary that we have here of the Sitter. Okay, so in perturbation theory, I can always parameterize the most generic wave function that depends on any fields. These fields can be scalars, can be gravitons, can be gauge fields, you name it. I just call them phi for simplicity of notation, as an exponential of a sum over an ever-growing number of fields with coefficients. When I specify all of those coefficients, order by order, I have specified all the wave function in perturbation theory. So my whole talk will be about what do we know and what can we say about this wave function coefficient. And to some extent, if you want to have a flat space analogy, those wave function coefficient is like the amplitudes. Okay, as n grows, I'm looking at amplitudes with more and more external particles, and I would like to know how general principles constrain those objects. Strictly speaking, the wave function itself is not an observable, but from the wave function, I can compute observable with the usual quantum mechanics rules that expectation value of an operator is the integral over the wave function with the operator in the middle. And we have a generic prescription on how to compute the wave function in a generic system. We can always write it, as a path integral from some vacuum e to the I is weighted by the action of the theory to some final condition on the boundary. So if you give me a theory some Lagrangian S, I can compute this, at least in perturbation theory. Just to say a word, typically a lot of people thinking about de Sitter, but perhaps also anti-de Sitter, you might want to think about correlators. Correlators are closely related to this wave function. In fact, in perturbation theory, you can always go from 2-point correlators, 3-point correlators, etc., to the coefficients appearing in this wave function. Quadratic coefficient, cubic coefficient, quartic coefficient, and so on. For this talk, and I will use the language of the wave function coefficient, but everything can be rephrased in terms of correlators. So just like in flat space, when we compute amplitudes, we have some straightforward rules in perturbation theory to compute any wave function coefficient to any order. And the rules are pretty similar to Feynman diagrams or Feynman-Witten diagrams, because they were similarly developed by Witten for the ADS, for the equivalent ADS problem. And the idea is that you write a generic diagram, you see the legs that make it to the asymptotic future boundary are the external fields. For each one of those, you put a propagator that goes from the bulk to the boundary. And for every internal line, you put a bulk-to-bulk propagator, which I call G. And for every vertex, you have to integrate over the whole of space-time and put whatever interaction happens there. Here already you see kind of one of the first characteristics of what happens in de Sitter, which when we compute amplitude, this is just, okay, so at loop order, we are used to the idea that we have loops, but that we have loop integrals. But here we will find a bunch of integrals already at tree level. And the reason is that in de Sitter, we don't have a globally defined time-like killing vector, so there is no time translations. And so these time integrals are not done automatically for us by energy conservation. We will have to keep them around. And that's what complicates a lot of the analysis, even in perturbation theory. So even at tree level, things are much more complicated than they are in flat space. So the idea is going to be to say as much as we can about these objects, but without computing them directly in a specific theory. So again, using general principles such as symmetries, unitarity, and locality to constrain these objects. And so let me start with symmetries. And so that the motivation here is that this eventually is going to have some application to our universe, and therefore it is reasonable to work our way up in terms of adding symmetries from what we actually observe in our universe. We observe our universe to be homogeneous and isotropic. So that means the isometries of three-dimensional Euclidean space. So 3 translations and 3 rotations. But we also observe the primordial perturbation to be scale invariance. And that's the strongest motivation that we have to think that there was some kind of phase of de Sitter-like expansion in the early universe. So it is reasonable to assume translations, rotations, and scale invariance, which is implemented by some dilation operator. But the question is whether we should assume something more. So if we were in exact de Sitter, then there would be additional symmetries given by the de Sitter boost, which is just the de Sitter generalization of Lorentz boost in Minkowski. Assuming the symmetries is extremely powerful and extremely constraining, and in fact we know that well from the study of conformal field theory, the symmetries on the future boundary of de Sitter become special conformal transformations, and then we can use the extremely powerful machinery of conformal field theory to say things about observable. And this has been beautifully developed over the years, going all the way back to Maldacena, Pimentel, Al-Kani-Ahmed, and most recently Bauman and Joyce have done a lot of work in this direction. However, we are pretty much, for reasons that I will explain, you could also decide not to assume any invariance under the Sitter boost or special conformal transformation. And there are a few reasons to do that. One is that we have never observed those symmetries in our universe. We have no reason to believe that they are actually applied. And the second reason is that they might be too constraining, and they might pretty much rule out all models that we are actually interested in. The reason is that even though our universe is approximated by de Sitter, it cannot be exactly de Sitter, because otherwise it wouldn't have a history. De Sitter is maximally symmetric, so every point is equal to every other. And the breaking of these de Sitter isometries can be arbitrarily large in terms of boosts. So I would never assume anything about de Sitter boost, but derive more general results. If you want, you can specify to the de Sitter limit and conformal field theory limit on the boundary, but most of the results will not rely on that assumption.
Enrico?
Yes.
I have a small question about your previous slide. When you draw the diagrams. Yeah, so here, let's say I'm working in some flat space approximation near one of these vertices. I guess I'm not requiring momentum conservation even in this flat space patch. So how should I think about this diagram? These are not to be thought of as some on-shell S-matrices or anything like that, right? So what are they exactly?
Yeah, so here there will be spatial momentum conservation at every vertex. Sorry, I have a lot of feedback. There will be spatial momentum conservation at every vertex. And in fact, as I said before, that every vertex should be integrated over the whole of space-time, but the integral in space, it's automatically done by spatial momentum conservation, but the integral in space. But the one in time cannot be captured by conservation of energy. I will show you that in the limit in which all of these interactions happens in the infinite past, you can think of energy as being approximately conserved because the expansion of the universe is very slow with respect to the physical process. And in that limit, this will become a scattering amplitude times a factor that I will write down. So you should think of this as being literally a scattering amplitude in flat space, but with additional insertion of energy at every vertex. So you can go to a limit where you take away that insertion of energy and it's just an amplitude in flat space. But what actually de Sitter does is that every time particles interact, they could also get some energy from the de Sitter background. And so that amplitude gets corrections that do not conserve energy.
Okay, thank
you. And I'll write down an explicit formula to prove that this equation in a certain limit is just a flat space amplitude.
Hi, Enrico. This
Yes.
is Sandeep here. You must go on, but I find it a little strange that you're not using any of the special conformal symmetries. And the reason I say this is when we did some of the work on imposing the consequences of symmetries, what we had shown was that even when you include the breaking of the de Sitter symmetries due to slow roll and so on, the breaking vis-a-vis the special conformal transformations is no more or less important than the scale invariance. And in fact, the special conformal transformations buy you a great deal, as you know, in the work we've done. So I'm a little surprised that you choose not to use those symmetries at all.
Yes, yeah, excellent question. In fact, I was about to say that you, Sandeep, and Subrat Raju had some very nice paper around 2012, 2014. And I think at the time, I just was not aware about these techniques that came from ADS-CFT. It took me 7 years to understand them. And now I'm slowly catching up. And I can see kind of the useful new ideas that you brought into the field. And I can tell you what are my thoughts, that if you study the simplest theories, for example, pure gravity or a canonical scalar field, then it's true that there is a single parameter that controls both the breaking of dilations and the breaking of boost or special conformal transformation. They are just fixed by the same parameters because the theory is particularly simple. Mm-hmm. More generally, in more general theories, for example, theories like P of X theories that have a general function of the kinetic term, very simple single derivative per field. In those theories, these two breakings are two completely different parameters. The breaking of dilations is given by slow roll parameters, deviation from the de Sitter expansion, while the breaking of boost or special conformal transformation is given, for example, by the speed of sound of perturbation, which can be arbitrarily different from one. So in those limits, special conformal transformation are just not a good approximation. And in fact, we know that all the models that actually predict some correlation, which is what we're trying to compute here, they precisely badly break boost while they approximately respect dilations.
Yeah.
There is some deeper reason why this is possible, which has to do with some kind of Coleman-Mandula theorem for CFTs, but maybe I'll mention that later. But I think that's the motivation. And in the theories that you were studying, indeed, the breaking was controlled because it was pure gravity or conformal canonical capo-scalar, but in more general theories, those two breakings are different.
Yeah. But nevertheless, and you must go on, of course, you know, it's worth studying the case where the conformal breaking effects are of the order of the scale invariance, because even though you're right, observationally, you can enhance the signals in the other case, like you mentioned. It's an in the long run, it becomes an observational question, because if you can measure the perturbations to the required accuracy, nature will decide, you know, which of the two scenarios is right. So it's worth keeping both in mind and not discarding the ones.
Yes, absolutely. Yeah, I don't think the other, exactly. Keeping those symmetries should definitely be high on our minds, because it's such a powerful constraint, as you have shown as well. And I'll maybe try to frame this discussion in a more concrete form in this following slide. So last year we proved the set of theorems, and perhaps the most important one for this discussion is theorem 2. We proved that if the only thing you care about are curvature perturbations coming from a de Sitter phase, and you are in single field, and you assume full de Sitter symmetries, then all the correlators are the correlators of a free theory, meaning all connected correlators are zero. So this tells me that, as somehow related to what you just said, that to get some non-trivial correlators, you need to break those symmetries a little bit. And the size of those correlators is related to the breaking of those symmetries. And so for the conceivable future, because of the finite resolution of experiments, we will only see that breaking if that breaking is large and much larger than slow roll. And which is why I'm interested for the phenomenological reason to break it by a large amount. Okay. So I think this kind of theorem that makes it very precise. If you keep those symmetries, then at most you will be slow roll suppressed. If you don't, you can be much larger. But you're right that that's an extremely interesting limit. And in fact, pure gravity should probably be the first theory that we understand. And that theory does obey the scaling that you described. Thank you. Thank you. Sorry for the interruption. Yeah, no, that's an excellent point. So I don't want to be critical about using those symmetries. It's just we were able to derive some results that do not rely on that. So why not? And so because of this theorem, most of the results, especially about unitarity that I'll discuss later on, will not assume this. So we'll be valid in any FLRW universe. So let me quickly discuss some notion of locality. So there should be some notion of what does it mean that in the bulk of the Sitter, interactions happen local. And similar questions can be asked on the ADS side, and they have some nice interpretation in terms of boundary observables. This interpretation is still, to a large extent, unclear in the Sitter, what it means to have a local interactions in the bulk. But one constraint that we were recently able to derive in a specific, under specific assumption is the following. So imagine that you only have scalar or spin 2 particles, such as an inflaton or a graviton, and pure gravity would be a case. And that's assume that the theory only includes interactions of fields at the same space-time points and their derivatives, but not interactions that involve inverse Laplacians, for example. Then under these two assumptions, the boundary wave function coefficient, which, as I argue, are related to observable, need to obey this very simple relation, which means that they cannot have linear term when expanded in any of the norm of the external vectors. So if this k are the momenta of the external particles, they have some norm, which I call k without the boldface. And when you Taylor expand in this k external, the linear term the d in decay at k equals 0 has to vanish. If it doesn't, the theory is not local in this sense. So this is very useful, and this does apply, for example, to pure gravity, and in fact, in any even number of space-time dimensions. So it's a very useful constraint. If you write something, you can automatically eliminate a lot of terms that don't obey this because they couldn't possibly come up. And in real space, this is really has to do with how fast spatial correlations are allowed to grow. Although here we write down the constraint in Fourier space.
Sorry, can I ask one question?
Yes.
Is there this locality principle that you showed that can be translated to the correlation functions also, right? And is there a like CFT understanding, pure CFT understanding of this condition?
Yeah, I would love to have it, and I spend a little bit of time in understanding it, but I still need to learn so much more than what I actually know. My understanding is that if you write this in terms, if you interpret this as a CFT correlators on the boundary, and you Fourier transform it to real space, you would imagine that the locality has to do with cluster decomposition on how quickly this correlator factorizes into the product of two correlators. And how quickly that can happen is dictated by the 2-point function. And so this constraint ensures that a correlator of a bunch of operators, as you physically separate them in real space, becomes the product plus corrections, and those corrections need to go to 0 at least as fast as the 2-point function. So this is the interpretation of this bound if you were to Fourier transform it. But I would love to understand this better and have a clearer picture. The main obstacle here is that a lot of concepts of locality and analysis in CFTs are done in real space, while all of this understanding that we have in the bulk is Fourier space and is a pain to go back and forth unless you have full conformal symmetry that fixes the answer.
Okay.
And I'd love to discuss with you and both about this and about CFT, parity odd CFT correlator. Thanks for the question. That's a very good question. Very good. I should stress that this constraints comes from manifest locality. So if you have cases in which you have inverse Laplacians, then it doesn't apply. The theory might still be local. So this is a sufficient condition to be local, but it's not necessary. It could be that secretly you can get rid of these inverse Laplacians by rewriting the theory with some constraint fields that have local interactions. So this is a necessary but not sufficient condition for locality. Okay, that's just the best we could do so far. There was a question earlier on, and this goes back to a paper by Raju and Maldacena Pimentel some 10 years ago, and then more recent progress, precisely how you can interpret this wave function coefficient. And in the limit in which you take the norm of all external fields, the sum of their norms to 0, we call that the total, well, they call it the total energy. So you go, there is always a pole of this wave function coefficient. They have a pole in KT, and the residue of that pole is the amplitude. And there is a very precise formula that can be written that we worked out last year with coefficients and all that says that there is a pole, which is 1 over KT. There are some overall factors that come from normalization, some numerical normalization in front. And here, eventually you find if this is a correlator, the real part of the amplitude, and if this is a wave function coefficient, just the full amplitude itself. So this is the connection to flat space physics, which has to do with the fact that in the infinite past, the perturbations were much shorter and so effectively lived in Minkowski space. And from this, the order of the pole is also an extremely simple formula, which is 1 plus the sum over all vertices involved of their mass dimension minus 4. So this tells you how severe this divergence will be. And an expansion in 1 over KT to some power is the equivalent of an effective field theory expansions of this object. The more derivative you have, higher dimension operators, the more severe this pole becomes. And that's how you probe the UV completion of the theory until the EFT breaks down.
You have 5 minutes.
Yeah, great. I haven't even talked about unitarity. So unitarity, you guys know better than me, U dagger equals 1 is the conservation of probability. what would be very interesting to know is how unitary time evolution in the bulk of the sitter is encoded on the spatial boundary. And this is more complicated than you would think, because time completely disappears in the boundary description. So it's not clear what unitary time evolution means, since there is no time evolution in the boundary. And also notice that time evolution is not a symmetry. So just having a unitary representation of the symmetries of the problem is a priori not sufficient to ensure that time evolution, which is not a symmetry, is unitary encoded. But we made some progress in perturbation theory to find the consequences of unitary time evolution in the bulk. And we came up with this basic idea. And what it does, it constrains the analytic structure of wave function coefficient. If you write wave function coefficient as a function of the external momenta, their vectors and their norms, and you separate out the norm from the direction of the vector, when you analytically continue the norms to minus themselves in the lower complex half plane and do a star, this thing is completely fixed by unitarity. For contact diagrams like this particular combination has to vanish. So we give it a name, we call it the discontinuity of psi down here. So for simple contact diagram, this discontinuity has to vanish. For more general diagrams that are not just contact, they have various interactions, the discontinuity is always fixed in terms of the discontinuities of simpler diagrams where you have cut internal lines. So the discontinuity of a 4-point function is fixed by the discontinuity of 2 3-point functions. And what we proved earlier this year was that this is valid to all ordering perturbation theory for particles of any mass, any spin, and arbitrary local interactions, as long as you assume a Bunch-Davies vacuum. That's the crucial assumption. So this is valid to any number of loops. It's valid for gravity, etc. And the general rule is that you have to sum the discontinuity of a graph is equal to the discontinuity of the sum of all possible cuts of internal lines. Single cut, double cut, triple cut, and so on. So this is the sitter equivalent of cosmological cutting rules. And it should be a constraint, and is a powerful constraint on the boundary observable. So you can predict many properties of the result just from this. For example, we show this how using this you can almost completely fix one loop corrections to the 2-point functions, which then leads to one loop correction to the power spectrum. And we recover some previously computed coefficient, but we extended it to other general theories. I don't have the time to describe this result, but the statement is that when you understand unitarity, you can constrain loops from 3-level objects because their cuts are fixed.
Sorry, I have a quick question. I know you're running out of time. Is there a general Hilbert space kind of proof of this, or is this just a perturbative argument by looking at the structure of perturbation theory? I mean, could you just indicate how the argument follows?
Yes, I would. It's a structure of perturbation theory, so it's fully perturbative. My main goal is try to understand how this can have a deeper meaning in terms of the Hilbert space, but I'm struggling to understand precisely what is the equivalent of time translations on the boundary where time translations disappear. They are not linear combination of the CFT generators because those are symmetries and this is not a symmetry. So that's something that I would like to understand better. I can tell you later how we are trying to understand it, but at the moment it's just a statement order by order in perturbation theory, and the way it works is to notice that bulk to boundary propagator obey a simple equation which says k star is equal k of minus k, some really simple thing, that in ADS it's almost there, that property, but because in ADS the radial direction is real, you cannot take a star to change its value. While in the sitter that becomes I tau, where tau is conformal time. So with a star you can put a minus, and that minus is compensated by a minus in the analytic continuation of energy. That's the trick. And this simple property about the bulk to boundary extends to the bulk to bulk propagator. And when you have that property, you can see how that bulk to bulk propagator gives you delta function when you apply this discontinuity, which eventually cuts it down. So I can maybe write an equation which would be simpler.
Yeah, no, just one more thing. I mean, the details I can try and see. But so you said it applies to the Bunch-Davies vacuum. But if there is some result that applies to all correlators, you can always act on the left and the right with the right operator and change the vacuum, right? So I'm confused about why some very general result would apply only to a specific vacuum.
I mean, as long as you have, if you go perturbative away from the Bunch-Davies vacuum, I think it's okay. If you have like a single A dagger perturbations, but if you go to an alpha vacuum, general, which is the non-perturbatively related, then it will not obey. And in fact, you can compute even the 2-point function from alpha vacua for particles of general mass. And if the mass is not 0 or conformally coupled, this thing will fail. So when you go too far away from that vacuum non-perturbatively, then it breaks down.
Okay, thank you.
Excellent question. So the main trick is just when you have this equation, then everything else follows. In perturbation theory.
Enrico, can you wind up in maybe a couple of minutes?
Yes. So I wanted to show you how these bootstrap rules we can already start using them to learn about 3-level things. And hopefully in the future, one will be able to learn about more complicated objects. And here I just wanted to show you that the structure of the simplest interacting object, which is the cubic wave function, is completely fixed. For massless scalars in the sitter, this has to be a rational function. All the poles are fixed by this choice of the Bunch-Davies vacuum. Then the numerator is a polynomial whose order is fixed by scale invariance and whose variables are fixed by Bose symmetry. And then solving the problem is just a simple algebraic question of what polynomials are allowed. And because of locality, we know that the derivative of this has to vanish. So you write down the most generic polynomial with free coefficients and all possible variables to all possible orders. And then you demand that it is manifestly local. And that fixes all of these coefficients. And by this very simple, a high school student could do this calculation, you find exactly all the results that we know and love in the literature, but infinitely many more. For example, the 0th order solution of this gives you exactly local non-Gaussianity, as well as the non-Gaussianity that comes from phi cube interactions, which has a log. If you solve this to the next non-trivial order, where there is a KT pole, then you find equilateral non-Gaussianity from the effective field theory of inflation and orthogonal non-Gaussianity from the next order in the effective field theory of inflation. But of course, you can go to all infinite orders in derivatives, and we have written down a closed form expression for this. So the calculation is much simpler. You don't have to do integrals. You don't have to write a Lagrangian. These are just the most generic 3-point wave functions that are compatible with locality and unitarity. Most recently, we showed how this very interestingly applies to non-Gaussianities of graviton too. And there was a surprise, well, for me at least, it was a big surprise. So in principle, as Joao discussed, if you want to constrain higher derivative corrections to gravity, you write a Lagrangian, you can write down infinitely many terms with more and more Riemanns contracted with more and more ways. And for the simplicity of this argument, let me only consider parity odd things that are contracted using precisely one epsilon tensor. So you would imagine that there are infinitely many of these terms, and therefore infinitely many 3-point functions of gravitons that break parity with more and more derivatives. Instead, we proved that if you, instead of the wave function, you only look at the correlator, which is the physical observable, there are only 3 possible shapes that are consistent with unitarities. All others must be non-unitary. So infinitely many terms in the Lagrangian actually give you only 3 shapes of graviton 3-point functions, to all orders in derivatives at 3 levels. This is an extremely powerful example, and it explains why for the past 5 years, people in the literature kept computing things with higher derivatives like Chern-Simons and kept finding 0 or one of these 3 shapes. And I wish I had the time to show you the proof, but I'm already out of time. But the proof is simple. You write down everything that is allowed by the symmetry, and all of pretty much everything violates unitarity as given by this optical theorem. You just apply it and you say that these don't violate the optical theorem, except for things that have no poles, and those are just simple cubic order polynomial, and there are only 3 of them. It would be great to connect this to some recent study by by Sachin Jain and other people about parity breaking tensor correlators on the CFT side. This is very general and extremely powerful and can be extended also to mixed correlator with scalars and tensor, but I'll skip that. Finally, kind of closing my seminar, sorry that I went long, but I did have many questions. I wanted to mention that this can be done also for general diagrams that have any kind of exchange, and you can develop a similar strategy to the recursion relation in flat space. And in this context, they are called partial energy recursion relations. Basically, you notice that the singularity of a most general three-level diagram are completely fixed by unitarity. The singularities can only be in partial energies, which are the energies that goes out of a sub-diagram. And all of those residues are fixed by unitarity. And once you have all the residues and all the singularities, almost the whole function is fixed up to boundary contributions. And so this really becomes a calculational tools that go to all orders in perturbation theory. Okay, I'll come to a summary. Sorry for going over time. So in the last few years, we have seen a lot of progress building up on really, seminal papers, some of which by Suvrat and Sandeep 10 years ago. But we have seen how those calculations present some general features and general properties, such as unitarity and locality. And once you have those, that's kind of your gateway to start applying a more of a bootstrap approach, like the one that Joao described in the previous talk. And it's nice to see how fundamental principles are encoded, and we can hope to do much better in the future. So my dream here would be to have really the sitter positivity bounds. We already know that the consistent theory in the sitter are not the same as in Minkowski. In Minkowski, you can have supergravity. In the sitter, it has to be broken. So it's not clear that you can have a consistent theory of self-interacting spin 3/2, massless spin 3/2 in the sitter. So there should be different rules. What are those rules? Hopefully they come out from something like that. You could try to do something more non-perturbative, but I think it's still early days, or you could do something more numeric, and Joao had a nice paper earlier this year about this. So I'll stop here and leave some time for questions. Thank you very much.
Thank you very much, Enrico, for a very interesting talk. Before we go to questions, I have been told to make an announcement that the next session is going to start at 4:30 p.m. So since we can have questions till then, let's continue discussing till then. If anybody wants to hang around. So 𝗦𝗫𝗀𝗀, your hand is raised.
Yeah, so you had that operator del Kc in front of the wave functions, which was being disputed a little earlier. So I was just wondering if you have, when you go to the position space basis, in general, you would have the 𝑒⁴ dot x minus x prime sort of thing along with the psi k's, right?
I'm sorry, so are we talking about now the locality thing or the?
Yeah, the locality thing, yeah, this one.
Okay.
So if you go to the position space basis,
yes,
then I would guess that in general you would have some Fourier coefficient like 𝑒⁴ dot x in along with the psi n's, right?
Yes.
In general.
Yeah.
So if you now if you can now do an integration by parts to convert the del Kc to act on the 𝑒⁴ dot x minus x prime to bring down the x minus x prime. So in the position space basis, the analogous thing would be some x minus x prime times the position space wave function equal to 0, right? Is that correct?
Yeah, somehow is the general rule that the Taylor expansion of a function around the origin tells you about how the Fourier transform goes to 0 at spatial infinity. So the fact that this is analytic and has vanished first derivative at k equals 0 means that the Fourier transform as a function of r, the distance, has to go to 0 appropriately fast, and appropriately for the massless function we're considering here means faster than 1 over distance to the 6th power, for example. So that's correct. So what you're saying is, so I'm saying that dk of psi of k equals 0, it implies that when you Fourier transform it, it gives you a power of x for any pair of fields, any pair of points in Fourier space that are separated, and this has to go like 1 over distance to the 6th power. 6 comes because I'm considering fields with dimension 3, so 2 times 3 is 6. But this hopefully can be extended to fields of different dimensions, but for massless fields, their corresponding conformal dimension is 3, so they have to go to 0 like r to the 6. So that's precisely what this condition implies. And you can do some Fourier transform as you're suggesting.
TFR.
Yeah, okay.
TFR, please unmute, yeah.
Hi. Thanks for the great talk. I had a quick question about your unitarity relation. If we were working in global de Sitter space rather than on the Poincaré patch, you could turn on sort of fluctuations both in the infinite past as well as the infinite future. And then, so you could send stuff from the infinite past into the infinite future. So that object would be very much like a genuine S-matrix. You prepare stuff in the past and you measure it in the future. And presumably that object would obey some version of S dagger S is equal to 0. I was wondering what the connection between the unitarity of that object and the unitarity that you're finding is.
Yeah, I mean, excellent question. I think it would be the same unitarity. And perhaps it's our fault why we didn't do it that way. We could have tried. So we have 2 derivations of this relation. The first one really starts from UU dagger in interaction picture perturbation theory, and we just follow that UU dagger. The main difficult, so that would be very similar to what you're saying, is that I should take global coordinates and evolve in the whole of the sitter. The main difficulty is that when you try to play the same game that you play for amplitude, you get a term which is, delta U plus delta U dagger is equal some kind of delta U dagger thing. And here you insert a resolution of the identity schematically. For amplitude, this delta U dagger thing, you just interpret it as an amplitude where initial and final particles are reversed. But for this case, we didn't have that interpretation for the Poincaré patch. And so that's where that analytic continuation came in. And that was a trick to rewrite this term. But perhaps if we were to do it for the global de Sitter, then this would have a more natural interpretation. That's an excellent suggestion.
Thank you.
Deepan.
Yes, sir. Am I audible?
Yes.
How does the de Sitter background affect the page curve, and also the de Sitter unitarity, and also the de Sitter unitarity? How does it affect the page curve and the black hole information problem?
Yeah, good question. I have been trying to myself to learn. I had a dream that if we understand the unitarity constraint beyond perturbation theory, maybe as a boundary CFT segment, that might tell us when perturbation theory violates this bound. We do expect that the finite entropy of the Sitter space, or rather of the Sitter static patch, is in contradiction with perturbation theory, because in perturbation theory you have infinitely many degrees of freedom. And so at some point perturbation theory is making a mistake, and there should be a correlation among all of the possible gravitons and scalar fields that you find in perturbative quantization. So my hope is that maybe translating some of these bounds to the static patch, you would see that at some point these unitarity bounds are violated. And like for the page curve, that would tell you here you should have some non-perturbative effect. At the moment, this is more aspirational than practical, but that's an excellent direction in which to try to think.
Okay, Sandeep.
Thank you.
Yeah. Hi, Enrico. Thanks for a really beautiful talk, and the results are really impressive. I just wanted to understand, didn't understand some of the things you said. if you just go to the bispectrum again in your slides, did I understand right that just imposing your notion of locality and unitarity, I meant the bispectrum, you can at most have only, say, these 3 or 4 functions which are allowed? Is that
No, sorry.
No,
they don't pull orders, so I haven't written them, but this was just the solution. So this is the equation that I'm solving, and I have to tell you what is the power, how many derivatives I'm working with, which is the number of derivatives in the EFT expansion tells me how severe this total energy pole is. So larger P means a bigger polynomial here.
Yeah, I see.
Capture for more derivatives, and then I have more and more solutions. And these are the solution in the next page for P equals 0, 1, 2, and 3. But then you can solve for P equals 4, 5, 6. And we have presented the solution to all orders. And those precisely match the infinitely many bispectra that you get if you were to do the calculation explicitly.
I see.
This is true for scalar. For graviton parity odd, there is the very surprising feature that correlators, actually, there are only 3. But that's a different one. For scalar, there are infinite.
They're infinite, I see. And in the scalar case, if you organize them in terms of the breaking of scale invariance, is there a sense in which at leading order, in a model independent way, there are only a few functions which can appear? Or these
are all exactly scale invariant, all of these.
These are all, so there's an infinite number, I guess, huh?
Yes, exactly.
I see. So a lot
these are all exactly scale invariant, but only 2 of them are spatial conformal invariant, while all the others are not. In fact, only something like this is spatial conformal invariant.
I see, but then so maybe I'm a little confused. I mean, in the standard slow roll inflation, the bispectrum originates due to the breaking of, in a sense, scale invariance, right? There's one factor of phi dot that suppresses the magnitude of the non-Gaussianity, as you said.
No, well, not really. In the sense, it is true that there is a phi dot, but there is also a 1 over CS squared in a equilateral or orthogonal. And because of that combination, you can make it as large as you want. So there are two non-Gaussianity. The local one, and I agree, that's always in single field, always suppressed by order epsilon or beta, which are slow roll.
True.
And the equilateral non-Gaussianity, because that is the factor of 1 over the speed of sound, even if you respect dilations, but you break a lot boost because you have
that's true.
A sound cone that is very different from the light cone.
Yeah.
Because you make CS much smaller than C. Then non-Gaussianity becomes huge, even in the limit in which dilations are unbroken. And that's what I was trying to say, that there's really 2 different order parameters. Yeah. It has to do with the fact that, well, if you have boundary non-unitary CFTs, you actually can have scale without conformal invariant. The 2 things are not bound together, which is probably related to the fact that the boundary theory doesn't have to be unitary in the Lorentzian sense.
Yeah, I see. So you say that these all preserve scale invariance.
Exactly scale invariant, yeah.
Exact scale invariance, I see. Okay.
Nevertheless, boost by an arbitrary amount, which is kind of why I think it's so interesting that there is a lot that is scale invariant, but not boost invariant. Right. And that's probably what we most likely will be able to see in the next 50 years. Maybe 100 years from now, we also see the smaller one, which is low roll suppressed.
Yeah. Thank you.
I mean,
Yeah, thank you for your talk. So I had a question about, you had a slide on Feynman diagrams where you mentioned the point that in de Sitter, even for tree-level diagrams, you have to compute these conformal time integrals because there's no conservation of energy. So I was just wondering, is it possible that there is some representation of correlation functions, which won't be the position or the momentum space representation, of course, in which one can just get the tree-level de Sitter correlator to be just a product of the propagators and vertex factors. So the reason I'm asking is that, for example, in ADS, we know that one can, again, at tree level, write the correlator in Mellin space. There are Feynman rules at tree level, and some things have been done at loop level also. And of course, in flat space QFT, we do this in momentum space. So is it a reasonable expectation or not that there is some representation that in which you have something similar for de Sitter? That will help also, perhaps, if there is such a thing for doing loop calculations. If de Sitter tree level correlators can be. I see.
Yeah, it's an excellent question. So there are Massimo Taronna and Charlotte Slade have developed this this approach to translate the Mellin space representation in ADS to de Sitter. And indeed, there things get more algebraic, exactly as you are suggesting. The main complication there is that there are some phases that you have to work out, which has to do with the fact that the notion of unitarity in de Sitter is different from the Lorentzian unitarity in ADS. But you're exactly right that for things that are fully de Sitter invariant, Mellin space is the way to go. And there things simplify a lot. As we were discussing before with Sandeep, there are things that if you really insist that everything is de Sitter invariant, there is nothing you can measure of the correlators we care about. You can measure some scalar fields, but the curvature perturbations cannot have non-trivial correlators because of the theorem I wrote before. So here I want to consider interactions, these Fs, that are actually violate de Sitter isometries. And then for those, this Mellin space representation cannot be used, meaning it would get extremely complicated. Just like Fourier space for something that doesn't preserve translations. And so for this, I had to do something else. Recently, we showed that this problem of having integrals can actually be resolved because there is a complete solution in Minkowski. For the wave function in Minkowski, all of these integrals can be done. And then we showed that you can uplift it from Minkowski using derivative operators. So we propose a differential representation recently, which is valid also for things that break de Sitter isometries and so cannot be represented in Mellin space. So I think you can choose. If you want to have de Sitter isometries, you stay here on the left and go for Mellin space. If you want to break this special conformal transformation, then you can use what we recently proposed. So I would say that that's how I would think about it.
Okay, thank you.
Okay, last question, Sachin.
This is related to what Siraj was asking. So if I take the, let's say, flat space limit, the unitarity, notion of unitarity that you have, that will reduce to the flat space amplitude unitarity, right?
Excellent, exactly. That's how we originally derived it. We knew that there was an optical theorem on the residue of that pole because that's the amplitude. And then we said, how come that the wave function knows about this optical theorem, and we were able to extend it away from that pole to the full wave functions. That's exactly as you said. Yeah.
I see. And can you go to the parity, or you said you got three solutions, right?
For the correlator, yes.
I'm just curious that, you know, from CFT perspective, maybe one can derive it, but even before that, there is always a one-to-one correspondence with this correlated to the flat space amplitudes, right? So from the flat space amplitude perspective, would you been able to get to the same conclusion that there would be just three possibilities?
Exactly. Yeah, precisely. Excellent question. Yeah, that's an excellent question. So clearly, the main theme here is that correlators are some real things, while wave functions and amplitudes are some complex things. So the relation is that the correlator is the real part of the amplitude, schematically, because of that equation that I wrote before. There is some factor of I. And so if you were to compute the flat space amplitude for this parity odd graviton 3-point function, you will see that they all have precisely the right number of I, that only 3 of them survive, and all those with higher and higher dimension, they have the wrong I's, and they will be purely imaginary, and therefore they will not contribute to the correlator. Yes, so you can do the way you are suggesting. And there it would be just a matter of counting I's. And you will see that the I's, for all but 3 of them, the I's in this formula will give you 0.
Nice. Okay. Okay. Thank you.
Okay, so let's thank Enrico again, and also Joao for a very productive session. So the next session is going to start now. I'll hand it over to Aalok Misra.
Thank you, Aninda. Thanks. Thank you. So is Shibaji there?
Yeah, I am here. Can you hear me?
Yes.
Okay.
So yeah, please take over. I mean, we start right away. Thank you.
Okay. Okay. So welcome to the last session of this of talks of this conference. So in this session, there will be 3 talks of 30 minutes duration each. So the first talk is by Ronak Soni from Cambridge University. And the title of his talk is From Bekenstein-Hawking to Gibbons-Hawking via Hawking page.
Thank you.
Okay, so I will remind you, Ronak, around 25 minutes.
Thanks a lot.
Okay.
Yeah, thanks a lot. Thank you, Shibaji, and thanks to the organizers for this wonderful conference and for inviting me. So I will talk about this paper I wrote with this set of people, and it is. So let's start with what the talk is about. Okay. Yeah. So this talk is really about the entropy of de Sitter space. So in ADS-CFT, the Bekenstein-Hawking entropy of a black hole has an obvious interpretation. It is a number of CFT microstates in the dual CFT. Okay. But the corresponding entropy of de Sitter, which is the Gibbons-Hawking entropy of the cosmic horizon, does not have such an interpretation. And this is the problem we will tackle. So to set the stage, I have drawn some pictures of the eternal black hole in ADS and de Sitter to remind you of what's similar and what's different. So the first picture is the Penrose diagram of the eternal black hole. As you can see, as you go outward in a space-like direction, the radius of the internal circle diverges, and as you go be inside the horizon, you hit a singularity where the radius goes to 0. Okay, de Sitter has the same Penrose diagram. Okay, but in the exterior, the radius of the circle goes to 0, and in the interior, it diverges. Okay, so it really looks like the same Penrose diagram flipped 90 degrees, and both of them have horizons, but these horizons are very different in some ways. So to see the difference, we'll look at a Cauchy slice of these two diagrams. In the black hole case, the Cauchy slice looks like a throat, and the horizon is the neck of this throat. Okay, and in de Sitter, the Cauchy slice looks like a sphere. Okay, and the horizon is the bulge of the sphere. This is called the cosmic horizon, and we will also call the corresponding opposing points the poles. If the cosmic horizon is the equator, these are the north and south poles. So this cosmic horizon is the guy whose entropy we will be talking about. And the main result of this talk is that at leading order in small g Newton, strictly leading order, we will give a South state counting interpretation for the Gibbons-Hawking entropy in 3D de Sitter space. The way we will do this is by relating the black hole and cosmic horizons using the TT bar plus lambda 2 deformation. Okay, so let's more of an introduction to the Gibbons-Hawking entropy. So taking a de Sitter 3 with de Sitter scale L, the cosmic horizon has a Gibbons-Hawking entropy, which is area by 4g Newton. Surprise, surprise. The area, because de Sitter, we are in de Sitter 3, the area is the area of a circle, and so it's just 2 pi into little l, where little l is a de Sitter radius. Okay. Now this is a very old observation dating back, I believe, to the 80s.
The new thing that was added in 2018 was that this value has a very interesting connection to CFT. So assume that there's a number C, which is 3L over 2G Newton. This formula 3L over 2G Newton is the Brown-Hanover formula for the central charge of a CFT dual to ADS, but De Sitter, of course, does not have a dual CFT, so here C is just some formal number. It turns out that the Gibbons-Hawking entropy is the number of states in the CFT at a given level, at a given conformal dimension, without spin. Okay, and the formula that counts the number of states in the CFT is called the Cardy entropy, and without spin it looks like this. And if you put delta equals C over 6 and plug in this value, you get this value. Okay, and yeah, so and the delta is not just any level; it is known as the Hawking page level. It is dual to the smallest BTZ black hole that is canonically stable. Canonically stable means that this black hole is a dominant saddle in the canonical ensemble. Okay, so it's a very special level in ADS. It's not just any level. And today we will argue that this is more than a coincidence. Okay, so one of the main ingredients we will use is what's called modular S invariance. So consider a QFT partition function on a torus with no spin. With the whose spatial cycle has length 2 pi r and whose time cycle has length beta. But notice that when I say this is spatial and this is time, that is completely meaningless because the torus is Euclidean. I might have called the second time and the first spatial. Okay, and this fact that there is no special time cycle goes by is in some sense a symmetry of the partition function written here, and is known as modular S invariance. Though the partition function, which is a number, is the same no matter what you call time, there is something special about time because eventually we will want to Wick rotate the time and go to Lorentzian space, and then it matters whether we are looking at this or that. And this I have illustrated here. So I've taken a case where beta is much bigger than 2 pi r. So the equality is that this partition function and this partition function are the same. Okay, but when we Wick rotate, we get two different states. In this case, we get a state on two thin cylinders with low entanglement, and in this case, we get a state on two thick cylinders with high entanglement. And states created by these half semicircle path integrals are called thermophile double states. As I'm sure most of you know. So let's say a little more. Let's now specialize to holographic CFTs. Now we will work with holographic CFTs that are dual to pure gravity, quote unquote. There are no such CFTs, but we will take this approximation, and the fact that we work in this approximation is a big footnote to the results of this talk. Okay. And what does it mean to be dual to pure gravity? It means that the only primary of dimension less than order C is the stress tensor. We do not actually know of a single CFT with this property. There is some evidence that averages of CFTs can have this property, but I don't know if the question has been settled. Okay, so in these cases, the partition function actually looks really simple. Minus log z looks like the minimum of two terms. In this equation, evac is the energy of the vacuum, and evac of 2 pi r is the energy of the vacuum on a circle of length 2 pi r. Okay, so you can see that the two terms correspond to the vacuum on 2 pi r propagating along the beta cycle, or the vacuum on beta propagating along the 2 pi r cycle. This is the minimal form consistent with modular S invariance, and it turns out that this formula has an extended range of validity for holographic CFTs, which was shown by this paper here. Okay, and the Hawking page transition is nothing but the transition between these two saddles, and as you can just by eyeballing this formula, this transition happens at beta equals 2 pi r, right? because that is a symmetric point. So when beta is greater than 2 pi r, we are in a low temperature phase. When beta is less than 2 pi r, we are in a high temperature phase. The low temperature phase and high temperature phase, when we go to the corresponding Lorentzian thermophile double and look at the bulk dual geometries, have a very nice form. The low temperature phase is what's known as thermal ADS, is 2 copies of vacuum ADS with entangled bulk fields. The high temperature phase, it just looks like a two-sided eternal black hole. And this can be, and this was the original Hawking Page transition. Hawking and Page's paper was about this transition. And later with ADS CFT, people understood more about the CFT dual of this. So the thermal ADS saddle, of course, gives a contribution which is beta into evac of 2 pi r, which is the vacuum propagating in the direct channel. And the BTZ saddle, so this is a BTZ black hole, looks like the vacuum propagating the cross channel, which can also be written in the thermodynamic form as minus the Cardy entropy at some conformal dimension delta, plus some excited state propagating along the beta channel. And right, and this conformal dimension is related to beta and 2 pi r by this equation. The details are not too important, but notice that at the symmetric point, this becomes C over 6, which is the level we saw earlier. And of course, when beta is less than 2 pi r, then the number increases, the conformal dimension increases. So this is the smallest conformal dimension for which the bulk is a black hole. And the corresponding horizon radius, so RH is the radius of the horizon, is just the ADS radius. Okay, so this is the Hawking Page level. Okay, so this is my quick introduction to Hawking Page transitions. So this is so we actually have now spoken about all the three things that turned up in the title. We are going to go from the Bekenstein-Hawking entropy to the Gibbons-Hawking entropy via the Hawking Page transition. Okay, and so what I've told you so far is about pure de Sitter or purely holographic CFTs. The way I will relate these two different systems is via the TT bar plus lambda 2 deformation. The TT bar plus lambda 2 deformation is a deformation of a 2D CFT defined by a differential equation of the partition function. The differential equation is given here. There is a parameter lambda. When lambda goes to 0, you end up at the CFT. Morally, the first term in the differential equation is determinant of the stress tensor, which is also known as TT bar. And the second term is just an integral of 1. And both the determinant of stress tensor and 1 are special operators in that they exist in a large class of theories. The fact that determinant exists in a large class is a very non-trivial fact proven in this paper over here. Now, notice that we said lambda is a deformation parameter. So we want to turn it off and get the CFT partition function. But here, if you look at this, this is not generically possible because there's a lambda in the denominator. Why is there a lambda in the denominator? Dimensional analysis. Lambda has dimensions of length squared. An area has dimension of length. The left-hand side has dimension of 1 by length squared. So you need a 1 over lambda squared to make up the difference. Right? So only when eta equals 1 can you send lambda to 0. Otherwise, this lambda 2 term diverges. So we start with this as a boundary condition, that when eta equals 1 and lambda equals 0, we get the CFT partition function. Now, then to define the theory for eta not equal to 1, we have to do something else. And for this, we make the following observation, that this lambda 2 term becomes unimportant when little lambda goes to infinity. Right? And so we say that no matter what eta is, it flows to the same value at little lambda equals infinity. So this is our definition of the theory. We have a differential equation and we have boundary conditions. Okay. Cool. And this is a solvable theory in the sense that we can find in all the energy levels on a circle of radius r, and they look like this for eta. Here I have defined a dimensionless combination lambda hat, which is lambda over the radius squared. And as you can imagine, everything important is encoded in lambda hat, not in lambda itself. So here delta minus C over 12 is the conformal dimension minus the Casimir energy of the vacuum. Minus C over 12 is of course the energy of the vacuum in CFT. And the thing to notice about this formula is that it has a square root. And square roots famously are not necessarily real. So what are the conditions for reality? So suppose eta equals 1 and delta is greater than C over 12. Okay, then lambda hat has a maximum value. So notice that this is very weird because we just said that we are interested in lambda hat going to infinity. But here for delta greater than C over 12, there's a maximum value. But this kind of makes sense because you said eta equals minus 1, say, or 0. The square root is only real if delta is less than C over 12, right? Because the second term has to be positive. And now lambda hat has a minimum value. So it all makes sense. Clearly the eta not equal to 1 theories are very weird in that they have very few states. Say eta equals minus 1 theory because delta has an upper bound, which is C over 12. This we can understand from the bulk as well. So for eta equals 1, this deformation takes a holographic CFT to the quote-unquote dual of finite cutoff patch of ADS3 with Dirichlet boundary conditions. So in the vacuum ADS, the CFT is dual to the entirety of vacuum ADS, but the deformed theory might be dual to just the blue region, or in the black hole, or for a black hole pure state, this blue region, where this is the horizon, and this is this line here is a cylinder, and yeah, so everything between the horizon and the boundary cylinder. Okay, this piece here, by the way, is where we assume that the CFT is dual to a pure gravity theory, and one hopes that one can correct this assumption with the in-perturbation theory. But for this talk, we will stick to the regime where this is exactly true and CFT is exactly dual to pure gravity. Cool. And the size of the cylinder, the radius of the cylinder, is given by 1 over root lambda hat. This is 4GNL is some factor, and the stress tensor is given by the extrinsic curvature on the boundary of the blue region, right? And this G mu over L gives you the uninteresting one part in the energy formula here, and the square root comes from the part dependent on extrinsic curvatures. And the upper limit on lambda hat we can now understand as the Dirichlet wall hitting the black hole horizon. Okay, because as lambda hat increases, capital R decreases, and at some point capital R will hit the radius of the horizon. This is for eta equals 1. For eta equals minus 1, we will, for general eta, the theory is dual to a bulk theory. The 2D theory is dual to a bulk theory with this cosmological constant, which is proportional to minus eta. So for eta equals minus 1, the cosmological constant is positive, and we have de Sitter. Okay, and the effect of lambda 2 disappearing when little lambda went to infinity was the same as saying that this cylinder here becomes really thin, so the inside looks flat. And so, you know, and the point is when you zoom into any space very close, what you have left looks flat. And that is the reason that the deformation looked universal in that limit. And yeah, so we use the boundary condition we mentioned earlier of matching at really small cylinders to define the theory in de Sitter. Okay, and now the upper limit on delta also makes sense, because in 3D there are no black holes when lambda 3 is positive. Okay, so anyway, after all the dust has settled, we have a theory dual to the orange region here. This is again a cylinder, and we call this region the pole patch. And the minimum of lambda hat that we mentioned earlier is when this pole patch boundary hits the cosmic horizon. But notice that the cosmic horizon is not included in the bulk. Okay. So this is kind of dissatisfying. There's no, it's all consistent, but the interesting part, the part that has all the entropy, is not included in the theory. But so this was the situation for a while, till this paper by Vasudev Shyam came out, which found an actual inconsistency, where he showed that the torus partition function of the de Sitter theory at high temperature gave us a thermal entropy. Okay. Gave us the Gibbons-Hawking entropy. So we have a theory without a cosmic horizon, which has the entropy of the cosmic horizon. Not only is this weird, this is inconsistent, because as I mentioned, the number of states of delta less than 0 at 12 do not scale with G Newton. They're order G Newton power 0. But this entropy is order 1 by G Newton. So there's much more entropy than states. And this is a torus partition function. It should have a state counting interpretation. The method he used to prove this was that he assumed modular S invariance. And he took the partition function to be just the contribution coming from the vacuum propagating the cross channel, the high temperature contribution we mentioned earlier. From here, you take the derivative, you get the entropy. So let's try to understand this in the bulk. So the pole patch we mentioned earlier has a metric of this form. This is Euclidean. The time has periodicity because it's Euclidean and it's a partition function. And yeah. And rho, which is the rho, has includes the pole, which is at rho equals 0 and has an upper limit. Now we do a modular S transformation, which means we exchange space and time, and we define R as the radius of the new spatial circle, which turns out to have this value. And after the dust settles, we end up with the same metric with some renamings, but with a different range of R. Now R goes from some minimum value to L, and R equals L was the cosmic horizon. So here we had a theory, we had a region without the cosmic horizon, we did a modular S transformation, and we found the cosmic horizon, which is similar to what Vasu did. And in pictures, it's easier to draw in Lorentzian space. The original theory, the thermophile double looks like this, just 2 copies of the pole patch. We do a modular S transformation, we get a region including the cosmic horizon. So this is why the S invariant theory had horizon entropy. It's because it has the horizon. And basically the point is that new states were added. The assumption of S invariance was not innocuous. It actually did something non-trivial. Okay. And one thing you notice is that if you calculate the energy using the extrinsic curvature in this phase, you get something that is just not included in the previous set of energy levels, which again goes with our intuition that new states were added. Okay, So I see I'm running out of time, so I'll be a bit quick. I just have a few more slides, so I'll just wait for the question if you don't mind. Basically the point is that now we have to look for new energy levels, and the way we look for new energy levels is we find a new boundary condition for the eta equals -1 partition function. And we noticed from the differential equation, that we could have put a boundary condition of this form for any non-zero value of lambda, because this only diverges at lambda equals 0. Right? So, is there such a nice non-zero value of lambda that we care? That looks nice. The answer is that basically it's when the Dirichlet wall hits the horizon. And this is because just like when we zoomed into vacuum ADS, we got flat space. When we zoom into a horizon, generally we get Rindler horizons. Okay, so this is a small calculation showing that whenever you go to a near horizon region, you get a Rindler horizon. You get Rindler space. And so we just take lambda naught as corresponding to the limit in which the boundary of ADS hits the horizon of some particular black hole. Now, which black hole? Now, when we actually get the near horizon metric to be Rindler space, we find that the circle has a specific radius, which is not open to us. It depends on where the horizon is, So we have to match the horizon radii across the transition. And since we are interested in the cosmic horizon, whose radius is L, we choose a black hole with the same radius. This radius, as we have seen before, it is the radius of the black hole dual to the Hawking page level. Okay, so I've written down
5 more minutes.
Yeah, thank you. Good. So I've written down the flow here. So the wall to horizon limit, as I mentioned earlier, is the one in which the square root of the energy formula vanishes. Okay, so this is the square root of the energy formula for eta equals 1, which is ADS. And as you can see, we replace delta equals C over 6, which is the Hawking page level here. And so that gives you a certain value of lambda hat naught where it vanishes. So our rule is we start with the CFT energy at this level, okay, which is this. We do the eta equals 1 deformation to lambda hat naught. We get this energy. We now flip eta to -1 and keep increasing lambda hat. And then we get this energy. And this energy is exactly what we found from the high temperature phase in the partition function. Okay, so now for node, we can do this for every energy eigenstate here. How many energy eigenstates are there? A Cardi entropy worth, right? So we end up with a Cardi entropy worth of energy eigenstates here. But we already mentioned that the Cardi entropy at this level is the Gibbons-Hawking entropy. So now we found the right number of states dual to a region with the cosmic horizon in it. This is a state counting interpretation of the Gibbons-Hawking entropy. Now this is the main result. So let me add 2 footnotes. One footnote, as I mentioned earlier, is that we assume the existence of a CFT dual to pure gravity. Where our hope is that we can go beyond this in perturbation theory. The other footnote is that we don't actually know that much about the microstates of a given black hole. We just know some very coarse-grained stuff like the number of microstates. So the actual statement is, if some magical elf came and gave you control over all the microstates of the black hole, you would be able to play with those microstates and get microstates of the cosmic horizon. So I will skip these 2 slides. So I told you here the deformation for a given level. One can ask about other values of delta, and it turns out that there are 2 proposals that we found, and both of them agree at the right value. But I will skip over that to the summary. So again, we defined the TT bar plus lambda to flow of a 2D holographic CFT, quote unquote, dual to pure gravity, that deforms the black hole microstates at delta equals 0.6 and ends up with giving you a state counting interpretation of the Gibbons-Hawking entropy. To summarize what we did, the original flow was taking the CFT, doing TT bar to large lambda, and then going backwards with eta by adding the lambda to term. TT bar, of course, is just the eta equals 1 deformation because the lambda to term vanishes. And this gives you states dual to the pole patch, and there are only order 1 number of states. You do an S transformation, you end up adding new states dual to a region considering the cosmic horizon. And the deformation that gives you this is you take the CFT, you do TT bar to a finite value, and then add a lambda to term and keep increasing lambda. These 2 flows look like they have nothing to do with each other, but it turned out that this flow plus modular S invariance forces you to have this flow. Okay, and there are 2 extensions to other levels. So this I have actually defined this flow only at delta equals C/6. At other levels, there are 2 possibilities, and we discussed them in the paper. I did not discuss them today. So I'll just tell you some further questions. One question is whether we can reproduce log corrections. For that, we require spin, as actually Ashok showed in a paper from a while ago, that the log corrections to black hole entropy or and also Gibbons-Hawking entropy require including spinning states. And today we set spin exactly to 0 everywhere. The other question, of course, is higher dimensions, which is more interesting. And then a natural question that appears when you start thinking about higher dimensions is that today we saw that the black hole horizon became the cosmic horizon. And there's a reason for this, because in 3D, de Sitter just doesn't have black holes, right? In higher dimensions, does the ADS black hole horizon become the cosmic horizon, or the black hole horizon of de Sitter, or either one depending on mood? This is an interesting question. Actually, we don't know the answer yet. Third one is adding matter, which is going beyond the dual to pure gravity assumption I mentioned earlier. And the reason this is hard is because earlier I just very cavalierly changed eta because it's just a classical solution. But in the case of matter, changing eta becomes a matter of changing the vacuum. And this is a kind of non-trivial step. So we don't know everything about what is required for this. Fourth point is that now we have a thermofield double, including the cosmic horizon. So once you have thermofield doubles, lots of papers have been written about the thermofield double in ADS. All those papers can be written with the flip of the cosmological constant. And immediate question is calculations of entanglement and quote-unquote top complexity, which is something I'm working on with Evan Coleman and Sangyan Yang. Hopefully, we will put up the paper soon. The second one is, the last point is thinking about how to get the entirety of de Sitter, not just one patch of it. And the broad idea is to take 2 copies of the partition function and integrate over the boundary metric in some way. So that one copy gives you the hope is that if one copy gives you this region and one copy gives you that region, and we're able to integrate over the metric of the joining region, we might get a theory where metric everywhere is dynamical, including here. And it includes all of de Sitter. We tried some ideas, it didn't quite work. This is the last question. And with this, I would like to end my talk. Thanks a lot. And I believe Somdatta had a question that I rudely said no to. Thanks a lot.
Okay. Thank you, Ronak. We have time for 1 or 2 very quick questions. I can see hands, Somdatta. If it is a quick question, you can ask. Otherwise, you can go to discussion sessions.
It's a quick question. Could you go back to your first slide where you had the Penrose diagrams for the de Sitter? Yeah. So the poles mean that, does the pole mean the right pole, does it mean that it's a initial singularity?
No, this is a Cauchy slice here. So these two poles are here and here. Like these are spatial slices. So de Sitter, the spatial slice really looks like a sphere.
Spatial slices, but the Penrose diagram has to have time, right?
Oh yeah, but sorry, this is the Penrose diagrams.
Yeah.
This is the
So in the
slices.
Penrose diagram, the R equal to 0, what does it indicate? What does it mean? What does it mean to have R equal to 0? Does it mean that
so R is no, it's at the space. It's not initial because it's first of all it's at to get to that from any bulk point you need to move in a spatial direction, and secondly it's not a singularity because basically you can look at the metric and it's smooth. What R equals 0 means is that basically some internal space is shrinking. In de Sitter 3 case it's a circle, and any internal space can shrink in either a smooth way or a non-smooth way. In ADS, at the singularity here, it shrinks in a non-smooth way. Here, it shrinks in a smooth way.
Yeah. So in any case, it's Okay, I'll talk in the discussion session.
Okay.
Maybe we can.
Are there any other questions? If not, let us thank the speaker again. And thank Ronak for a nice talk. And the next speaker is Siddharth Prabhu from ICTS Bangalore. And the title of his talk is The Asymptotic Structure of Gravity in Higher Dimensional Flat Spacetime. Okay, Siddharth. Hello. Yeah, you can start.
Can you hear me?
Yeah.
Okay. Yeah, so welcome everybody. And my name is Siddharth Prabhu. I'm a postdoc here at TIFR Mumbai. And before I start, I would like to thank the organizers for this wonderful conference and for giving me this opportunity to present my research here. And I would also like to give, thanks to you guys for making it thus far and to one of the last talks of this conference. And I would like to give a shout out to my collaborators with the work that I'm presenting today is about the asymptotic structure of gravity in high dimensional flat spacetimes. And this is in collaboration with Chandramouli Chowdhury, who is a grad student at ICTS, Ruchira Mishra, who was an undergrad at IIT Roorkee and now is a grad student at University of Chicago. And this is motivated by earlier work and ongoing work with Aalok, Suvrata, and Pushkar, who's also a postdoc here at TIFR. So I want to motivate my talk by starting with the question, where does all the information in the universe reside? By which I mean, if you were to if you want to ask about some question about some process that's happening in the universe, where do you make your experiments? And the first answer to that question is everywhere. There's this, you can do experiments anywhere in the universe and you get some information. But this is of course a redundant description. In principle, there are subsets which contain all information. And that's the idea of having a Cauchy slice of the spacetime. So you have all the information on a particular Cauchy slice, but is that minimal? And our investigations of the past couple of decades have led us to this conclusion that at least in asymptotically ADS spacetimes, one can just look at the boundary of a Cauchy slice, and all the information that's present on the Cauchy slice is also present on the boundary of that Cauchy slice. So that's the answer that we seem to get in asymptotically ADS spacetimes. But we would like to move away from that and perhaps come a little closer to our universe by understanding asymptotically flat spacetimes. And if we do that, here is a Penrose diagram of asymptotically flat space. So you have null lines which start from scri minus past null infinity and go to scri plus, which is future null infinity here. And then you have the past of future null infinity, which you call scri plus minus, and the future of past null infinity, which is called scri minus plus. So we don't know how to define quantum gravity non-perturbatively in flat space. And flat space has a very intricate infrared structure. And there have been various proposals about how to do holography in flat space before. But a couple of years ago, we started trying to answer this question of how is information stored in flat space. And we came to the conclusion in this paper about this paper that we put out last year with Aalok, Suvrata, and Pushkar, that at least when you look at massless excitations, all information about massless excitations in the theory of quantum gravity can be obtained from the past boundary of future null infinity. And to make this thing work, even though we don't know everything about the full theory, we have to make certain assumptions about it, which is based upon our understanding of the low energy structure of quantum gravity. And those assumptions are that the spectrum of the Hamiltonian is bounded from below, and that near scri plus minus, you have operators which can label the vacuum of the full theory and can map the space of vacuum back to itself. So under these assumptions, you get the conclusion that all information about massless excitations can be obtained from the past boundary of future null infinity. If you make a further assumption that the evolution equation of the Bondi mass and its commutators with the asymptotic operators continue to hold, you also get the statement that all information in a cut of future null infinity is present in an earlier cut. And so there is an intricate nested structure of information storage at null infinity. And if you look at the Penrose diagram from before, we define two kinds of algebras of operators at null infinity. One which is at some finite u, so this is a u naught epsilon, and one which is at the past boundary of future infinity, which is marked here in red. And the statement then is that if you look at this full Cauchy slice of Sky plus, then the information that's contained there is actually contained just in its boundary, which is in this red region. And if you look at a finite region of Sky plus, then its boundary is this blue region where the information is contained in just the boundary again. So this leads us to the principle that the boundary determines what's inside, or a principle of holography of information. Now we'd like to understand how much of this story holds for higher dimensions. And in doing that, the crucial thing is to understand the algebra of operators here at let's say the past boundary of future null infinity, and to see if it continues to retain the structure that it does in 4 dimensions. But before getting there, one might also ask, I've only talked about massless fields, so one might ask, what about massive fields? And so I'd like to, even though this is not the focus of my talk today, I'd just like to mention some results we now have about massive fields. And this is also work with Aalok, Siddharth, and Pushkal. So naturally, you would think about massive fields at future or past time-like infinity, which are these 2 points here on the Penrose diagram. But instead, we'll be looking at spatial infinity. So if you look at the first line here, which is the metric of Minkowski in these coordinates, rho, tau, and omega, where rho is the light cone distance, then usually you'd think of of spatial infinity as a point on this Penrose diagram, but you need to actually blow it up in order to make sense of fields, of taking this limit to spatial infinity for various fields. So you do that by looking at this metric, and you take rho going to infinity while rescaling these constant rho metrics by 1 over rho squared. So once you do that, in this diagram, if you see, these orange regions are regions of fixed tau. And as you go to rho going to infinity, you get a d-sitter, a 3-dimensional d-sitter at spatial infinity with this metric here. And then you can get massive fields on that d-sitter 3, which is at spatial infinity. So if you take a massive field in the bulk phi rho comma x, where x are these coordinates tau and omega, then unlike massive fields, unlike massless fields, which have a power law decay as you go to null infinity, massive fields exponentially decay as you go to spatial infinity. And so the extrapolate dictionary works slightly differently. So in order to be able to detect them, you need to measure these exponential tails. So you can define an extrapolate operator, which is here defined like this by using an exponential of rho. So if you do that and you get these z of x's defined at spatial infinity, then the statement is that we continue to find that information about massless and massive excitations in the bulk can be actually obtained by taking a union of the past of future null infinity, which is this red line here, and this green region, which is some open set on spatial infinity. So you consider correlators like this, where the fields on the left here are all the ones that you got on the past to future null infinity, and the fields here, the z's, are fields that you're getting on some open set on spatial infinity. So with that, let me come to the focus of today's talk, which is to try and understand what the asymptotic structure is in higher dimensional spacetimes, and if we can say similar things that we've said in 4 dimensions about high dimensions. So the first thing I would like to say is that we want to restrict to even dimensions, and that is because if you there's various reasons for it, which is that if you look at, for example, the Green's function, and you look at how it behaves in odd and even dimensions, then you see that in even dimensions, it has a regular behavior with some power law fall off. But in odd dimensions, there are non-integer fall offs, which lead to some non-analyticities. And hence, for now, we would like to only talk about even dimensions. And then let's see what is known in higher even dimensions. So the first observation that was made by these people is that in higher dimensions, there is a qualitative difference with respect to 4 dimensions, which is that you can choose boundary conditions for asymptotically flat spacetimes that include radiating spacetimes, but they don't include supertranslations. So it is consistent to not have supertranslations, and that's what these authors pointed out. And further, they pointed out that if you were to include supertranslations, then you'd probably run into problems with defining the symplectic structure. As you have heard probably before, and in this conference, in this nice review talk by Laura, there is a connection between soft theorems and supertranslations. And this connection continues to hold in any dimension because the soft theorems hold in any dimension. And this connection is that if you look at the word identities that come from supertranslation symmetries, you get soft theorems. So motivated by this statement, these authors here put some relaxed boundary conditions and saw that you could indeed include supertranslations with some relaxed boundary conditions. However, they did a linear analysis of gravity in high dimensional spacetimes, and if you go beyond the linearized analysis, you run into issues which was already pointed out in this paper here by Ankit Agarwal, where he constructed finite charges for the linearized case, but also saw that if the fall-off conditions that one would need to impose on these fields in the linearized analysis would get violated once you go away from the linearized analysis. So our job then is to take a step back and find what is the asymptotic phase space in high dimensions in the full nonlinear theory, and whether the conclusions that come from the linearized analysis continue to hold in the full nonlinear theory. So with that, let me come to the plan of my talk. I've already given you the introduction and motivation for the talk. Next, I want to set the stage by talking about the asymptotic metric and what are the fields that we get from there. And then we want to look at the action of supertranslations on this asymptotic metric, taking the point of view that given the soft theorems exist in any dimension, we would like to have supertranslations also, and we'd like to understand what the effect of supertranslations are. Finally, we'll look at the Bondi mass and supertranslation charges, and then we'll conclude the talk. So to set the stage, in the Bondi gauge, the metric looks like this in any dimension, where there are these arbitrary alpha, beta, UA, and GAB that I've written. Now, we want to make the assumption that as you go to infinity, you get just Minkowski, and then there are corrections to this. So here the assumption is that there are no corrections to the Minkowski metric which diverge as you take R going to infinity. So we are going to impose just that one restriction, and then we're going to try and find what Einstein equations tell us about the form that this metric can take. So since we are in even dimensions, the alpha, beta, UA, and these GAB, we expand in integer powers of R in this way. And the first thing to do is to try and see what are the constraints on all these quantities appearing here in the metric. So the first thing that we'll see is from the Bondi gauge. So we've already imposed these two conditions of the Bondi gauge in the metric that I've just shown. Now we'll impose this last condition, which is the Bondi determinant condition. And you see that if you want to impose this condition, what you end up with is a condition on the trace of each of these C's that appear. So here you have the CA, what I'm calling the CAB ends, and the Bondi determinant condition will determine for you the trace of all of them. So in notation that will be particularly useful later in the talk, I'll call CAB1 as CAB, CAB2 as DAB, and CAB2 as EAB, so CAB3 here as EAB, which is so this one goes as R times CAB in the metric. This one goes as R to the 0, and this one goes as 1 over R. And so you will see that this condition here in the full nonlinear theory gives you the traces of each of these quantities. Next, we'll look at the implications of the Einstein equations. So if you look at the RR component, you end up with this equation here, which tells you that all of the beta n's that we had, we can write in terms of the GABs. So for example, beta 1, beta 2, beta 3, and so on are determined in this way. Next, if you look at the RA component of the Einstein equations, then you see that you get this equation here. This is again the full nonlinear theory, and you see that the UAs that we define now also get fixed in terms of the GABs or the CABNs. So for example, UA0 is this, and UA1 is given by this expression here, and we're going to have to use some of these for our computations later. Finally, we'll come to this RUR component, and now we see that this constrains the alpha, the alphas that were appearing in the metric, and they are constrained by this equation here. Everything on the right is already determined in terms of what we found earlier. So then we can go ahead and solve for these alphas. But you notice that the left-hand side here disappears if you put alpha n, if you put, once you expand for alpha and you put alpha, and you take alpha n such that n equals d minus 3. So except for alpha d minus 3, this equation determines everything, all the other alphas in terms of the CABNs. So coming back to this metric here, then what we have seen is that Einstein equations tell us that the alpha n's, beta n's, and the UA n's are all determined in terms of these CABNs that appear along with that appear as corrections to the ST-2 metric, and except for this one quantity, which was alpha d minus 3. So at this point, you can make a guess for what the alpha d minus 3 is. It's the analog of the Bondi mass in general dimensions, and which would be determined. Its u derivative would be determined by the constraint equation coming from the Einstein equations. And the other fields at this point are these CABNs. So we know that in d dimensions, radiative fields fall off as 1 over r to the d by 2 minus 1. So then you expect that the radiative degrees of freedom are contained in this in a particular CABN with n equal to d by 2 minus 1. And you see this fact borne out if you look at the AB component of the Einstein's equations. So first, let's look at the leading order. And what you see in the leading order is that at r to the 0, you see that if you are in d equal to 4, this doesn't give you any constraint. But if you're in d not equal to 4, it tells you that del u CAB is 0. So CAB is just u independent. And in fact, if you look at the all order expansion, you see that at every dimension, there is precisely one of these CABs whose u derivative is not fixed. And it's precisely that CAB which corresponds to the radiative fall-off. So this bears with the expectation that we have that the independent field here is the one which corresponds to the radiative fall-off, and so the u derivative of that field is not fixed, whereas u derivative of all other fields that appeared in the expansion of this metric of ST-2 is fixed by this component of the Einstein's equation. So let's then before we go ahead to the Bondi mass evolution equation, let's look at what happens in 4 dimensions. In 4 dimensions, the
Siddharth, can I ask you something here? So in the UA,
you don't see the angular momentum aspect?
Sorry, can you? I couldn't quite hear you.
In the UA, you don't see the angular momentum aspect. So you talk about the mass aspect, but there is also angular momentum.
Right. So I have not looked at the I'm not looking at the angular momentum aspect here, because as we'll see, since we are only interested in super translations, we only needed the Bondi mass aspect. So in the 4-dimension case also, I'm not really writing down the angular momentum aspect here.
Yeah. Oh, okay. Thanks.
What do you mean by radiative fall off?
Oh, I only mean that if you look at how does the if you just ask how does radiation fall off in d dimensions, then you get the fall off to be 1 over r to the d by 2 minus 1. So,
and why is that related to del u Cn not being equal to 0?
Yeah, because you would expect that if you would expect that the physical degree of freedom is there in this radiative in the part of the metric which has the radiative fall off, right? You should not be able to determine its u derivative, because if you did, then there is no radiation, right? Because the fact that the CAB varies along Scri plus is what is the fact that radiation is reaching Scri plus, right? So there is some function which is varying along Scri plus. So you would want so that's the field here, and so its u derivative should not be fixed, which is what we are seeing from the equation of motion. Okay. So in the 4-dimensional case, at this point you would get this metric here, and so this guy here with the 1 over r fall off is the Bondi mass, and this and CAB is what comes in this way. And just to recap, the Bondi mass is the angular density of space-time energy. So if you took the Bondi mass and integrated over the S2 in 4 dimensions, you would get a notion of space-time energy, which if you took u going to minus infinity limit of, you would get the ADM mass. And if you took the u derivative of this of m of u defined here, you would see that it's proportional to n squared integrated over the S2, where n is the u derivative of CAB. So NAB is the analog of the electromagnetic field strength, and so its square gives you the flux of gravitational radiation that's passing through a particular S2 on Scri plus, and that's related to how the mass of the space-time changes. So in d dimensions, we expect a similar story with the right CAB, which is the one with n equal to d by 2 minus 1, and then you expect that if you took its u derivative, then you define a news in d dimensions, and then if you integrated that on the SD minus 2, then that gives you the flux of radiation passing through some portion of Scri plus. So in 4 dimensions, the constraint at Scri plus is given by this equation here, the u derivative of the Bondi mass. And you can define an infinity of charges, which are the super translation charges, by taking the Bondi mass aspect and integrating it at Scri plus minus on an S2 with an arbitrary spherical harmonic. And now if you took this expression here and you rewrote it as an integral over all of Scri plus, then you get 2 contributions, one which is linear in the news and one which is quadratic in the news. The linear guy is called the soft charge, and the quadratic guy is called the hard charge. So this is what happens in 4 dimensions. And in order to make we'd like to see if something like this happens also in high dimensions, and we'll see what are the issues that we run into. But before that, let's the fact that you have these infinity of super translation charges means that you can see that there are eigenstates of these super translation charges, and those are the degenerate vacua that you get in 4 dimensions. And so the Hilbert space structure in 4 dimensions has this form where there is one particular soft sector that you can build on top of one of these degenerate vector using all your news operators and other matter fields that you have. And then your full Hilbert space is a direct sum of these various soft sectors that you built in this way. So you can use these guys to get in. Oh, okay. Okay. Okay, all right. So so then I'll just skip through this part, and point here was just to say that using these operators M, N, and C, you can build the algebra of observables at Sky Plus, either at a fixed U or at U going to -infinity. So if you now come to what happens in high dimensions, in 6 dimensions, the equation for the constraint equation for the Bondi mass looks like this, and you see that it's a horribly complicated equation with a lot of nonlinear terms, and so it at first glance seems like there is very little chance of making something like the 4-dimensional story work out. But in order to see how to make it work out, we'll go to the action of super translations. And one can see that so we saw what the metric looks like in the Bondi gauge. If you ask what are the general class of diffeomorphisms that leave the form of the Bondi metric invariant, in D dimensions you get this form, where the diffeomorphisms are parameterized by a single function f, which is a function on the st-2 at infinity. And in 4 dimensions, if you looked at what happened when you acted with these super translations on CAB, you get this form. So you get 2 contributions here, one which is just the news tensor, and the other which actually doesn't depend on CAB. Further, you know that in 4 dimensions, the asymptotic structure simplifies and you get a free theory where the CAB is symplectically paired with the NAB. So right from this expression here, then you can see that you would have one contribution to the charge, which becomes quadratic, which comes from this term, and one contribution to the charge, which becomes linear, which comes from this term here, depending on f. So that's how you get both the soft and hard charges in 4 dimensions. Now, when you go to d greater than 4, the first term disappears, as I just told you that del UC is 0. So you only get this second term here. So it continues to hold that if you started off with a solution where you put CAB equal to 0, then super translations will turn CAB on. And so if you asked if you thought that the only physical degrees of freedom are in the radiative mode and in the Coulombic mode, you should also be considering this guy, because if you believe in super translations, then super translations will turn CAB on. So but if you look at what the content of super translations is, it's just a single scalar function on the SD-2. So whereas the CAB is a full tensor worth degree of freedom on the SD-2. In other words, if you did a spherical harmonic decomposition of CAB, you would get a tensor part, a vector part, and a scalar part. And as we have been arguing, the only reason to keep CAB is that super translations turn it on, which means that the tensor and the vector pieces have no physical information, but only the scalar pieces have physical information. And the Bondi condition, the Bondi determinant gauge condition sets trace of C to 0, and so we are only left with this last term here. So which all of this is amounting to say that we can think of CAB as a pure super translation, and that is the physical meaning that we want to give to CAB in any dimensions. And so we shall choose CAB to have this form here, where if you acted on this now with a super translation, then you would just change the psi to change the psi by the f that the super translation acts with. Okay, so with that, then let's look at what happens to the other CABs when you act with super translations. And what happens is that they always give you so you want to really look at in some dimension D, you want to look at the d/2 minus 1, the CAB d/2 minus 1, and super translations will act on it by having this first piece here, which is dependent on the news, plus a whole bunch of other terms which depend on the CABs at lower orders. So you see that if you started off with a solution where you just turned off everything, and you acted with the super translation, then only CAB gets turned on, because the only CAB has a part here that is just a function of the F that the super translation acts with. But in high dimensions, now you see that in 4 dimensions, you see that now things were special because CAB had 2 pieces, one which was depending on the NAB and the other which was just depending on the F. And here you see that the role of super translations is actually played by 2 different fields, one by CAB itself and one by CABD by 2 - 1. So this gives us some hint as to how to proceed in high dimensions. So to be concrete here, we'll now stick to 6 dimensions, and we'll look at the action of super translations on the CAB and on the radiative mode in 6 dimensions, which I'm calling DAB. So you see that if you put D equal to 6, these are the things that you get. And now to really recover the role that, so we said that CAB, which had 2 roles to play in 4 dimensions, is now in 6 dimensions, the roles are being played by CAB and DAB. And to really see that, we want to, you might be motivated at this point to see that since the CAB changes, the super translation changes CAB by this amount, you want DAB to only change by the news piece and not by all of these other pieces here. In other words, you want to define a D tilde, which can be defined in this way, which satisfies the following property. If you act super translations on this D tilde, you only get this one piece, which is F times del U D tilde. So as we shall see, this resolves a crucial puzzle that was also seen. If you try and go beyond the linear analysis that I told you, which is that if you try to get a finite charge in high dimensions, the fall-off conditions that you put on D get violated by the action of super translations when you go to the nonlinear theory. However, you see that if you instead redefine D to get this D tilde, then the action of super translations keeps you within the fall-offs that you put on D tilde. In other words, going from a vacuum where you put CAB equal to 0 to some non-trivial vacuum with a non-trivial value of CAB, one needs to account for that by redefining your fields in this way. So now if you go back to what the Bondi mass evolution looks like, we had this horribly complicated form, but if you redefine things in terms of the D tilde I had on the previous slide, then you can see that the super translation charges get these very nice looking expressions here, where I do the same thing that I did in 4 dimensions and take the super translation charge defined in this way, and then write it as integral over all of chi plus. Then you get a soft contribution and a hard contribution, where I've imposed this fall-off condition here on D tilde, not D, which goes as 1 over U to 1 plus epsilon as U goes to plus minus infinity. So this sort of a condition is also there in 4 dimensions, but here now the good thing is that once you impose this condition, the super translations actually respect this fall-off. And so the charges now are well defined. The other way of saying this is that we propose that for example, in D equal to 6, the symplectic form at chi plus is given by this expression here, and the action of super translations respects the fall-off that you need to impose to get finite charges from this action, from the symplectic form. It continues to hold in 6 dimensions that if you imposed the action of the fact that you have super translation symmetries as a symmetry of the S matrix, then yeah, I'm just done.
Time. Yeah.
This is just my second last slide. Yeah, I'm just almost done. So it continues to hold that if you look at a generic scattering process and you ask for invariance of that, you ask that the full super translation charge, including the soft and hard pieces, is a symmetry, then you see that if you started off with eigenstate of the soft charge, then you will land up at in the in the in state, then you will land up in the out state with a different eigenstate of the soft charge. So the four-dimensional story continues to hold, where you now have a set of degenerate vacua, and you have access to the soft charge, which lets you identify which soft vacua you are in, and there are transitions going from one soft vacua to other in generic scattering processes. So I'll just end my talk by flashing the results. So we have a finite symplectic structure for high-dimensional flat spacetimes, which is consistent with the action of supertranslations in the full nonlinear theory, and it gives us the expected charges, which are consistent with the ward identities from supertranslation symmetries. So we feel resolved the puzzle that was seen earlier in trying to get a symplectic structure for high-dimensional spacetimes, which includes supertranslations. We would like to understand what happens in odd dimensions in the future, what happens if we include massive fields, and if we can write down specific protocols for retrieval of information from the boundary of high-dimensional flat spacetimes. Okay, thank you. Sorry for going a little over time.
Sorry, we don't have time for questions right now. You can ask questions in the discussion section. And so let us thank Siddharth for the nice talk, and we can move on to the next speaker. Okay. Is that all right? Okay. Okay, next speaker is Aalok Misra from IIT Roorkee, and the title of his talk is Differential Geometry of Flavor Memory in M Theory at Intermediate at Hooft Coupling. Okay, Aalok.
Okay, I hope I'm audible and my slides are visible.
Yeah. Everything is fine.
Okay, great. So thank you. Unfortunately, it seems I cannot start with a sentence which most speakers have for obvious reasons. In lieu of that, I'm going to thank the NOC for their kind permission so that I could present the work done by our group. And this work has been done in collaboration with what I love to refer to, at least in my own mind, as VG Yadavs, the very good Yadavs, because they are. Vikas and Gopal, my students, and okay, so basically the talk is going to be about classification of non-supersymmetric geometries relevant to a top-down holographic thermal QCD at intermediate couplings. So that's the basic theme. And a customary outline would go something as follows. I'm going to be quickly reviewing something which I have talked about in previous installments of NSMs, a no-brainer M-theory dual, but this time it's going to be eventually including or inclusive of the quadratic corrections and curvature of, and this is a dual of large and thermal QCD-like theories. And essentially, it's the first steps towards working out top-down thermal holographic QCD at intermediate coupling. In that process, to get some physics context, I'm going to be talking about flavor memory. And I'm going to go back to my thesis days, which is I'm going to make contact with chiral perturbation theory, but from M theory. And I'm also going to be talking about possible non-renormalization of deconfinement temperature, all with the inclusion of terms quadratic into curvature. Then we're going to go to the veggie of the talk, given that I'm a vegetarian, which is the G-structure classification of non-supersymmetric geometries. And we'll conclude with a summary and future directions. Okay, so here is a flow chart of sorts, something which probably I might have shared a couple of NSMs ago, but all the same. So I have no idea whether you can see this hand moving. I pray it is visible. So if it isn't, you should look at the top lower portion of the screen. And that is what spells out the brane construct involving a bunch of branes. This is type 2b part of the story. In a resolved conifold at high temperatures, as worked out with the, I should call it the erstwhile McGill group or the McGill diaspora. And so the gravity dual of the same was also constructed by the same folks. And what we did was to actually analyze. So it's always, I mean, I forgot to say this. I think it is very refreshing for me to be able to not be the only person talking about the stuff that I'm going to be talking about, thanks to Lara Anderson's talk yesterday. So we've already had a quick intro to, in particular, SU3 structure torsion classes. So suffice it to say that in the so-called, what I'm going to be spelling out as the 𝗰𝗶𝗶𝗶 limit, which is an example of a large N limit, the SU3 structure torsion classes, which are 5 in number, are of the type that makes the underlying geometry essentially in the large limit a conformal Calabi-Yau. And so the Strominger-Yau-Zaslow SYZ mirror for this on the gauge theory side was worked out again by folks at McGill. And they ended up getting essentially type 2A construct, this time with a deformed conifold at finite temperature. And what we did was worked out the same for the gravity dual. And so to begin with, we had, in fact, a non-Kähler resolved Watt deformed conifold. That's what the McGill diaspora folks had. And what we ended up getting was, in fact, a non-Kähler Watt resolved conifold, of course, with a black hole. And because we worked out the gravity dual at high temperatures. And with a duality chasing of torsion classes, we also ended up with more or less a conformal Calabi-Yau. And so there's this beautiful table of underlying geometries and the associated restrictions on torsion classes worked out by Mariana Grana, Booty, and so forth. And interestingly, very interestingly, we ended up with a proportionality of the 4th and the 5th torsion classes. If one recalls the Strominger system of supersymmetry n equals 1 supersymmetry heterotic string theory also had a similar non-trivial W4 and W5, but the proportionality constant was different. So the signature 2/3 proportionality constant is indicative of a conifold geometry. We didn't get that, but the proportionality was still there. And interestingly, despite having finite temperature, despite breaking supersymmetry, torsion class-wise, we actually had mildly broken supersymmetry. This could be understood in another way, which I'd probably get to during the talk. And then finally, the whole story was uplifted to M theory, and we ended up with 7 folds with G2 structure. Remember, it's a no-brainer setup without the I. And of the 4 G2 structure torsion classes, we ended up with 2, which essentially carry information about 2 forms and 3 forms. I'll be talking more about this, but this time with the inclusion of out of the 4. This story is pre-COVID. That means as of 2019. All right, now, so what we're trying to address, what I'll try to address is the following proposition. So, the non-Kähler Watt resolved 6-fold, which is obtained as a cone over a compact 5-fold that appears in the type 2A background that I've already referred to, corresponding to the M3 uplift of thermal QCD-like theories at high temperature, in the neighborhood of Wang embedding. So that's a holomorphic embedding of flavor D7 branes of the parent type 2B theory. Okay, and this is done in what was dubbed as the 𝗰𝗶𝗶𝗶 limit, which is essentially this limit that you have the number of color D3 branes very large. However, the number of fractional D3 branes with the D5 branes wrapping the vanishing S2 and the flavor D7 branes to be of order 1, the string coupling is not very small. And there's this crucial ratio, which is GSM² over N, GSM² times any positive integer of GS times NF over N to be much less than 1. That's going to play a pretty crucial role in all supergravity computations. So the proposition is that with inclusion of the LP to the 6 corrections arising from the quadratic terms in the action, in the 11-dimensional supergravity action, we end up with a non-complex manifold. Okay, so however, I did mention that there are 5 SU3 torsion classes. We also know that from Lara's talk yesterday. It turns out that the Nienhuis tensor's information, in particular the vanishing of the same, is actually equivalent to the vanishing of the first 2 of the 5 torsion classes. Now, it turns out that that is not identically true, but it is approximately true in the larger limits, such as the 𝗰𝗶𝗶𝗶 limit. I've already spelled this out. Without the inclusion of out of the 4th, this is retained or preserved, even with the inclusion of out of the 4th, that you have conifold-like constraints involving torsion classes of the 4th and the 5th type for SU3. Coming to the G2 structure torsion classes, so the 7-fold turns out to be a Watt product of a thermal circle times a non-compact R3 and a cone. over which a 6-fold, which itself is an S1 fibration over a 5-fold. So the 5-fold, if you wish, is a non-Kähler generalization of the Sasaki-Einstein 5-fold, where we've got the following as regards the Pontryagin classes. So the square of the first Pontryagin class and the second are trivial, PA being the 8th Pontryagin class, and the G2 structure torsion classes are valued again in what were, even without the inclusion of R to the 4th. Okay, being a Dumbo, I don't really know how to push this stupid mute stop video black bar out of my view. So anyways, so I'm going to do the best that I can. So inclusive of the thermal circular compact X0, we in fact also worked out the SU4 and the other exceptional G structure torsion class, in particular spin 7, and we got the result which is quoted at the last line. Okay, so that was a proposition. Now, that is all good, but well, you need a physics reason. I mean, I needed a physics reason. It would sound good that if I had a physics reason, to be frankly very precise. So the physics reason was essentially provided by largely Gopal and also partly Vikas. And after about a 13-month-long calculation, Vikas was able to actually work out the order out of the 4th corrections to the M-theory dual, which Mansi and I had worked out 8 years ago with the inclusion of order out of the 4th corrections. So the story in the type 2b side with the inclusion of high derivative corrections like order alpha prime cube corrections. I'm also, the team should help me. I'm also admitting folks. So as I'm speaking. So the alpha prime cube corrections in type 2b were already worked out largely because of the expertise of Arkady Cyclin and utilized by the erstwhile, I guess, MIT Oxford group, primarily Grozdanov and Starinets. And but you know, I really have absolutely no idea. It's just too good to be true. But this n=4 super Yang-Mills should not have anything to do with real QCD. But apparently, there's a lot of stuff which goes on. So we were not happy with that, and we decided to actually pursue the M-theory uplift, or what we would consider to be a much closer M-theory uplift of what we call as thermal QCD-like theories, which means theories which have a non-trivial RG flow of the gauge coupling, such that you have UV conformality, infrared confinement, and fundamental quarks. All right, so this is old hat. We all know about this, when we talk about the high derivative corrections. So there are essentially 1, 2, 3 varieties of high derivative terms, which are spelled out on the second line. So one has, perhaps some of us are more used to the so-called T8 notation. So you've got T8 R to the 4th, that's your J0. You've got epsilon 11 R to the 4th, which is your epsilon 8, which is an 11-dimensional generalization of the 8-dimensional Eulerian density. This is the anomaly inflow term worked out by Witten. And okay, I'm sorry, Mike Duff reminded us, no, they beat them to it. So Mike Duff and friends. And then we've got this whole list of terms involving the 4-form fluxes and R cubed with the T8 squared tensorial structure, which was given by Minassian, Simpson, and so forth. We picked out a sample term. And this is with the expectation that you can actually holographically renormalize this action. We will actually make some remarks that it can actually be done. And this X8 or friend is, again, a linear combination of the square of the first for Pontryagin class and the second for the 11th fold. So you got the equation of motion, you got the Bianchi identity, and henceforth, the LP to the 6 corrections are going to be labeled or relabeled as beta. Now, the long and short of the story is this, that you perform an order beta expansion of the metric and of the 3-form potential. And one can actually show, so there's a cool result that we had gotten several years ago, which actually showed that, because remember the triviality of the Pontryagin class, you can actually show that X8 is trivial. And then you also end up with these constraints. So there's a magenta worth of constraints, there's a brown color worth of constraints, and of course a black. Now, stripped CMN henceforth are going to denote the constants of integration appearing in the solutions of the equations of motion for this FMN, which basically encode the information about the order beta correction to the MQGB uplift worked out by Mansi and myself 8 years ago. Now, this keep your, please, I would request you to keep these combinations in your minds. So Z, X, and Y, I apologize, I didn't spell it, I did not spell it out here, are actually the T3 slag analogs of theta1, phi1, and psi, which are the compact part of the so-called non-compact 4-cycle wrapped by the flavin D7 brains in the parent type 2b theory. Okay, so it turns out that it suits one more if one works in two kinds of coordinate patches. If you are restricting yourself to being near the Wang embedding locus of the flavin D7 brains in the parent type 2b story, which is psi to be an even multiple of pi or not. It turns out that in the former, one has a beautiful simplification of a decoupling of the radial direction from the angular directions. Okay. So this is just a sample of what J0 and E8 looks like. What Vikas very painstakingly actually showed is a hierarchy of the higher derivative order out of the fourth terms. And it's written in the last line. Okay, a quick remark about if you work out the on-shell action, one can actually show that first off, you got two kinds of UV divergences of the type written in the last two lines, and one can actually construct systematic boundary counter terms to cancel the same. So now let's come to the first. Yeah, I apologize. There are no pictures. There's one sorry excuse of a graph that I have later on, but it's just black and blue and green with, I don't know why this turned out to be a blue, but blue in my color coding scheme are supposed to be stuff that we've done. Red is supposed to be what others have done, and black is the commentary. Of course, supplemented by my verbal commentary. So what we have here is a list of corrections, and what the second and the third rows, third and the fourth columns, for God's sake. The third and the fourth columns give us is information about the infrared enhancement and the large end suppression. So why do we care? Well, it turns out that the so-called order beta corrections to the M3 uplift can actually symbolically or succinctly be written in the following form. Stripped RH as written here. Actually, I can't see what the heck is written over here because of the stupid black bar. But anyways, it's supposed to be actually a dimensionless object that you construct, which is a ratio of the horizon radius and the d5 to d5 separation, which is something which we use as roughly a boundary between the UV and the UV IR interpolating region in the infrared. Okay, so therefore, I mean, RH is much less than 1. Log of this is going to be something which can be the modulus of log RH can be pretty large. Now, so what you have is therefore a competition between an infrared enhancement coming from these log RH factors, log stripped RH factors, and an N suppression coming from these reciprocal powers of N. So, okay, so then basically what does it tell you? It tells you, okay, if it so turns out that the infrared enhancement wins over the large N suppression, then you are all set to go to the next order in the correction, whatever that is. It also turned out, okay, I don't know why I've written the first point I've already said verbally. The second point has to do with the following fact that very interestingly, the higher order derivative corrections also carry with them, most of them, information about the non-conformality in the story. Now, the non-conformality in the story is actually encoded in the number of fractional D3 brains, so these D5s wrapping and vanishing is 2, denoted by M. If you turn out the M, most of the corrections drop out. Now, okay, I'm halfway through, plus a minute or something. Now, so this is where Gopal steps in. So in fact, I would invite you to check out his talk at what is called as HEPCATS, which is organized by this consortium of IISER Mohali, IIT Roorkee, and bunch of, and in principle, Roorkee also, though we've never done it. So he has a talk tomorrow. He's going to be talking more about this stuff. So he has taught me a lot of stuff. I hope I've been a good learner, at least a moderate one. Now, this is where I make contact. This is kind of an homage to my supervisor, the late Professor Daniel Colton. Of course, back then in the day, I was working from a nuclear physics point of view, but now, of course, So now we're going to be briefly, so let me just mention the summary. So the idea is that if you try to reproduce the Gasoloid-Wheeler's SU3 chiral perturbation theory Lagrangian up to order P to the 4th, P being typically, like, let's say, a pionic mass in the setup, from M theory with the inclusion of order out of the 4th corrections, you end up with some surprises. One of the surprises that you get is actually a connection between a 1/n suppression coming through, let's say, the GSM²/n corrections and these the order out of the fourth corrections. So the manifestation of that is that one can actually show that you can relate the resolution parameter of the blown up S2 and the resolved, the resolution part of the geometry to the infrared cutoff. And so intentionally, this B is supposed to, we call it a bare resolution parameter. So this is the stuff, this is a proportionality constant, which is independent of the logarithm term of R0 and also independent of the non-conformality correction. The message that the takeaway in this is that apart from that competition between the infrared enhancement and large N suppression, there is actually a contribution that you pick up, which is LP³/n, okay, which we had missed earlier. And okay, so this is a kind of a wordy slide. I'm not too wordy myself, but let me just see how we can go about this. So the long and short of this part of this slide is, and probably even yeah, mostly this one. It turns out that the order beta to the order beta correction, the contribution of the order beta correction to the M theory metric, which is used in the coupling constants. If you work in the chiral limit of the chiral perturbation theory Lagrangian, it turns out to have a very specific linear combination of the stripped CMNs that I alluded to earlier. Yeah. So, and these stripped CMNs are precisely the ones which correspond to the compact part of the non-compact force cycle wrapped by the flavor D7 branes in the parent type 2B theory. So this is what we allude to as memory, flavor memory. Okay, so Gopal also taught us this. So apparently there's the cool paper by oh, where the heck is it? But anyway, it's by Klebanov, Morgan, and the third guy, which I don't remember. I'm sorry. Which talks about computation of deconfinement temperature by entanglement. So there's a lot of talk on entanglement. That's where Gopal comes into the story. So he taught us how to calculate deconfinement temperature. So we went about calculation of TC in by two different routes. The one was the usual old Witten style semi-classical computation, and the other one was by this other route that I mentioned. It turned out that there is so this is something that Ashok had also referred to earlier. I mean, there's this beautiful computation of 4 graviton scattering in the presence of a Dean-Sinton background in 1987 by Michael Green, 𝗬𝗓𝗪, Green, and Van Hove. And there it turns out that there is actually, if you look at it, so they conjectured an SL2Z completion of the order out of the fourth contribution in that scattering. And it turns out that if you work in the so-called zero instanton sector, all you have are contributions which are of the type alpha prime cubed, which are like the high derivative corrections in the string theory, and a one loop contribution. Now we actually show that it is actually consistent. One can consistently show that the TC that you calculate with the exclusion of order out of the fourth terms also can stick or can still be the same even with the inclusion of order out of the fourth terms, provided you end up with the following match. So you match the contribution coming from the M theory circle on the thermal side, which is the gravity dual to temperatures below TC, with the same linear combination which appears in the M chiral perturbation theory low energy coupling constants matched with experimental data, which carried information about the compact part of the non-compact force cycle wrapped by our good old flavor D7 branes in the parent type 2B theory. And there was a delicate cancellation which actually showed that you precisely get a zero, you get a null contribution coming from out of the fourth to the TC, and kind of reinforcing the conjecture that we make that possibly there is an all loop non-renormalization of TC in these theories at order out of the fourth. Okay, so this is this excuse of a graph, and I think if I get into this, I'll probably ruin it. But all I'm going to say is this, that so there is an entanglement calculation of a segment with this complement, and if the length of that segment is L, there's a beautiful graph which Gopal got, which simply said that if you plot L versus I mean, you plot entanglement entropy. So there turn out to be two RT surfaces, a connected and a disconnected, which I think is usual. It turns out that if you are below a certain critical value of L, it is the connected entropy which is lower. If you're above, it is a disconnected entropy which is lower, and that is supposed to mimic a confinement to deconfinement transition. Okay, I think that's more than enough of physics context that I can say or afford to say. And now comes what in the remaining, good Lord, 10 minus some minutes. Okay, so I think I would heavily lean on the quick intro which had been given by Lara yesterday. And all I'm going to say is this, that so in general, if you got G-structure torsion classes, you'd actually, in the context of, let's say, 6 folds, you're talking about the non-Calabi-Yawness of your manifold. And in the, let's say in the context of 7 folds, if you talk about G2 structure torsion classes, you're talking about the non-G2 holonomy-ness, to coin yet another word, of your 7-fold. Okay, so I think, yeah, I just wanted to point this out that the literature, if you do a wiki search in the math literature, so we know that there is a wiki page maintained by Urs Schreiber, NLab, now NCAT Lab. So this is some a screenshot of some of the papers having to do with the G structure and in fact even generalized complex geometry, which by the way we don't use. And in the context of G structures relevant to M-theory duals of thermal QCD, that's our paper at the bottom. And apparently ours is the only one out there. Okay, so it is a well-known problem that there is no existing classification of non-Kähler geometries. You can look up a nice paper by Magdalena Larfors. There are attempts which have been there in some specific contexts by the Berlin group of Dieter Lewis and friends and Mariana Grana and so forth. But in general, it's a difficult problem, probably an unsolved problem. So what we wanted to do was to at least try and look for a classification of SU3, G2, spin 7, and spin 4 structures relevant to non-SUSY string theoretic duals or larger thermal QCD-like theories and their M3 uplifts. Okay, that is what we wanted to do. And this is the first step in that direction by looking at the order out of the 4th corrections. Okay, so okay, there's a way. I mean, there are ways you can motivate these torsion classes. I think I'll just mention the spin 7 because there is a cute little identity which talks about the existence of spin 7 folds given by Ivanov, and based on a little modification of the arguments mentioned earlier, you can actually show that each of these 3 terms is actually trivial. So it points out that the existence of a spin 7 structure, we actually work it out. So though it's going to eat into my time, I just wanted to mention something which when we found, which when I came across, it was very surprising. So there are these nice, there's an appendix of the written by Umemura in these very old Dave Mumford lectures, Tata lectures. And that's where he talks about, Umemura talks about writing solutions to polynomial equations, roots of the polynomial equations in terms of what can be called as Siegel theta functions. So it turns out that obviously, if you want to work out the coefficients, you'll be required to diagonalize the metric. It turns out that you will have to eventually, in the psi equal to 2n pi quadrant patch, you'll need to actually solve a quintic. And so this is one of the roots. It's not amenable to calculations. There's another result by Zivkov, which says that instead of working with genus 3, you can actually work with genus 2 and their derivatives. But that is also not amenable, largely because the period integrals are not very easy to calculate. And that's okay. That's where I came across this amazing book written by I don't know, it's Bruce King. I don't remember. It's called Beyond the Quadratic Equation. The cool thing is that this is a book written by.
You have 5 minutes.
I have 5 minutes. Yeah, I've got a stopwatch running right next to me. Thanks, anyways. So this guy is a chemist. Yeah. So he actually discusses what is called as the Kiefert's algorithm. So I'm not going to go into it what it is, but the long and short is this is what we use, and it's a beautiful algorithm. Now, okay, so this is SU3 structure torsion classes. Now, remember, I had made a statement about these. There are 5 SU3 structure torsion classes, and roughly what we see is that we know that for Calabi-Yau, the J and the omega are close, but when they are not, that's where the information about the non-Calabi-Yauness is encoded. It turns out in 5 torsion classes. The 4th being proportional to 5 is roughly can be alternatively understood that even though we're dealing with non-compact geometries, but if you were to look at a little locally, the GKP geometries, we know that IST is it is an essential condition required for SUSY. So it turns out that the deviation from ISD condition is a resolution parameter to the fourth suppressed. So the SUSY is very quote unquote mildly broken. Just wanted to make that remark. And similarly, when you talk about G2 structure torsion classes, we talk about these positive 3 form phi, which is going to be closed and co-closed. If it isn't, if it were, it's G2 holonomy. If it isn't, you have G2 structure. Okay, spin 7. Okay, so I think I come to the summary of my talk, which is essentially this table, which is the same proposition put in a table. Yeah. And so we looked at the SU3 structure torsion classes for the 6-fold, the G2 structure for the 7-fold, the SU4 and spin 7 torsion classes for the 8-fold. And yeah, I mean, so for example, for the SU3 torsion classes, what we ended up with is sometimes what is referred to is some cousin of a conformal collabia. I'm not sure there are specific names given to the others. I'm not familiar with them. For some future directions. So I'm sorry, apologies to mathematicians, especially Japanese mathematicians and other mathematicians like Huo and for Sasaki. So there is a very nice connection between G2 structures and almost contact structures. Okay, so the idea is that if you have a closed or a non-closed 7-fold Y with the G2 structure equipped with a positive form var phi, then you can actually associate an ACMS with it. And so there is an endomorphism, which is actually given by the interior product of a globally defined vector with the same positive 3 form. And you can talk about there was a talk in this conference in the context of thermodynamics, though, in classical mechanics, but this is in the context of getting it from G2 structures. And then, I mean, one of the things that we want to do is actually look at a classification of almost contact, almost contact 3 structures, contact 3 structures, and associated SU2 structures in here. And also there is a way of talking about, this is something which we are exploring, about reducing the G2 structure to SU3 structures. Okay, so with that, I conclude. I think I'm within time. Thank you.
Okay, thank you, Aalok. Okay, any question?
Somdat, I think, raised his hand.
Yeah, Somdat.
Yeah, so could you go back to your action for the M theory, the slide on which you have the action for the M theory?
Can you see it?
Yeah.
Yeah.
So yeah. So the understanding is that when you compactify on some 7-dimensional manifold, you get the QCD action, right? That's the understanding, right?
That'll be too ambitious, but I mean, this is the supergravity, the bulk part probably, yeah, because remember that, I mean, yeah, I mean, it is too ambitious a statement. I would hesitate.
My question is, what do you mean by the M theory lift of QCD? What exactly do you mean by that in the context of this action?
Yeah, okay. So here's the story. So remember, let's go back to this flow chart with your permission. Oh, without. So which is this, that, so the starting point of the story is a 10-dimensional theory, whatever that is, yeah. It turns out that this theory is defined in 10 dimensions, and it is what is referred to as type 2B theory. Now, remember I showed something which I call as an MQGP limit, which is spelled over here. I have no idea how to highlight, good Lord. So you realize here that I made a statement. I hope you recall that I made a statement that the string coupling is not small. Now, when the string coupling is not small, strictly speaking, you better address the background from an M theory perspective. Now, the question therefore is, how does one go from the type 2B 10-dimensional background to M theory? Okay, so that process of going from 10 to 11 is an uplift. But I mean, this, though you didn't ask, I'm just putting it as a one-line addendum, is actually this uplift is actually a 2-step process. First, you go from B to A, type 2B to type 2A, and then there is a direct prescription given by Witten of uplifting that type 2A to M. So that's the uplift.
Okay, fine. Now how do you get the QCD action? That's what I'm concerned about.
Okay, so yeah, sure. So let me take you to something which I had not shown, which is in the context of 𝗦𝗊𝗶𝗶. Okay, so the chiral perturbation theory action is of course not QCD action. It is by itself an effective theory, but what we ventured to try was to actually get that action, if you wish, starting from M theory. Okay, so I don't know if I can get to that slide, but while I'm trying to, let me just speak anyways. So the idea is that you have an effective theory, which is the Gas-Alloy-Wheeler theory. Here we go. So you realize that this is an action which is an order p to the fourth action. The order p squared action, it turns out that there are only even powers, which you can easily argue just by simple power counting due to Weinberg. It turns out that the leading order term is essentially more or less, there is a universal term, which is essentially, if you wish, a nonlinear sigma model, along with a mass term if you want to break chiral symmetry. And in the chiral limit, these are the only terms that you can get. Now, the question is, can we reproduce these terms from M theory? Okay, so what we do there in that context is actually look at the reduction from the M theory, which we had gotten with the inclusion of order out of the fourth, and brought it down to type 2A, and looked at the so-called the flavor dBi action for the flavor D6 branes, and performed actually an expansion using what is called as a hidden local symmetry formalism of some of these groups by Harada, Yamawaki, and so forth. So that's how you make contact with QCD.
Okay, good.
Okay, let us thank Aalok for a nice talk.
Thank you.
And so this is the end of this session, and there will be a discussion session right after this. So Aalok will take care of that.
Oh, no. Sandeep is going to take care of that.
Okay, that's fine. But feel free to do it, Aalok, or at least
no. Please.
Part of it.
No, please. No.
Okay, as you like.
Up.
As you like. No. Okay, well, so thanks a lot, Aalok, and thanks, Shivaji. And so we move on to the discussion session. We're running about 15 minutes late. We have Davide Gaiotto's talk after the discussion session. And the other thing to say is what we'll do is we have planned a group photo since we are coming to the end of this conference after the discussion session, before the last session where Davide will speak. So please do stay for that group photo, which should be about half an hour from now. We'll be a little late starting Davide's talk. I hope that's okay with Davide and all of you. But we hope to get going about 6:45 for that then. So let's get going. I hope many of the speakers are here. I know some of them are not here, but I know that Joao and Enrico are not here. I hope many of the others, no one else wrote to me, so I assume that they're all here. And please turn on your mics and also videos if you can. And the floor is open. We have a very informal discussion here lined up. So go ahead, ask your questions, and let's have a good discussion. It'll be for half an hour, and we'll have to close after that, but maybe enough for you to at least strike up an initial conversation, which you can take forward later. Okay. Anyone who didn't get a chance to ask their questions, would like to make comments, please go ahead. I'm going to look at the hands being raised anywhere. No hands being raised. Everyone's a little tired, maybe. Okay, here we go. There is a hand. Shomdat. Okay, go ahead, Shomdat.
I have a question for Ronak. So, is he there?
Yeah, hi.
Are you there? Okay.
Yeah, I'm here. Thanks.
Yeah. So, what is the final state of the de Sitter universe? If the final state is R equal to 0 manifold, if the final state is an R equal to 0 manifold, isn't the de Sitter just undergoing a big crunch or something?
No, sorry, the final state of the de Sitter is actually an R equal to infinity region. So it's like an asymptotic region. And actually Enrico was really working with that region of de Sitter, for example. The R equals 0 region is off to the side. It's not in the future or the past. It's in the space-like ends. So it's like you should really think of it as, if I may share a whiteboard, like de Sitter really looks like this. This is a hyperboloid, and each spatial slice looks like a little circle, and the circle grows with time. This thing is kind of, in an obscure fashion, converted into that Penrose diagram. So the final state is that.
But in the Penrose diagram on the left, you had R equal to 0, right?
Yeah. So the point is that.
What does that mean?
So these two lines. Where is there it is there. So yeah, let me just draw the lines. Yeah. So these two lines are R equals to 0. Okay.
Yeah.
And broadly speaking, you should think of those two lines as these two lines. Okay. And yeah. So it's on the side. It's not in the future.
I don't understand what you mean by that, because I would guess that R equals 0 means that the space manifold is just going to 0, right?
Yeah. So here you should think of the spatial manifold as an S0, which is 2 points. So what is R here? R here is really the kind of distance between this point and this point. So this is a DS2 I'm drawing. Okay. And in DS3, there will be a circle here, but in DS2, this is S0. S0 is 2 points. So the R is the distance between, this is kind of like R, and R equals 0 is when these 2 points hit each other out here.
Hello.
Yeah,
Anyway.
go ahead. Amitabh, do you want to ask something?
No, actually, I have just a random comment for Ronak. He in one of his last slides, you said something about higher dimensions and black holes in de Sitter. So I mean, and you were saying that it's important that you should be able to make a distinction between the cosmological horizon and the event horizon. Otherwise, you would not know to which one you are going to under this deformation. I wanted to say that actually this distinction blurs when you are in sufficiently high dimensions and you have rotation. The cosmological horizon can touch the event horizon.
Yeah.
So it's not clear how.
I agree. Yeah. So certainly, and this is also the question. Even in 4 dimensions without rotation, if you're in the exterior of both the cosmological and the event horizon, there is a certain level of ambiguity where it's not always clear which is which. And so this is why I said that you expect the ADS black hole horizon to sometimes be the cosmological horizon, sometimes be the black hole horizon, and it will depend on quote unquote mood, where we don't know what mood means. Mood presumably means something precise. And yeah, I agree completely. This is the distinction is not very well defined, and this is why there is a question here. Thanks. Yeah.
Okay, anybody else wants to ask a question to any one of the speakers?
Hi, Sandeep.
Yes, Abhijit, please.
If Sandeepan is around, I would like to ask him a question.
Okay, let's hope so. Sandeepan, are you there, please? Maybe it's getting on. I had requested everyone to stay on, but I'm not sure if timings could work.
Yeah, I think for him, the time doesn't work.
Yeah. Do you want to ask your question anyway, and we can see if someone else wants to take it up, or you?
Sure.
Yeah.
So Sandeepan talked about this out of time ordered correlation function, and he introduced this notion of extremal chaos, where all the chaos inequalities were saturated, and the function took the form, the correlation, the out of time order correlation point took the form that it dipped, and that dip was governed by the MSS bound, the saturated MSS bound, and it came up again and stayed constant asymptotically in time. So I just wanted to understand what this means, that it stays, comes back to 1 and stays constant all the way to infinity.
I see. I see. I don't know if anyone has a comment to offer, or
Yeah,
Arnab has something to say. I'm sorry, I may not see all the hands. Just speak up. It's not a very formal thing. Anyone would like to comment on that, or I'm not sure. Yeah, I don't see anyone.
Okay.
Sorry.
It's
Yeah.
I might be wrong on this point, but based on this paper by Phil Sard, where he studied it in JT gravity, this constant region is what's called the plateau, and basically it's given by a sort of coherent state of arbitrary number of some branes that they don't define, and so it's some extremely non-perturbative thing. I think in their matrix model it was doubly non-perturbative.
Wait, were you talking, what correlation function were you talking about, Abhijit?
I was talking about the standard out of time order correlator that Mardasina Stanford Shankar studied.
That's sort of what I thought. I see.
Yeah.
I know. I know of the plateau regions for correlators of the partition functions.
Yeah, that's this spectral form factor or something, right?
Yeah.
Is that what you were referring to, Ronak?
So this a very similar calculation actually calculates OTOX as well.
I see.
So basically, they have to convert. When you take two partition functions into Lorentzian time, you can just put two operators at the top and two operators at the bottom to break time reversal, and this gives you an OTOC actually.
But there, when it comes up, it does not come all the way up to 1, right? It just stays very because it's usually displayed on the logarithmic scale, and it's much less than the initial value.
Yes.
But in his calculation, it somehow went to 1, and then he defined the spectral presentation, and it seemed like even if you use any density, this property should be universal for any sort of spectral representation. So it seemed like a universal property. That's why I wanted to understand what it means and so on.
I see. Yeah.
Hi, Abhijit. Can I make a very
Arnab, go ahead. Sorry.
Sorry. I mean, I don't really have anything very specific to say. I'm not sure if what I'm going to say is actually either correct, but nonetheless, I mean, I think in some sense, you know, what seems to be expect, of course, these correlators to start from somewhere, have a non-trivial dynamics, and then decay to 0 and stay 0 forever. I mean, that's the usual story. But what Sandeepan seems to be suggesting is something similar to what would happen if you could access, let's say, the Poincare recurrence time, because then the system would again, you know, reproduce, go back to your initial state, and you could actually collect everything. So to me, it sort of looked like that. But I'm also very confused by it because the time scale at which it happens is slightly after the scrambling time, which is again not what you would normally expect it to see. I mean, right? I mean, it's like doubly exponentially large. So I'm not really sure what to make of the fact that it actually goes back all the way up to, you know, where it started from. In fact, I'm also not sure even if it did not go all the way up to the starting point, even if it were staying somewhere non-zero and staying flat for forever essentially, I would not quite know how to interpret that either. But I mean, anyway, it's just a comment, and maybe Sandeepan, if he was around.
The scrambling time is a lot shorter than the Poincare recurrence.
Yeah. Of course.
That's I see. And it was going back up, you say, on that kind of time scale.
Yes, it's going back up. I mean, for example, it's going back up even much before the Heisenberg time, which is what you could access otherwise, right? Heisenberg time is when you would start to see all this deep ramp plateau kind of structure happening.
No,
So,
but actually, Sandeepan had a flexible parameter. I mean, it was just a solution to some constraints that he had.
Right.
It was parameterized by a solution which looked like that. But the scale at which this happens is something that he could control.
Correct.
It was just a parameter in his solution.
Correct.
So
correct.
one could get around what you are saying by saying that that tau effective or whatever scale is very, very far, right?
Yeah.
So in that sense, you could push it very far off into time. But nevertheless, what was definitive was the coming up at one part.
Yeah. I mean, my confusion is that you have no a priori way of saying that this parameter need to be tuned so that it has to be pushed very far, right? I mean, you could also have it happening right at the scrambling time scale, which would be very confusing because, well, at least, I mean, okay, to be honest though, I mean, in that treatment, there's a small parameter which is not quite specified. So it kind of depends on what that small parameter really is physically. So for example, when we do this calculation in CFT, large C or whatever in holography, etc., we always stop at the first order. We don't even begin to see what Sandeepan was describing because we don't have a small parameter on top of it. So maybe if we have a small parameter, which is, in some sense controllable, and then on top of that can do this kind of calculation, then maybe it's natural for some reason. So for example, one thing that I had mentioned, although this connection is not really as sharp as probably one would like, but nonetheless, there's a similarity in the sense that if you have these 2D CFTs and if you do this, strip calculation with some inhomogeneity in the boundary, etc., some by hand introduce small parameter in the system, then actually you could design that perturbation in such a way that all at least some of the subleading constraints that Sandeepan was describing could be saturated. So this curve going back up would need a resummation of all of those. But I'm just saying that it may not be completely exotic or out of completely crazy to think about such a situation where you have a small parameter. But I do not know of a good example of a small parameter. The thing that confuses me a lot, not confuses, but I don't quite know how to do it, is because having weakly coupled theories is not really good. I mean, weak coupling is not going to give you this. So this is something else. And yeah, I don't, as I said, I don't have anything sharp to say, and probably Sandeepan could have clarified this.
Sorry, one comment about this: the computations that Stanford and company did, Stanford and Schenker and company, in the Iconol approximation, don't show this.
Sorry,
do not.
Yeah.
It just, the way it goes is that it's like 1/1 plus exponential growth, their answer, with a small parameter behind, G Newton behind. So if you expand that in a Taylor series expansion in G Newton, you get 1 minus G Newton times exponential growth.
Yeah.
And but if you look at the whole function, it's 1/1 plus G times exponential growth, just decays forever. In Iconol approximation.
Okay.
So that is right. That is right. So 1/n expansion. Any result in large n theory in a 1/n expansion will not probably give you this. Will not make the OTOC rise again.
No, this is not 1/n expansion. This is just large Iconol approximation at large times.
Yeah.
Looks like the function is just decaying.
I guess, yeah.
No, but it's also large n, right?
It's G Newton. I guess you meant in 1/, there's a G Newton suppression there to that term.
Yes.
Okay, right.
It's also a large n result.
Okay, let's see. Anyone else who hasn't asked anything yet on any other speakers, or even for someone? Let me see. We are going to do the following, if you don't mind. Davide's talk has already been pushed 15 minutes. So we'll close at 6:40 and have a group photograph. That will take about few minutes to organize and so on. And then we move sort of at 6:45 at least onto Davide's talk, so we don't push it by more than 15 minutes. Okay. So but we have to keep ourselves entertained. I'm not letting you guys go before that, for one thing, simply because all of your photos are most important. So let's see.
I have a question for Siddharth.
Okay, go ahead. Ask your question, and Shomdat has another. Ask it. Go ahead, please, Amitabh.
Yeah, no, actually, I have already clarified this, but just to discuss this, I have clarified this with Siddharth on chat, but just to discuss in the.
Please.
Yeah.
We can all benefit. Yeah.
Yeah. So you showed this symplectic 2 form, and you said this is a proposal for your symplectic 2 form. So can you comment on that? How it relates, how it comes from the Lee-Wald symplectic form and things like this?
Right. So I said it's a proposal because we motivated it by calculating the charges from the Bondi mass solution equation, and it matches with those charges. If you were to compute it from the bulk, if you were to compute it using a bulk symplectic form and a Cauchy slice and pushing that to null infinity, then we see that this redefinition of ours, together with our fall-off conditions and so on, they take care of most of the terms that come in this computation. But we have still not taken care of one class of divergences that come up, which are really just which come up because of these CABs. So since the CAB, which is the which is U independent, there are some terms in that bulk symplectic form which are just pure functions of those CABs, and those being U independent, once you integrate over U, they give you some divergence. So that's the reason I didn't talk about deriving it from the bulk.
Yeah.
So but I do think that we'll probably be able to cure those divergences by some renormalization of the procedure.
Yeah. I mean, as I was telling you on the chat, recently there have been many papers, and you know very well, recently there have been many papers on this renormalization of the symplectic 2 form. And perhaps those things can be used to fix this divergence.
Absolutely. So there was this paper recently that talked about doing about implementing holographic renormalization for asymptotically flat spacetimes, and they have a procedure they claim which will enable one to write down finite symplectic forms for asymptotically flat spacetimes, and they carry through their procedure for d equal to 4. So my guess is that if one were to do that for higher dimensions, then one would be able to solve this issue.
Yeah, thanks.
Thanks for the question.
I have a question for Siddharth.
Go ahead, show him that.
For d equals 4, yeah, I thought there was some kind of vanishing of some coefficient, right, in the equation for the CABs. Is that correct?
Right.
Yeah. So is that the reason that the straightforward analysis in d equals 4 is not easy or something?
No, but
or,
yeah. No. So
because you did it for d equals 6. So
right.
That was what I was wondering about. Why you didn't do it for d equals 4?
Right. So the point was that so in d equals 4, CAB was playing 2 roles. So the U derivative of CAB gives you the Nu's tensor, and that was giving you the flux of gravitational radiation. And it was also in CAB in any dimensions gives you the soft charge, because it's symplectically paired with the operator that gives you the soft charge. So what is happening was that this vanishing that I showed, which if you looked at the AB component, the Einstein equation, there's a d-4 that comes out, and then you get a del U CAB. But that itself is not special to 4 dimensions, because in any dimension there is a particular CAB, the one which corresponds to the radiative fall-off, whose U derivative is not fixed. So for 4 dimensions, it happens to be the same CAB that gave you the soft charge. And so that is a coincidence in some sense, that in 4 dimensions, both these fields are the same. But the fact that something del U, you have a particular del U of some particular CAB vanishing, that is true in any dimension. And in any dimension, there is one particular CAB that does that, which, as I was saying, is the one that gives you the radiation.
So the coefficient multiplying the del U CAB, that entire term vanishing doesn't create any problems.
No, that doesn't create any problems. And in fact, we need that, because if it didn't vanish, then we would be in trouble, because then you would not have then we would be wondering where radiation is coming from at all.
Okay.
Okay, very nice. I think let's wrap up the discussion just a little bit early so we can move to our photo. Now, what I'm going to request is all of you, before we do that, because it's Friday evening, we have a very important last session coming up, and you all, I am sure, are waiting like I am for Davide's talk. But just before that, let's do 2 things, if you don't mind. We'll thank everyone after Davide's talk. But let's do that because a few people might be wandering off or whatever. So what I want to do is just thank on all of our behalf the organizers now, and we come back and thank them again formally at the end, but some of them are filtering off. So I thought let's do that. So please, all of you, just open up your videos and let's thank the organizers. And after that, let's take a group photo. And then let's move to the talk. Okay, so first of all, join me in a huge round of applause for all the organizers, please. Thank you. I want to thank especially Aalok Misra for really being the helmsman of this whole meeting, the National Organizing Committee for all the work you all did, and the choice of excellent speakers, all the speakers, the audience, which is most important, especially online, to keep your attention and ask your questions, etc. And all the organizers in Roorkee, the AV team, and especially I want to thank 3 students. I hope they are here. Please turn on your videos. Mohak, Lucky, and Shubham, are you there, please? I can't see who is who, but I hope you're there. And a special thank you to you all from all of us. Aalok has told me how much you have done, and we are all grateful to you for having worked day and night and made this conference such a big success. So thanks again, Aalok, your whole team, and everyone for a wonderful, wonderful meeting. I'm now going to hand over to Aalok to organize the group photo. Aalok, are you there?
Yes, thanks. Thank you so much, Sandeep. With your permission, I just wanted to thank one particular individual. Can I, with your kind permission?
Yes, of course. I'm sorry.
So I would put it this way, that if any one of us ever thinks of having an NOC, you need to have one man on that team, and that person is Sunil Mukhi.
Okay.
And I'm so grateful to Sunil. I really have no words. I mean, there are so many things that I have been asking him. I don't know what they call it, offline, online, everything is online, but I mean, and he has been so precise, so prompt, and so objective about everything. I mean, I'm so grateful, Sunil. Thank you so much. Really appreciate it.
Sunil, come on video. I can't see you.
He is.
Here he is. Okay. All right. Congratulations. Thank you, Sunil. I mean, I think we all know that what Aalok has said is absolutely true.
Everyone pitched in. I think I don't think I really did much. Alok took all the stress, and his team, I think, did everything. So
no, I'm sure you did a lot. Thank you. Thank you very much. Aalok, also please thank IIT Roorkee administration from all of us for allowing us the use of all the facilities and the beautiful backdrop, which we hope to visit in person.
Yes.
Looks like the White House, as you said, but I think it's more impressive.
That's what students call it.
Looks much more impressive. Okay.
So
all
I
right.
think can I take that group picture? It's going to
be
there are,
and then we'll move on.
Okay. So there are 3 screens that I see. So I'm going to do it So this is 1. I do see some who would still turn off their cameras. Maybe if possible, they could kindly turn it on. Maybe not. Okay. That's screen 2. And then the final screen 3. Again, I request maybe can we all turn on our cameras? Really appreciate that. Just a moment. Sorry. Just a moment, please. Yes, we're all done. Thank you so much. Thank you.
Thank you, Aalok. Thank you very much. So, Aalok, is it okay if we move on to
Absolutely.
Davide's talk now?
Please. Yeah. Sorry,
Okay.
Davide. Apologize. Sorry.
Yeah, Davide, are you here? Okay, here he is. Well, it's a great pleasure to welcome Davide to this session. And Davide, you will give the grand finale talk. So thank you very much and go ahead.
Thank you very much for the opportunity to speak. I would like to review, in general, some of the things that have been done in the subject of twisted holography. And in particular, I will try to discuss in detail a nice example that I've worked out with my student, Kaja Budzik. But the part of the work that I'm going to describe that I did was done in collaboration with Kaja and with Kevin Costello. Okay, so twisted holography. I use this term twisted holography to denote a general program based on the idea that a lot of the examples of holography that you know involve supersymmetric quantum field theories, and the supersymmetric quantum field theories admit twists, which are ways to sort of separate out a consistent subsector, a protected subsector. And so in principle, it should be possible to match precisely a given subsector of a quantum field theory with a protected subsector of the holographic dual theory. And of course, this is something that has been done from the very beginning of holography, because typically protected subsectors are the only places we can do calculations. But the element which is novel in twisted holography is that you try to use this technology developed by people like Costello and his collaborators to really write down a self-contained twisted theory which captures the whole protected sector in the form of his own sort of quantum field theory. So you try to define a simplified quantum field theory which captures only the protected subsector, and to match it with an actual simplified version of the theory of supergravity. And so this offers novel perspectives on all calculations, but also allows you to do new calculations. I should also say that this subject has some very interesting resonance with the sort of topic that Professor Gopakumar described on Monday, in the sense that a lot of the calculations done in the context of on the quantum field theory side of twisted holography involve essentially free correlation functions, because in these protected subsectors, the coupling is essentially turned off. And so, but on the other hand, as I said, you get sort of full toy models of holography where these free protected calculations are dual to actual holographic setups. And so it must be possible to extract these holographic dual geometries just by staring hard enough at free correlation functions. Essentially, in general, in the twisted holographic setup, things like the Hooft coupling drop out, and all you're left is sort of the combinatorics of the large N. So on the gravitational side, there is a 1/n expansion, and that matches something that could be the Hooft expansion in the gauge theory in sort of string theory examples, or something more complicated in M theory examples. So what does it mean twisting a theory concretely? So this is something you can do whenever your supersymmetric quantum field theory admits an nilpotent supercharge. So you just need one of the supercharges squared to 0. This is often possible, not always. For example, if you have 3D n equal 1 supersymmetry. It's not possible to find an important supercharge, but most quantum field theories admit, supersymmetric quantum field theories admit such a supercharge. And then you take the supercharge and you add it to the BRST differential for your theory, which essentially means that you're passing to the cohomology of the supercharge. And that's what simplifies the theory. And essentially you just process the whole theory with this new BRST differential using the formalism, and you can do simplifications because you can add and remove few exact terms and things like that, and at the end you get sort of simplified, consistent quantum field theory. The resulting quantum field theory is typically topological or holomorphic, in the sense that when you pass the topology of supercharge, all the translations which are in the image of the supercharge become exact. So you lose those translation generators, the correlation functions, the theory becomes independent of those translation generators. Correspondingly, you lose some components of the stress tensor that become exact. And so your theory will not depend on the full metric on the space-time, but only on some parts of the metric. And so in some situations, this might be enough to just remove completely the metric dependence, in which case your resulting theory is topological. But in a lot of situations, it sort of keeps only the complex structure. So most of the twists that you have available in situations of low supersymmetry, for example, are holomorphic twists. And I have to say, to open a parenthesis, holomorphic twists have not been studied much in the physics literature. But I think they are potentially interesting. For example, holomorphic twists are available in 4D n equal 1 gauge theories, where we don't have topological twists. And I think it would really be nice to know if these twists can really tell us anything about the physics of these low supersymmetry quantum field theories. Again, in an holographic context, this is sort of related to efforts of studying things like 16 PPS states in equal 4 supermills. There have been several efforts in the past to sort of understand this minimally protected subsector of an equal 4 supermills and match it to holographic calculations, sometimes with quite some success. And this sort of thing can be sort of encapsulated self-consistently in a twisted holographic calculation. Now, another thing I should mention, right? So sometimes you can do something like omega deformation, which also reduces the number of dimensions of space-time. So, for example, you could take a 4-dimensional theory, but extract a 2-dimensional protected subsector. So this is the best understood part of the process. As I was saying, these manipulations of the quantum field theory should be something that you can match on the supergravity side. And so it should be possible to match these twist of the supersymmetric quantum field theories to some protected subsector of supergravity, something you could call twisted supergravity or twisted superstring or twisted M theory. So Costello has conjectured a variety of descriptions of possible twisted supergravity theories. And so this gives you a way to propose possible holographic duals. Although the analysis is not quite finished at the moment, there is sort of a lack of a precise prescription to take a supergravity solution and map it to a twisted supergravity solution. And I think understanding how to do that will be really useful to progress in various directions. And take this as an invitation to people who know supergravity very well and BPS configurations of supergravity to perhaps give a look at the twisted holography setup and trying to figure out how to integrate this knowledge with the twisted supergravity approach of Costello. So in my talk, I will discuss a couple of examples. But yes.
So why does the usual method fail for supergravity, like considering a certain supercharge and setting it to, by twisting it and setting it to 0, why does it fail for supergravity?
Oh, well, so
you're saying that supergravity.
Mm-hmm. So on the supergravity side, you do something similar to slightly different. So on the supergravity side, the supersymmetry is not global. It's a gauge symmetry. So you cannot just say, okay, take the supercharged and added to the BRST differential. You can do something, so Costello's perspective, instead you can do something that is a bit unusual physically, but seems to work, which is to give an expectation value to a bosonic ghost, which essentially has the same effect on the BRST charge of the theory. And then you do perturbative calculations around this new background. But yeah, so for example, I don't know, when you do certain twists of type 2b string theory, the result is the B model, BCUV theory in 3 complex dimensions. So in principle, you're studying essentially Calabi-Yau geometries in 3 dimensions. What would be nice to be able to do would be to take an actual supergravity solution like LLM and extract from it a Calabi-Yau geometry to be used in twisted supergravity, twisted holography. And it's actually, I've been actually trying to do that for the last month, and it's painful. And I think that somebody who knows supergravity very well could do this sort of translation much better. So this sort of, there is all this literature on the how do you call it, special geometry, where you take your Killing spinner, extract a variety of forms and geometric objects out of it, and you constrain your supergravity solution. That same data should be something that can be translated into the twisted supergravity background. And I think it would be very nice to do so. Anyway, so once you manage to identify both the twisted supersymmetric quantum field theory and the twisted supergravity background, then you get yourself a simplified but self-consistent model of holography, where everything is potentially computable and can be done in a mathematically rigorous way. So it's a setup where you can literally prove an example of holography, a complete example of holography. And as I was mentioning, there's a lot of the calculations in the quantum field theory side are essentially free field theory calculations. This might also give insight on how to extract a geometry from free field theory correlation functions. So how geometry emerges from large and limit independently of the coupling. There have been some nice mathematical work done on this topic. This work is sometimes called holography, or perhaps in a physical language would be more properly called pre-holography, in the sense that it focuses on understanding in detail the effect of the twist on the coupling between the bulk string theory and the Word volume theory of D-branes. Once you understand this coupling in detail, then which is done in flat space essentially, then the presence of the D-brane, of course, back reacts the geometry in some way, and one can follow this back reaction perturbatively and sort of get information in order by order in N, and then use mathematical technology to actually bootstrap this to all orders in N. So you get situations where you can really compute the OPE of various types of OPE, depending on topological or holomorphic setups on the quantum field theory side, and match it with calculations done in the twisted supergravity. Costello worked this out in some beautiful examples in M theory, sort of studying the volume theories of N2s on fibranes and their sort of omega deformed topological twists, and matching them with calculations done in a beautiful, very twisted M theory which is defined by sort of 5-dimensional Chern-Simons theory. And there was also this group of Istiak, Muzarian, and Zhu, which did beautiful calculations involving interfaces in equal force superior meals. But I was saying these derivations focus on the OPE or local operators and work effectively perturbatively in N. not in one order n. It's kind of funny. You're sort of turning on the effect of the d-branes order by order in n. And the reason this can be sort of made sense of in the large n limit is that these OPEs are often polynomial in n. And so you can study a polynomial starting from the leading coefficient or from the first coefficient, and it works both ways. In the sort of work that I did with Costello and with Kaja, I was trying to study situations where instead working with a non-perturbative back reaction really matters, so that you have a full, you're studying a fully back-reacted setup. So you really have the analog of ADS 5 times S5, say, matching the twisted quantum field theory calculations. And so that's what I'm going to discuss next. Any questions before I get there?
I was just wondering whether you can take the zero mode of the supercharge operator for supergravity and consider the twisting or something like that, because the zero mode would be some charge, right? I mean, it would be because the local supercharge, you can always make an expansion in terms of the moments which would each correspond to some version of supersymmetry, and maybe the zero mode can be considered as a global charge. Global supercharge, right?
I'm not sure. I mean, clearly in a holographic situation, there is a supercharge, a sort of a global supercharge, because of the local gauge symmetry in the bulk. It's restricted to the boundary. But I'm not sure it would have the same effect. Also, in holographic language, I think that in an holographic language, adding the BRST charge, the supersymmetric charge to the BRST charge, really maps to the holographic dictionary to turning on a VEV for the super ghost. But that's all I know at the moment. I'm not sure I can give a good answer. Sorry.
Okay, fine.
Okay, so I'm going to focus for the rest of the talk on a certain subsector of N=4 supermills called the chiral algebra subsector. This was introduced for the N=2 theories by these authors. So for any 4D N=2 theory, you can extract a chiral algebra whose correlation functions capture some of the correlation functions of the 4-dimensional theory, superconformal theory. In this original work, this subset was introduced as a cohomology of a peculiar combination of supercharges and superconformal charges, but it's possible to reformulate it as the result of an omega-deformed holomorphic topological twist, which sort of puts it more clearly within the twisted holography setup. Concretely, what are you doing? You take 4 of the scalar fields on N=4 supermills. I denote them as pi plus minus plus minus. You restrict them to live on a plane, but you also take position-dependent linear combination of these scalar fields in such a way that their green function becomes holomorphic. Essentially, once you put the operators on the plane, the green function becomes something like 1 over absolute value of z squared. And if you take position linear combinations, which depends on z bar, in such a way that you get a z bar at the numerator, you end up with a correlation function that looks like 1 over z in the free theory. But the magical thing is that this is then not affected by coupling. So this chiral algebra subsector has a correlation function that can be computed in the free theory. For the case of N=4 supermills, it looks like a chiral two-dimensional gauge theory coupled to 2 adjoint scalar fields, which behave like a beta gamma system in 2 dimensions, so symplectic bosons. As I said, the correlation functions are computed in the free name. essentially in the free theory, the only effect of the gauge coupling or the gauge interactions is that it gives a certain projection on gauge invariant operators that we'll discuss momentarily. And the holographic dual of this chiral algebra was identified in my work. Well, actually, in a sense, you could say that the dual was proposed in a paper by Dijkgraaf and Wafan, where in the paragraph they proposed that they proposed this chiral algebra, which is they discussed the fact that this chiral algebra appears in the volume of the two branes in the three-dimensional B model, and they suggest that perhaps it could be dual in some sense to the B model under the form conical. So indeed, the proposal is that the chiral algebra subsector is dual to the B model on SL2C, which is the deformed conical. And then the local operators of the chiral algebra coupled to dual to fluctuations of the complex structure of SL2C near the boundary. Now, as I mentioned, the precise dictionary between supersymmetric solutions of type 2B string theory and deformations, Calabi-Yau deformation of SL2C has not been worked out in detail, but it would be very nice to do so. Now, in the gauge theory, you essentially build local operators out of these two fields X and Y, and of the ghost and some BC ghosts with a Beresty charge, which is might be familiar from two-dimensional conformal field theory. Essentially, it's a Beresty charge that makes the current in the Beckhammer system exact. You can compute the cohomology in the large N. You find 4 towers of single trace operators, which are sort of super partners of traces of linear, super symmetrized traces built out of the X and Y fields. And you can develop a precise holographic dictionary, which matches these local operators to specific deformations of the complex structure of the boundary. And so in principle, you can do calculations where you take a 4-point function of these local operators and you try to match them with the B model topological strings in SL2C. By the way, the B model has this nice property that after it's a topological string theory, it is also a local quantum field theory in a sense. So I mean, the string field theory for the B model has a finite collection of fields, and it's called the Kodara-Spencer theory. This is a theory which is not renormalizable in principle, but Costello and Lee shown that it is actually has a unique renormalization if you require it to be coupled to D branes. So calculations can be done in the B model topological string or in this BCOV theory, and essentially do Witten diagrams in SL2C. So with Costello, we proposed, so that one of the key ingredients of defining this, of making this duality work is really to find what are the correct holographic boundary conditions in SL2C, which boundary condition can you put on the BCOV fields in SL2C so that the boundary deformations are precisely dual to the operators of the chiral algebra. So with Costello, we defined the boundary conditions, and we verified that indeed the boundary deformations of the boundary conditions are in one-to-one correspondence with the single trace operators. And also we verified that the leading in N, so both sides of the duality have a very large symmetry algebra and the large N limit, and we match it. And this is enough to show that things like the leading N contribution to the leading N 3-point functions match on the two sides. But it would definitely be nice to push this further and to study in detail the 1/n expansion with correlation functions and match it with the Witten diagrams in SL2C. Or perhaps even better, to find a way to derive the worksheet theory of the B model out of the Hooft expansion of these correlation functions. I think that would be fascinating. in the work with Pajer, we tried to identify a situation where we could study non-perturbative aspects of this correspondence. So, because I mean, ultimately, I think I find fascinating about these crystallography examples is that potentially you can learn things about the saddle expansion, the expansion of semi-classical saddles in gravity or string theory. You can learn non-perturbative information in the sense that if you look at intricate enough configurations on the gauge theory side, you might be able to find situations where on the holographic dual side, you have a sum over different geometries. And then it would be nice to see, you know, which criteria do you use to determine which geometries contribute, what sort of Stokes phenomena are there, and things like that. Now, we are definitely trying to study a situation where there are multiple geometries, but for now with Pajer, we studied the toy model where the geometry is still SH2C, but you have multiple, but you have D branes in the bulk, and there is a sum of different D brane geometries. Sort of, and this is what I would like to discuss in detail for the rest of the talk.
So you don't have some sorts of wormholes or something? No.
Sorry?
In the bulk?
Yes.
You don't have wormholes or things like that in the bulk?
I don't know. Honestly, I don't know. So it would be very nice to figure out which sort of Calabi-Yau geometries appear in the dual of a variety of different correlation functions. There are many things one can do. First, I mean, the most obvious thing is to just insert local operators, which are built of order n square fields, and which can sort of create an actual macroscopic deformation of the geometry near the boundary, and then see how this deformation, you know, is filled in by actual Calabi-Yau geometries. But you know, I think this toy model, I mean, it should be possible to use this toy model for a, you know, to explore a variety of phenomena in holography. Although, to be honest, I never quite know if what has been learned has to do with supergravity or with superstring theory, because of course everything that is computed is independent of the Hooft coupling. So it's possible that some of the phenomena you observe are actually associated to string theory in a strongly curved DS rather than supergravity in a weakly curved DS. It's hard to know. Still, no perturbative information about either string theory or supergravity should be interesting.
And what do you think the corresponding boundary theory would reflect of these wormholes? Something like what matrix models JT gravity duality have uncovered, something like that?
Well, one thing that is kind of interesting is that you can embed all matrix models inside this chiral algebra. So if you look at 2-point functions where you put complicated operators at 0 and at infinity, those 2-point functions are actually computed by a 2-matrix model. So I don't know, and it's possible that you know, some of these toy models of holography can actually be integrated within this twisted holography setup. So I could imagine engineering a 2-matrix model and then pushing it to criticality and seeing what happens in the dual geometry. I'm actually trying to do these sort of things. There can be connections. You know, again, diagraph. You know, so there is the whole literature on various ways to connect the beam model to matrix models, and I think this literature can be filtered past the lens of twisted holography for interesting, you know, to get interesting constructions. So I don't know exactly what is the limit of what can be, you know, what can be accomplished here. You know, the chiral algebra looks simple, but there is a lot of structure in the states that you can insert at each point on the sphere. And most calculations actually, are, so if you set complicated enough states, you can get calculations that are definitely beyond the current matrix model techniques. So you can get multi-matrix models and things like that, which at the moment we don't know how to solve. So, right, in trying to do we've been trying to do calculations involving these operators built out of order and square fields, and right, we're struggling against the limitations of the current matrix model technology. I'm happy to discuss this more in the questions afterwards. But for now, I'm going to restrict myself to operators of size n, which do not deform the geometry, but insert D-branes in the holographic dual. So they tell you, I want to have a D-brane that arrives at the boundary at a collection of points, and then you need to figure out how to fill in the picture. So, right. So the operators that are relevant for this context are called determinant. Call them determinant operators. I call determinant operators. They are what you get if you take a determinant. So they're sort of BPS determinant operators. You take a certain null combination of the scalar fields of the nickel 4 square mills, this n.5. Maybe you add the multiple of the identity, and you take the determinant of that. So you get a certain superposition of polynomials in traces, if you want, but of order n, which depends on this parameter m and on this direction n. And these high-BPS giant gravitons are known or conjectured to be dual to the insertion of a D3 brane of a specific shape near the boundary. This D brane is called a giant graviton. It wraps an S3 inside S5 and looks like a line approaching the boundary in ADS5. This parameter n essentially determines the orientation. It tells you which S3 are you looking at inside S5. And this parameter m tells you the size of this S3. So that when m is equal to 0, you get a maximal S3 inside S5. And when you increase m, the sphere becomes smaller. And my objective is to study the correlation function of multiple determinants and the large n within the chiral algebra subsector. So in the physical theory, the expectation is that, as I'm saying, each determinant insertion tells you that there is a D3 brane arriving at the boundary in a certain way. And then the correlation function should be at large n controlled by, in large Hooft coupling, controlled by a D3 brane wrapping some for manifold in ADS5 times S5, which approaches the boundary in this specified way. And so in the bulk, the calculation should involve essentially open-closed type should be string theory, where you have both closed strings propagating about, but also open strings living on M4 and interacting with the closed strings. And the sort of basic calculation one could do in this setup is to say, I put a trace at some point on the sphere, I put a collection of determinants, and maybe in the large n limit, this will be controlled by a closed string propagating from the boundary to the D brane saddle. The crucial subtlety is that the same boundary conditions on the D branes might result in many different types of saddles. So there might be many different ways of filling in with the D3 brane these asymptotic tubes that are coming in from the boundary. You might have completely disconnected saddles where each tube sort of closes off at some distance from the boundary. You might have partially connected saddle where some tubes connect each other and some close off. And then you could have perhaps this sort of amoeba where all tubes come together and merge. Each of these solutions in the physical theory will have its own action. And the final answer will be a sum over exponential terms dominated by by one of the saddles, and which saddle dominates will depend on the parameters. And as you explore the parameter space, presumably different saddles will kick in and get in and out of the problem. There will be Stokes phenomenon and so on. Of course, in the full physical theory, it's yes.
You're talking about the Green-Schwarz superstring or the 𝗫𝗫-Schwarz superstring?
I'm talking about type should be string theory in DS5 times S5. Pick whatever description you want of the theory.
What I'm concerned about is don't you have problems with the 5 form, the usual problems with the 5 form?
Meaning?
In the ADS5 cross X5 background, you have the 5 form, right?
Yes.
You have a non-trivial 5 form. So usually it's not known how to formulate the string theory on such a background.
Oh no, absolutely. I'm not saying that I will do this calculation. I'm saying, in principle, in the physical holography, this is what one should be doing in order to match large N behavior of determinants. At the moment, I don't think there is any computational technique to compute the correlation function of determinants at strong tooth coupling in the QFT. And as you're saying, there are also, of course, challenges in doing the calculation in this DS5 times S5. I don't know if, but this is right. But all I'm trying to say is that even at the leading order in N, there is this subtlety that there would be multiple saddles on both sides. And a basic holographic conjecture would be that you can, if you could compute the correlation function on the quantum field theory side, you should be able to see saddles which are in one-to-one correspondence to the possible D3 branes, which on the gravity side fill in these tubes. And actually, it would be an interesting question of which of the D3 brane configurations can actually contribute to a given correlation function. Now, as I said, so I'm not going to do this calculation in the full physical theory, of course, that's beyond my abilities, but I can try to take determinants which happen to live in the chiral algebra subsector, and I can try to see what happens in the twisted holography. So essentially, as I was mentioning, right here in the chiral algebra subsector, you pick some linear combinations of four of the scalar fields. You can just put those specific linear combinations inside your determinants. So I'm going to study something like determinant of M plus X plus Vy. So in the chiral algebra subsector, I'll have determinants which depend on now 2 parameters plus the position, so 3 parameters, the position Z, V that controls the linear combination, and M that controls the size. The correlation functions of a collection of determinants are going to be rational functions in Z, just free chiral algebra correlation functions, and they're going to be polynomials in these parameters V and M. But somehow you would like to see that in the large N limit, you get an e to the minus N behavior with multiple saddles, which can have a geometric interpretation. What were the 3 branes in the physical theory should become D2 branes in the B model, essentially things that wrap an holomorphic curve inside a 3-dimensional complex geometry. And these parameters M, Z, and V control some endpoints of these D branes as they approach the boundary infinity in SHC along some C star. And as I say, what I want to do is to really try to match saddles between the quantum field theory and the B model. So I want to find the saddles in the quantum field theory, and I want to match them with holomorphic curves in SHC. And I want the match to be exact, at least in the linear order in N, as a function of this parameter N, Z, and V for each determinant. Now, if we had the full dictionary between twisted holography, between sort of the B model and supergravity, I could then take these saddles in SHC and promote them or lift them to actual saddles in ADS5 times S5. And I think that would be very interesting. At the moment, I don't know how to do so. So the calculation of the quantum theories is done using the free quantum field theory. And luckily, these authors, Giancomas and Vescovi, had just studied the problem of correlation functional determinants in a free theory. For them, the purpose was to sort of use this as a springboard to a full calculation at all values of tooth coupling, perhaps using integrability. In the twisted holograph setup, we can just stop at the first step and take the free field theory calculation and study it. So they have a very nice way to study the problem, the first step is to fermionize the determinants. So you take this determinant of an n by n matrix, you write it as the Grassmann integral, introducing these auxiliary fields, these auxiliary fermions, psi and psi bar, which are sort of n zero-dimensional fermions, such that the path integral of the integral over psi and psi bar reproduces the determinant. So it sort of gives these fermions a quadratic action proportional to m, x, and y. So you can give a physical interpretation to this in terms of the string stretch between the giant gravitons and the original brains. I'm not going to get into that, but it's a very convenient technique, because once you fermionize all of your determinants, then the correlation function of a collection of determinants just becomes a correlation function of a collection of exponentials in the x and y fields, and this is easy to compute. Once you integrate away the x and y fields, you end up with a quartic action for the fermions. It's just you get a finite dimensional integral over sort of k copies of this psi and psi bar, where k is the number of determinants, with an action which is quartic. And then you can apply, the idea is to use the Hubbard-Stratonovich transformation, where you essentially introduce some extra auxiliary fields, a matrix of size k, of bosons, which integrate in a way to make the path integral of the fermion Gaussian. And then you integrate away the fermions, and you end up with just an effective action for this auxiliary field rho. So an effective action for a k by k bosonic matrix rho. Now, this effective action has sort of two terms. One that came out of sort of just the classical correlation function. So you had the quartic term on the fermions and some quartic action for rho, a quadratic action for rho, which depends on the Green's functions of the fields x and y. And then there is an extra term that comes from integrating away the fermions. These fermions coupled to rho with a quadratic action, something like psi bar rho psi. So when you integrate away the fermions, you just get the determinant of rho to the number of fermions, which is n. So you get a one loop term. It's something like the determinant of rho, but to the power of n. And so your action is sort of two terms, both of order n, one classical and one loop. And so you get an on-trip, you can sort of, in the large n limit, you can then study the behavior of this setup by looking at classical saddles for this action for rho. And this was the proposal of Jan Komatsu and Vescovi, that somehow the classical saddles of the action for rho should be identified with essentially the geometric saddles on the holographic dual side. I think in the physical theory, this is a tricky statement, because it's not clear that as you turn on the Hooft coupling, sort of rho will be the correct auxiliary field to add, but it's definitely a very natural statement in the free theory. So before I was understanding what to make, before I move on just a second. Well, okay, I will say it later. So right, so how do the saddle equations look like? In the particular case of the chiral algebra setup, the saddle equations simplify a little bit. The original saddle equation in Jan Komatsu and Vescovi are equations for a matrix, but they're not matrix equations in the sense that they involve operations that are more complicated than multiplication or inversion. But in the chiral algebra setup, there is a very neat simplification, and the saddle equations can be written in this simple form. So let me denote as zeta the diagonal matrix whose entries are the positions of the determinants on the sphere. Let me denote as mu the diagonal matrix whose entries are the orientation of the different giant gravitons. Then the saddle equations become simply the commutator of zeta and rho plus the commutator between mu and rho inverse equals to 0. Intuitively, the rho inverse comes in because when you integrate the fermions, you get this determinant of rho to the power of n. That becomes the exponential of the logarithm of rho. And so when you look right down the subtle equations, the derivative of logarithm of rho is the Roy inverse. Once, if you find a solution, yes.
So when you do the Hubbard-Stratonovich transformation, you would in general get a kinetic term for the rows also, right?
Yes, that's right. So you get the kinetic term for the row.
Yeah,
absolutely.
So you would have. Why doesn't the kinetic term appear in the equation of motion?
Oh, it does. So right. So here. So this moved a little bit. Also, I'm for some reason I dropped the formula. I don't know where it went. But so these are the subtle equations in a general setup. The ones derived by Komatsu and Jan Komatsu and Vescovi. So essentially, they set up rho inverse to be equal to the product element-wise of rho and of the propagator, the Green's function between the linear combinations of fields which appear in two of the determinants. This is what comes from the kinetic term you're mentioning, and this is what comes from integrating away the fermions.
Okay.
In this particular situation of the chiral algebra, this G actually looks like sort of VA minus VB over ZA minus ZB. So I can move the ZA minus ZB to the left, and there was anyway. So you end up with something like a difference of two things multiplying rho AB, and a difference of two things multiplying rho inverse AB, and you can write that as a commutator with diagonal matrices. So this is how the subtle equation here emerges. So there is an important simplification. The equations are hard to study in the general setup, even for free Yang-Mills theory. It would definitely be interesting to study them more in detail because, if you have a proposal for what the holographic dual is of free Yang-Mills theory, then you should be able to match the subtle equations with d-branes in the holographic dual. Absolutely, it would be interesting to understand this more generally. But in the case of the chiral algebra, there is a simplification, which was a key. So you see, when you look at it, when you see equations involves sums of commutators equal to 0, they remind me the sort of equations you find in integrability, like Kitchen equations, which usually come from some kind of a lax matrix. And so with Kaja, we played around a little bit, and we tried to rewrite this equation as the equation for the commutation of two matrices. So we observed that if you build matrices B and C, depending on a spectral parameter A of this form, A mu minus rho and A zeta plus rho inverse, then the subtle equations become equivalent to the statement B and C commute. Another property of these matrices B and C is that the product BC, because there is a rho and rho inverse, has a 1. So you can define a new matrix D so that AD minus BC is equal to 1. Okay, so every time you can find a solution of the subtle equations, you can also find this collection of 3 matrices, B, C, and D. We satisfy this relation. Why is this interesting? Well, because now you can study a spectral problem, find a spectral curve. You can say, okay, for each A, I diagonalize B, C, and D. I can do that because they commute. So I look for a simultaneous eigenvector of B, C, and D. This will have eigenvalues, little b, little c, little d. Is a very A, I get k copies of these eigenvalues. So I'm going to get some kind of a curve as a function of A, as a very A k-sheeted cover of the plane. And because of the relation AD minus BC equal to 1, this curve actually lives in SL2C because its eigenvalues will satisfy a relation AD minus BC is equal to 1. So out of a saddle in the chiral algebra, the quantum field theory, we get the equation for an holomorphic curve in SL2C. And SL2C, remember, was the holographic dual of the chiral algebra. So you get immediately a possible candidate for the holomorphic curve, which describes the various saddles. And so we conjecture that this is indeed the holographic dual curve. and then we check it in various ways. The first check is that it has the correct asymptotic shape as it approaches infinity. So this homomorphic curve really goes to infinity in the form of these tubes with specific orientation. If you're given a solution, a saddle solution, there is a way to study the action of the saddle. Of course, you can write down an action as a function of rho, but even better is to look at the derivative of the action with respect to these parameters m. So it turns out that the m's are the diagonal components of rho, and the conjugate momenta are the diagonal components of rho inverse. So if you understand, so this allows us to get to a geometric interpretation of this and really match the action of in the large n limit of the quantum field theory saddle with the action of the d-brane on the bimodal side. We also study the analog of this problem. We take a closed string insertion, and we really take a propagator going from the insertion to the d-brane and integrate it over the d-brane, and we match the expectation value of a single trace operator in the background of the determinants. And finally, we check the sort of global symmetry algebra identified with Kevin acts properly on both sides in a way that matches. And we did some one-loop checks too. So all in all, I feel really confident that our conjecture is correct and that we found a way to identify the correct d-branes starting from the saddle point equations, the quantum field theory. So what sort of things would be nice to do next? First of all, at the moment, we're not sure that every curve in SL2C can be written as a spectral curve. We proved it for genus 0, but we don't know if it's true in general. So in general, in this holographic setup, it would be nice to know which saddles on the gravitational side actually contribute to the quantum field theory calculation. When you study twisted holography, there is also the extra challenge of figuring out which saddles of the twisted gravity setup can be lifted to saddles of the gravity setup. So both questions are kind of interesting, and it's not obvious that all saddles. So this means that it's not obvious that all saddles on the bimodal side contribute to the correlation function. So it would be nice to know if that's the case. Yes.
So the holomorphic curves usually usually correspond to some genus G Riemann surfaces, right?
Yes. Yes.
So what bearing does that have here?
So the short answer is I do not know. So at the moment, for when the surfaces of genus 0, we can show that every surface of genus 0 in SL2C is the spectral curve for some rho. At the moment, I do not know if that's true for curves of general genus. I think a spectral curve can have genus different from 0, but we don't have many explicit examples of solutions for rho. So again, I'm not sure. I would like to understand this better. It would be nice to match the 1/n corrections to these statements. In principle, so this is mathematically rigorous on both sides. It should be possible to really prove that the large n expansion, the 1/n expansion around the saddle on the quantum field theory side matches the BCOV theory in the presence of a d-brane on the bimodal side. I should say that, by the way, the the 1/n expansion around the saddles, lives in the general umbrella of the Hooft expansion, but it's not the standard Hooft expansion. So I would like to understand a little bit better how things work. So if you do the standard Hooft expansion of the correlation function, what you land on is sort of this saddle where all the d-branes are disconnected. And this procedure of integrating in auxiliary fields and looking at the saddle of rho somehow allows you to explore other saddles, but I don't fully understand the Hooft expansion, how the Hooft expansion works in that context. I think it would be nice to understand it a bit better. Another point is that this is just one of the examples of twisted holography. There are a lot of ordinary true theories which have holographic duals, and they have chiral algebras too. And one can study, this gives rise to a variety of extensions of the setup I discussed in this talk. And then there are the other twisted holograph examples involving M theory and whatnot. And for all of those examples, you can study determinants and the corresponding d-branes. Yes?
Oh, hi, Davide. Hi. So I was waiting for you to finish so that I can ask the question.
Okay, okay.
Yeah, maybe later is fine.
Mm-hmm. The fourth point is that, as I said, I would really like to know, given a spectral curve in S2C, how to get a d-brane in the size S5. I think this should be definitely doable. There is a well developed general story on how to associate supersymmetric d-branes in the size S5 with holomorphic objects by Mikhailov. But Mikhailov's work does not seem to be quite covering this particular example, so it would be nice to extend it. I think knowing the D3 brane shapes would also help extending this work beyond the chiral algebra setup. I could study things like a correlation function of chiral algebra determinants, but in the presence of single trace operators which are outside the chiral algebra. It might be possible to study this problem. Sort of try to start, or maybe operators which are close to being in the chiral algebra. So it might be possible to have some kind of near chiral algebra expansion, where perhaps the Hooft coupling is multiplied by some small parameters, so that the perturbative expansion is manageable. And finally, right, the big project is to understand situations where operators are order n squared instead of order n, so that you're really inserting non-trivial geometries and finding non-trivial gravitational saddles. And that's very much in progress, but it's tricky. Okay, I think this is all I wanted to say.
Well, let's thank Davide, and then we'll move to questions. Maybe just thank you, Davide.
Hi,
Abhijit, go for it.
Hi, Davide. Thanks a lot for a fantastic talk. So I have two questions. One is about whether one can study the twisted holography in the context of lower supersymmetric operators. So here you worked with the chiral algebra sector, which preserve more than is not the minimal, let's say they preserve a certain supersymmetry. These are the sure operators and so on. So, but is there a way to do that even for less supersymmetric operators? Let's say 1/16 in n equals 4, 1/8 of n equals 4.
Yes, absolutely. So the 1/16 BPS operators are precisely what's captured by the holomorphic twist of n equals 4 super mills. And I've been looking at the problem a little bit. There is nice work by done by Minwala and collaborators first, and then also some nice work by Sheen and his student. All of those calculations can be carried over to the holographic twist, the holomorphic twist of n equals 4 super mills, and we're trying to understand if it's possible to push them further using this holomorphic twist technology.
But what is this bulk you would have in mind in that context?
So the bulk, as far as I know, it's a sort of a 5-dimensional version of the B model, which Costello and Lee introduced at some point. I don't understand it very well yet. It's BCOV theory somehow in 5 dimensions instead of 3. But the back reaction is less easy to understand. So in the context of this chiral algebra setup, you had a 3-dimensional B model, and the 3-brane back reaction turned on a complex structure deformation. So that is easy for me to wrap my head around. You know, I take C3, I deform it to something else, I get SL2C. But in this 5-dimensional setup, the D3 branes source what I think it's a non-commutativity, some kind of a position-dependent non-commutativity. And so at the moment, I don't think people know how to describe the full holographic dual geometry.
So sorry, just to ask you further about what you just said. So how do you think about the SL2C in this chiral algebra sector? Like, because in what sense the chiral algebra lives at the boundary, let's say, of the SL2C? Or
it's just a standard holographic dictionary.
It's what? Sorry?
It's just a standard holographic dictionary. It's not that the chiral algebra lives at the boundary as much as bimodal correlation functions with boundary deformations are equal to the chiral algebra correlation functions.
Okay.
But if you were trying to so what you can do is to try to derive this correspondence using the same strategy as Maldacena did for the full physical correspondence. So instead of the 3 branes in in R10, you would study holomorphic branes, holomorphic D2 branes in C3, and these backreact the geometry, and the backreacted geometry is SL2C.
Oh, I see. That's what you said. I see. Okay.
Yes.
I see. Thanks.
But if you try to do the same thing for the holomorphic twist, then you need to backreact C5 with this non-commutativity, position-dependent non-commutativity.
Okay.
And if you can understand the result, then you could do finite. You know, you could do some more interesting.
And this back reaction for the case of D3, this holomorphic D2 branes to give rise to this SL2. So this has, I mean, what is the reference for this?
So with Costello, we do the calculation, but this goes farther back. For example, the whole story about the relation between resolved conifold and deformed conifold was based on a similar procedure where you put these 2 branes wrapping a CP1 in the resolved conifold, and you claim that you get the deformed conifold.
Thanks a lot.
Okay. Any other questions, comments?
I have a question. So you got the.
Go ahead, and then there's Kaushik. Yeah, go ahead, Shomdat, and then there's Kaushik. Go ahead, please.
Yeah. So you got the action for the rho by subsequently integrating out and integrating in some fields, right?
Yes.
So once you have the solution for the rho in terms of the A's and the B's, can you sort of reverse engineer the process and integrate in and integrate out to get back the original action in terms of the X's? And then you would have a sort of handle on what kind of theory the solution looks like in the original variables. Would that be sort of some sort of help?
Well, so right, it's not clear to me exactly what that concretely means. So see, giving a VEV to rho essentially means that you're studying a situation where there is a fermion, a VEV or the fermion bilinear. And I'm not quite sure how to follow that all the way back.
You have the VEV, right? And you can always expand around the VEV.
Right, but that's a tricky thing, right? I don't know how to expand around the VEV of a fermion, right? It's a VEV of the fermion bilinear. So you know, you're using this VEV of rho to sort of encode a slightly non-perturbative phenomenon where
rho is a scalar.
Rho is a
scalar.
Yes. So if you can definitely sort of write down an action which has rho, size, and axis without integrating away rho, size, and axis, and then give a VEV to rho, and then Hooft expand that. That's definitely something you can do.
Yeah, maybe.
Kaushik, go ahead, please.
Sorry if I missed something, but about your first question of matching spectral curves of SL2C with all curves, under constraints on the degree of spectral curves for SL2C, which in turn will restrict the genus? Or I'm completely mistaken?
I'm not sure. So I should definitely learn more algebraic geometry. So at the moment, it's not quite clear to me what are the constraints on the possible genus or properties of this spectral curve.
I mean, after all, it's even dimensional thing. So yeah.
So right. So we're studying one-dimensional holomorphic curve inside some compactification of SL2C, which intersects the compactification divisor in a specific way.
Yeah. So how do you get higher degree spectral curves in SL2C?
I'm not sure what the degree is here.
So if I start writing down the usual spectral curve in SL2C,
yes.
What is the representation that you choose here?
I'm sorry.
I mean, you're writing the usual spectral curves of SL2C, right?
I don't know what the usual spectral curves of SL2C are.
I mean, the spectral equation gives you some curves in SL2C with certain kinds of singular. I thought there's a classification of Beauville which studied that. So, and if I remember that doesn't have all the degrees.
Okay, I know nothing about it. I would love to. If you have a reference, I would love to.
Okay, Beauville had this. I can probably send it to you later on. I don't have it.
So Beauville, you said?
Yeah, Beauville had some classification.
Okay, maybe write the name in the chat so I don't.
BAEAUVILLE.
Write it in the chat, Kaushik, if you don't mind. And let's take the last question while Kaushik is doing that from ICTS. Then we'll have to close. Go ahead, ICTS.
Hello. Hi. Am I audible?
Yes.
Okay. So I just wanted to ask a question about a comment that you had made about the relation between the B branes and the D3 branes.
Yes.
Can you expand upon it in the sense that what data should be compared to actually understand how the mapping goes? Is it understood? Like what calculation one should do to say understand which B branes correspond to D3 branes?
Yes. So the correct answer would be I don't know. Worse, I have an intuition which might be wrong. So my intuition is that SL2C is ADS3 times S3, and this ADS3 times S3 is a locus inside ADS5 times S5, which is preserved by some symmetries. So there are two rotations which are also preserved by the setup, and the fixed locus is an ADS3 times S3. And then, according to this intuition, the holomorphic curve could be the intersection of this M4 with that SL2C, with that ADS3 times S3. But I do not know if this intuition is correct. It might be incorrect. A better statement would be that somehow, again, the kappa symmetry constraint on the D3 shape gives you some geometric data, and that the geometric data somehow is encoded in the holomorphic curve. But yeah, I really understand this much less than I would like.
Okay, thank you.
Okay, well, friends, let's thank Davide once more. And thanks a lot, Davide, for a great talk. And before we close, I'd like to once more thank all the organizers, Aalok, and everyone from Roorkee and the entire organizing team. Thank you all very much. It's been a very exciting conference. We've learned a lot. And look forward to meeting again next year for the National Strings meeting. Thank you all very much. Aalok, do you have anything to say as the last? You have the last word, sir.
No, thank you. Thank you, everybody. Thank you so much. Thank you.
Thanks to you and all your team. They did a wonderful work.
Thank you so much. Really appreciate that. Thank you. Thank you very much. Thank you so much. Thank you. Please stay safe. Thank you.
Thank you all.
Yeah,
bye.
Bye.
Take care. Bye.
And a happy new year, I guess.
Right. Happy New Year. Happy holidays, everyone.
Happy holidays. Yeah.
Bye.
Thank you, Alok. Thank you, Alok.
Thank you. Thank you so much. Thank you.